How fun. Okay, so that's all from me. So next up, we have John with a happy intro.
Is it possible to download the slides and show them natively? That's
Yeah. Which ones are you? Oh, happy.
there it is.
Download.
Also have a secondary microphone for people to ask questions. Let me see if that works.
That would be good. Growing pains of going back to in-person. It's been a while.
Yeah.
All right, I will.
Is that being shared?
Yeah, let me. New share.
Real quick, I'm gonna test this microphone.
Stop share. Okay.
Does our guest mic work? Yes, it does.
All right.
Okay.
Cool. So if anyone in the room wants to ask a question, we've heard on Zoom, you're gonna have to grab a microphone. So I think we don't have to
Maybe
turn it
swap
over.
displays.
No, it's
Oh, no, it's good. Okay.
Can people online see the presentation?
Oh, yeah, it is showing up full screen.
Yes.
Looks good.
Okay, great. All right, so yeah, thanks. Great to see everybody in person again. This is wonderful. I'll give a presentation here on one of the PyHC core packages relating to Happy, but I'm also going to zoom out. And so the title is kind of expansive. What would you do with universal standard data access? Because that's kind of the goal of Happy. And so this talk focuses on why Happy is relevant now and in the future. There's a long list of people who've contributed to this. Some of them are up here because these are sort of the active contributors recently. Bob Weigel, Jeremy Faden, Sandy Antunes, Doug Lindholm here at last, Bernie Harris, who I saw online, Bobby Candy, Eric Grimes, who's on the SpeedOS team. So, okay, we'll spend some time talking about what is Happy, the basics, some interface details. This is for people that are newish. At the intermediate level, there's some details about how it works. You get to like the extreme details. Okay, here's what's recently changed. There's some interesting stuff in there. And we'll talk a little bit about where Happy is being used. A brief comment on and there's a chance to try it out. If people have your computer up and are online, there's an audience participation segment. Implications for service providers. Just a quick slide on that. And then focusing on where do we go from here? What's the relationship to other PyHC packages and what is it that we could work on together and envision for the future? So, all right, what is Happy? Well, the purpose, start with the purpose. It's like any other data standardization mechanism. We're trying to get sameness everywhere. And so the question is, well, where do you put the sameness? Where do you make things the same in your data system so that you can not have to repeat things over and over? And the big vision is, what if there was a single way to get to everything, right? So Happy is about time series data. So for the time series data, what if you could get to any of it with a single API? Wouldn't that be great? So the sameness, the place to put the sameness is what I call the fill my array problem, because scientists don't really care, and they shouldn't care about all the data storage details, the format, which data is in which file, how do I stitch these files together? So if you have data out there and you want to get it into your own data structures, you have to write some data wrangling code. And then you get into the data structures in your own code. That's when it's really yours, right? You can take it and then do analysis on it. And then the next thing is, oh, you come across some new data. Hopefully your data wrangling code works with that. But this whole process of taking the data and getting it into your structures, that was what I call the fill my array problem. And that's what we're trying to solve with Happy to make that more universal. So how does Happy go about doing that? Where does it fit in? Well, I'm going to spend a few minutes talking through this sort of conceptual structure of how data analysis works. If you have a server offering data, you have to have some code somewhere to read the data and make it available. If you want to make it available, you need some kind of interface or API where you have a request coming in of a certain structure and a response going back. And so Happy at its core level is a specification that defines that kind of interaction, the request and the response from the server. And so some people get confused about what is Happy. At the fundamental level, it's a specification. And then if you implement that on your server, then you have a happy server that implements that specification. And so that gets used then on the client side because there's client code that has to understand how to construct those requests and interpret those responses. And so this is where we interact most strongly with PyHC because there is a Python happy client that people can use to pull in data and start analyzing it. That's the fill my array piece. And then that client analysis program uses the data structures to do analysis. That's a happy enabled client. It might do other things besides read from happy, but if it has this library embedded in it, then it can interact with happy servers. Okay, so the happy specification, you can kind of think of it as HTTP for data, right? It's a protocol where you give some, construct some URL, and then you'll get back a specified response. And it's RESTful in that there's no state maintained between the calls. Every call is independent. And that means you can kind of think about those URLs that you end up making as a request as a kind of semi-permanent, reference to the data. I used this data. I say semi-permanent because, servers come and go, data gets upgraded. But the idea is that at least for a reasonable amount of time, there should be a kind of a permanent way to reference the data. And happy servers define endpoints that, and I'll talk about that on the next slide, but one endpoint, for example, is the data endpoint. So if you're thinking about this as a protocol, here's the endpoint piece, this is the data endpoint, and all the stuff after that is the elements required by this protocol to specify the request. And then the response, happy servers must implement a CSV, comma separated value response, and that response will be the same from every server, and that's where the sameness comes in. Okay, so the endpoints that Happy defines are these. I'm not going to go into great detail. The bottom three are the key ones: the catalog, info, and data. Catalog is a list of all the data sets supported by the server. The info, you give it one of those data set identifiers, it will give you the metadata for the data set. And then the data response is then the actual content. For this data set ID and this time range, give me the data. So, all right, so, excuse me. So that's the basics of Happy. So what has changed recently? And by recently, I mean, it's about to be implemented in 3.2. So things that we have added to the spec, and we're about to make a new release. So one thing that we got asked a lot was, can the catalog just give me everything? Not just the list of data sets, but go ahead and give me the metadata for all of those data sets all at once. And so that way you don't have to, if you have a lot of data sets, you'd have to make, a request every time to collect all that metadata. So there's now an option to that catalog endpoint that says, just stuff everything in there. It's shorter than that, but I forget exactly what it is, but you can say depth equals full or something, and then you get all the metadata. Also, Happy metadata is very limited. So in the info response now, we created a place where you can stuff additional metadata. Maybe you're serving data that has rich metadata included. Happy has very limited metadata, just enough to be able to use it for plotting and so forth. But if you don't want to discard that metadata, there's now a place in the info response you can stuff it all, and it won't conflict with other namespaces and so forth. You can at least carry it along, it won't get lost. And we recently added a new /about endpoint to let you inform people about the server. We added a way, this is really useful, and we're going to leverage this for stuff in the future. You can specify that certain quantities are vector quantities. This is a directional quantity, and these components in here represent the XYZ components, or represent R, latitude, longitude, or whatever. You can say, this is how you would make a directional quantity out of this. And it doesn't take a human to infer that, oh, look, XYZ, that must be a vector. Happy now advertises that this is a vector quantity. Here are the components, and here's the coordinate frame, the coordinate system name that it's in. And here's the schema that these coordinate system names come from. Here, we're a little bit ahead of our time because those don't exist yet. There is no community agreed upon schema for coordinate system names. John, microphone.
I don't want to digress on this too long, but this is, I think
not just a happy problem. This is a
No,
problem with
this is
everything.
universal. There's an idea working group on it.
Oh, good, good.
It hasn't really met because everyone's like, oh, this is really hard.
Because I've got two concerns here. One is that this is something we need to solve as a community, and obviously somebody solving it in draft is necessary to make progress in general.
Yeah,
But
Bob Weigel would love to work on this. I didn't see if he was online, but yeah, Rebecca has a question too. No, the thing that's in Happy is absolutely just a placeholder to support whatever hopefully appears in terms of coordinate
wanna
system
wrap
schemas.
And then my own is, it's always been interesting that Happy has tried to be pretty thin, and it seems like it's creeping a little bit.
Yeah, these are optional.
Okay.
Everything that we're adding like this is optional. You do not have to specify that this is a vector quantity.
But we should keep trying to coordinate these as much as possible.
Absolutely.
So-
Yeah, no, we are always fighting the keep it simple thing. Yeah.
There is a session that will be at Dash in October where a lot of the conversation will be about the coordinate systems. So please join.
Great, yeah, and following Dash
Thanks.
is the idea meeting, and if we can get the working group going on that, we can maybe make progress. Okay, and then the last thing that we added, we debated a long time about this, but people said, well, can I serve images using Happy? And we're like, well, sort of. You could stuff all those bits into the data, but no one wants to treat images that way. You already know what an image is. So, but we added a URI type. You can do integers, floating point, strings, and now officially URIs. And that would allow you to list out the images just as references. Go, here's the image at this URL, this URL, this URL. There's a lot of implications for allowing that. And there's danger everywhere. So I'm going to talk about that for a second. So using Happy to serve images. So this is just a schematic representation of what Happy returns. It's a tabular information. And now you can see the URI strings in there. And the reason why this kind of works for images is because people know what to do with that. What we absolutely do not want people to do, and here's the danger, is to just list out your CDFs. Hey, I have a Happy server. You can get to my data. I list out the CDFs. No, you've just created a directory listing service, not a data service, right? So, but for images, people usually know what to do with image files. If it's a PNG, your browser could show it, or a JPEG. If it's a FITS image and you were looking for FITS images, you probably have code to deal with FITS images. And so generic Happy clients won't necessarily know what to do with these images, but as customized communities build their own clients that can deal with images, Happy is capable of serving them that way. Rebecca has a question again. And I'll say more after her question.
So let me not block people. So I know one of the problems that we have with serving model data from various institutions is all of the specialized file formats. What are your thoughts about using the listing service idea to serve, say, the names of binary files that you would plug into SpacePy instead of serving a data stream for?
That could absolutely be done. And this now explicitly supports that. As long as people are aware that this Happy service is functioning as a listing service. So we're trying to find ways to maybe encourage standardization there, because if you're going to list files, there's certain things people might always want to know. So if you are using Happy as a file listing service, please use the following kind of arrangement to also include date stamp and file size and, something else like that. So that's the next level above this to try and create. So if everyone makes a listing service, there might be some cohesion there. I mean, this is the question of every data standard. You can't control what people put in there, but you can recommend schemas.
Would you be willing to allow, say, a note on maybe a comment on this serving thing, so that there would be a note on how to use this data file?
Sure. I mean, there's the Happy servers can have a landing page to describe things. Yeah. So yeah, there's lots to talk about with this. We're going to be working with, for example, the SunPy folks and the VSO, Virtual Solar Observatory, to work on how to best integrate this with what's already being done for SunPy They have a FIDO listing service. So, how can we coordinate with that? We haven't done that yet, but that's on the agenda. The other thing that we could think of is, a way to use this would be, all these FITS images have metadata in them, lots of metadata. Go ahead and put those metadata fields in the happy stream as separate parameters. And then you could filter the images after you've retrieved them on the client side by filtering on the metadata pieces. That's not a lot of extra information. And so having to pull it all to the client won't necessarily slow you down that much, but we haven't tried that yet. We're just still exploring. But we debated this for a long time. This is like a very multi-year open issue because we wanted to not let people just list. We didn't want Happy to be a listing service. We wanted it to be a data service. So, all right. There's a lot of data sets and services that are using Happy now. I won't go over this list, but Intermagnet got added this year. Simon came to us, hey, I've got this Happy thing going. Can you guys check it out? So we only interacted with him at the end to help him kind of finalize things. So that was good to see. There are several Happy services that are, I'll say, imminent or in the works. ESA is implementing one. They just need some security checks to be finalized. The Dutch Meteorological Society implemented one, and they have a very nice client that we're trying to get them, and they have open sourced it, but to try and make it a separable piece. The PDS planetary data service at the PPI planetary plasma and planetary interactions node, they have a Happy server. I'm going to be working with the NSF folks with Cedar and Madrigal. They have a Madrigal data system, and it would be great if that stuff was available as well. Okay, do I have time for this? I think I don't. But this is a chance to interact with Happy. You can try this if you want during other people's talks. Yeah, that's it. No, but this is a great way to interact with the existing Happy servers. You can go to this website, happy-server.org/servers. And what you have there is a Happy client. It's basically a bunch of JavaScript in the web page that lets you interact with a list of known Happy servers. You can pick a server. You can then it immediately consults the server. Hey, give me your list of data sets. And then you pick a data set. And so it's helping you explore what's available with Happy data. And then it can construct that query and bring you the data. And so here's an example. If you follow through this example, you will get data that you can just download and plot. One thing I want to emphasize here is the script capability. One of the options at this site is to, hey, give me a script that I can use. I can stuff this into my own Python routines, and then it makes the Happy calls for you, and it will show you how to get that into your program. This is the Fill My Array vision that we started with, right? So this site can really help you get started using Happy. It shows you what's available and even gives you a code stub you can start using in your own mechanisms. Yeah, here's the code stub from an example, not the one on the previous page, but from a different one. Okay, I'm going to skip over this. The one comment here is Happy serves finalized data. There are no options in the Happy call, just the time range. You can't say, oh, and this processing level, oh, and this whatever, because those are data set specific. That couldn't be part of a standard. So you have to serve the finalized data. These are the parameters that are available. You can serve those. And we did that on purpose because how would you standardize random options? We couldn't think of a way, so we didn't. I'm going to skip over this. Okay, relationship to packages. There's a lot of different activity going on with Happy. And we have a generic Python server that still needs work. We have, of course, the Happy Python client, and that's what's used, I think, now inside PySpeedos to bring data in and to do the Fill My Array thing inside Speedos. And there's a verifier. If you're building a server, you can check to see if you're doing it right. And I just mentioned the web page to explore Happy servers. So there's 29 different repos. I call them projects, but they're really different repositories at this GitHub organization. And some of them are Python, but there's other languages in there too. And I wanted to mention a few things now that have been in relationship to the PyHC community. One is a Python adapters project where we tried to develop adapters so that that film array piece could happen interchangeably amongst all the different packages. So SunPy could take advantage of SpacePy and Happy. If it was available through Happy or SpacePy, then SunPy could just read it right into its own native structures, and vice versa for all the other packages. That mostly worked, except we just have to finish. It just takes a lot of coordination. And so this was a $75K grant that went to like 4 institutions. So it was kind of a labor of love, and we're almost done. So we have pull requests. It's just getting that integrated at the right time during the development phase of the existing projects. It was not as easy as we thought. So this is still ongoing. There's other projects. I have to ask permission for Rebecca. Can I talk about the one that you submitted? What? Okay, good. I was hoping you would say that because I put a slide in on it. I would skip over it real quick if you said no. So, okay, and Sandy put one in too for a Happy stand-up server. Drop a Happy server on top of your data. And then you can look at your own local data alongside other Happy data that's available. And then Rebecca, and I helped with this too, but it's mostly other institutions doing the work to create Happy on top of Komodo. Komodo is already getting to a lot of model data and making it on uniform grids. So uniform gridded time series data, hey, that's Happy. So put Happy on top of that. Now Happy can reach all that model data. So yeah, there's a lot of subtleties here. I'm going through this really fast.
This is not the fly through work that other people are doing. This is on top of the model readers.
Yeah, this is the hugely voluminous model data where, like, you see the array sizes, 1,000 by 2,000 by 3,000. That's your single parameter, and you have that at every time step. Yeah. And this is, well, that's what I could fit on the PowerPoint slide. So, okay. I'm going to skip over that. The vision is universal access to all heliophysics time series data. So it's everything, everywhere, well, at any time, right? So that's kind of what we're shooting for. So here are some exciting projects that I'm looking for collaboration on. If people are interested here, we could definitely work together on this. The generic Python server could use some work. So that could be a proposal. The data adapters project, it's got that 20% left at the end that will bring us to the finish line. Coordinate transforms as a Happy service. Maybe you hit a Happy service. I want to go from this frame to that frame. You don't want to have to install anything. Just give me the matrices. Maybe we could build a service for that. A routine that takes Happy streams from all over the place, combines them, filters them, and then dumps them to your favorite file format, right? So there's a lot of things we could do. There's a idea working group on a federated search mechanism. Happy isn't really built for search or discovery, but if there was a way to include Happy results in larger search mechanisms, that would be useful. So I'm proposing here an unconference session on not just Happy ideas, but ideas that everybody has together. What could we actually propose to do next to try and build on what we've all done? So we could go over upcoming proposal opportunities. There could be, if people are new or newish at writing proposals, we could try to encourage those people or connect them with mentors. And it's a chance for us to make concrete plans on specific proposals. I think we should do that here. We're all together, so let's talk about it. And I should probably stop there because I'm out of time. I hit escape and everything went dark.
I put my presentation on the folder thing, so.
Oh, it's back. Okay. Sorry.
Gotta love it.
Okay.
Okay, what kind of thing do you have? USB-C?
If
If you have a,
the folder.
oh, okay,
so
perfect. So I'll just, yeah, I'll pull it there.
Hopefully that'll work.
Sorry, y'all.
Uh-oh.
I swear it's been like over a week. It's just the cough probably. Murphy plasma. That is likely what we want.
Yes,
Oop, 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 my bad, that one.
that might not. That's all another PDF.
Oh, there we go. This looks like
Yes,
slides. This cough is so annoying.
Okay.
Okay,
That should work.
okay, cool. All right, moving right along to Nick Murphy.
Okay. Yes, it's there. Okay. Hi, everyone. It's weird to be here in person as my second talks. My second talk since the pandemic sort of stuff. But it is still really nice to be here with all of you. And you're gonna bear with me in this talk as I slowly get more and more caffeinated. Okay. And I'll put a stopwatch so I do things. Okay. So I'm going to talk about Plasma Pi. And this is work that's been done by a whole bunch of people. So it's a real community effort. All right. So it turns out that plasma physics is fundamental to heliophysics. And that's because the heliosphere is mostly plasma. By volume, there's barely anything that isn't plasma. And there's a synergy because laboratory plasma studies help us understand what's happening in the heliosphere, especially on small scales. And heliophysics also gives us a chance to do in situ studies of plasma processes in regimes that we have no chance of getting in the laboratory. Sure. Yeah, we'll talk if so. So plasma physics functionality is needed for a software ecosystem for heliophysics. And oh, that didn't turn out quite great. Okay, so the mission of the Plasma Pi project is to grow an open source software ecosystem for plasma research and education. And by software ecosystem, I think we mostly understand that it's software that is developed together, grows together, and works together. So there are a number of Plasma Pi subpackages, and I'll talk about the 6 most developed ones. The first one is plasmapi.particles, which contains a bunch of functions and to access basic particle data and also object-oriented representations of particles, including collections of particles. Our plasmapi.formulary subpackage includes a whole bunch of functions to calculate things like ranging from the alphane speed to the lower hybrid drift frequency to various collision parameters. So a lot of functionality that comes from the NRL plasma formulary. We've had a lot of work done recently on plasmapi.dispersion, which includes, at this point, mostly 2 fluid dispersion relation solvers for plasma waves. A couple of other packages. Plasmapi.analysis includes a bunch of analysis techniques from that we can apply to simulations, experiments, and observations. It's still very much under development. There are like very big ranges of applications that we still need to add functionality for, and we need community input. We also have plasmapi.diagnostics, which is more from a laboratory perspective, but also potentially could be applied to space instrumentation. And this includes analysis for Langmuir probes, Thomson scattering, especially, and synthetic diagnostics, including for magnetized laboratory plasma experiments and high energy density plasma experiments. I want to mention a little more detail about plasmapi.particles, since it's probably the most broadly useful subpackage within Plasma Pi, and it's also my favorite. So I mentioned there were several functions that we could use to access particle data, but I want to talk about a couple of the classes to create particle objects. So we have the particle class, which you can feed it something particle-like. So in this case, it's P plus a string for a proton. You can also spell out proton. And it accepts a wide variety of formats. It's pretty flexible. And then once you create a proton, you can get attributes like the mass, charge, charge number, and so on. And then you can also, there are a couple of methods like is category to tell if it's a baryon or not in this case. We have about 20 categories or so. In the future, we might change it so that it's a particle hierarchy, but that isn't one of our highest priorities at the moment. We also recently added a particle list object, which you can add an iterable containing multiple particle representations. So if you want to create a list containing helium ions, then you can do that, He-4 1+, and then it also accepts symbols like alpha. And then with that also you can get helium ions.charge. So it has a lot of the same attributes as the particle class. We also have a custom particle class, which essentially stores things like charge and mass, but not much else. And now my favorite decorator in Plasma Pi is particle input. And this is intended for functions that accept particles as arguments. And it works alongside particle-like, which is a typing construct for the different types that can be converted into a particle. So the different particle-like objects. So we can decorate a function with it, in this case, particle mass, and we annotate the parameter with particle-like. And what this is going to do is if you pass the particle parameter a particle-like argument, then that is going to convert it into a particle. So in this case, we pass particle mass a representation of a proton, and then as it gets passed into here, the decorator converts it into a proton, so we can get proton.mass, which is pretty handy. It ends up saving a huge amount of code in other parts of the package. And there are other capabilities too for more specialized cases. Like if you have a parameter named ion, it'll make sure that it's an ion or also a neutral particle, but at least that it's an ionic level, I should say. All right, so we're in the process of decorating a lot of our functions in the formulary with particle input. And that's going to have the advantage that we can pass collections of particles and create a particle list and then get things like the gyro radius for all of them. And we can also pass things like the mass and also supply the charge number as a different argument to Z. All right, so I'll mention a couple of more recent projects and also some ongoing work. So I mentioned that we have a bunch of two-fluid dispersion relation solvers for different authors who use different approximations. And this has been done by a lot of students who were previously at the University of Delaware. So Elliot Johnson, Ramiz Kutsi, and Shane Brown. And another intern, Mohammed Haq, is implementing some functionality for 1D and 2D equilibria. I come from the reconnection community originally, so we're adding the Harris sheet, and we can add a bunch of other 1D equilibria. And we'll also have spheromech equilibria, which can include the Lundquist solution. Ends up being pretty similar. Again, motivated by reconnection. Another intern, Haman Bagarian-Lamraski, added a null point finder for a 3D grid containing magnetic field data. So if you're analyzing simulation of reconnection, and we can use this prototype null point finder. And he has also added, or has worked on functionality for getting the magnetic skeleton. So things like separators and spines and things like that. And that's his internship finished like right when it was getting good with that. So it's still a little bit of work to be done there. We've also had some functionality added for doing excess statistics time series analysis. And this is something which the motivation was for studying events in tokamaks. And there is potential for applying this to space plasmas also. And we also have a bunch of laboratory plasma diagnostic efforts that we've been working on. Not me, since I barely do anything with plasma diagnostics, but Eric Everson has worked on Langmuir probes. Peter Hoyer has worked on Thomson scattering. And then Peter Hoyer and a high school student, Jaden Roberts, have also been working on a diagnostic for high energy density plasmas, where you shoot protons or other charged particles through a laser produced plasma and see how much the protons get deflected. And with that, you can get a lot of information on the electromagnetic field in there. It's a really cool diagnostic. And then Elliot Johnson also added some functionality for calculating the thermalization ratio of plasma in transit. So I'm going to try to get this right. But the idea is that you take plasma, 2 species, and set the initial temperatures and densities for them, and then different parameterizations for how the temperature and I think density changes in, like, for example, the solar wind. And this functionality will calculate the temperature ratio as a function of time. And this is probably our most heliophysics specific functionality. It's pretty neat too. Elliot has a paper coming out anywhere between like -3 and 15 days from now in AppJ. So we'll put that in the documentation. This is going to be in our next release. So I want to mention a couple of the challenges that we've had. And our biggest one has been onboarding new contributors. And as most of us probably have experienced, it's difficult to learn things like Git and GitHub. Especially in plasma physics, it's not covered in the courses that we take. We end up taking courses on plasma physics or heliophysics rather than things that are maybe a bit more useful. But we ended up having Plasma Hack Week the last 2 summers, which Hack Week is kind of a mix between a summer school and a hackathon. And so we had a couple of 2-hour sessions per day. And this was online, so we had people from a whole bunch of different continents participate. And it was, I think it worked, some of it worked fairly well, but having an online event is different than having an in-person summer school like PyHC did last year. We also did a really thorough overhaul of our contributor guide. It's pretty extensive and it's worth checking out if you have a chance. And that includes the code contribution workflow, how to get ready for contributing, the steps you have to do to make a pull request. It includes a coding guide and also guides on writing tests and documentation. John, did you want to get the microphone?
Yeah, so does that work? I mean, you have contributions from a ton of people. I was going to ask you, are those all going to be useful long-term? I mean, we have interns and sometimes we keep their code and sometimes we don't. So, you know, how is this working, the contributor guide, and what fraction of these intern contributions are you keeping? It sounds like all of them, which is great.
Yeah, we're keeping most of them, I think. So is the contributor guide working? The one answer is it's too early to tell. The second answer is it's too long and it's intimidating. So we're trying to rearrange it so that the stuff that people need to know is at the beginning, and like the stuff on how to build documentation, how to run tests. New contributors don't need that as urgently because when they do a pull request, the tests will be run for them, the documentation will be built for them. So it's challenging. But we're going to try to keep this updated. It is pretty extensive, but that also means there's a lot for us to maintain, which is a drawback. But overall, you kind of led me into the next bullet point that we really do need in-person or hybrid summer school. So things like a summer school on not so much how to use Plasma Pi, but how to contribute to an open source project. So a research software engineering summer school. And there's one example through the Intersect program that Joy is going to be participating in July. And so hopefully you'll be able to tell us more about it, but it's going to cover a lot of the stuff that someone who has maybe some experience contributing to an open source package, but wants to level up. So John, I think you had a question.
Well, the infamous more of a comment. So as you said, there's a lot of this to maintain. And if we're thinking in terms of particularly learning Git and GitHub, the model we did with the summer school was we found a lot of the good stuff out there, right? And we tried to consolidate that and put that on PyHC. It'd be good to do it with Git. The two things I found useful are, if you just Google visual Git reference, you'll find something that actually has all of the little pointers between the commits and such. And there's also somebody gamified it. Look for Oh My Git. And it is is done up as a card game, but it shows you what the actual command line is for each thing. And so you learn about merges and branches and polling with that. It's really good. I think part of the problem is that ultimately, all of the nonsense about the index and all of that stuff makes no sense until the point where you have actually gone down a hole and you are in a terrible, terrible mess. And that's a very hard place to learn, but you can't really learn in advance. I don't have a good answer for that. But it actually comes also what you said about the Turing guide. As soon as you write enough documentation that you've got everything covered, it's too long. And one thing we tried with SpacePy that we need to go and revisit this because it's 10 years old is to have a quick start and then have that link out to the more detailed stuff. So at least you have some chance of chunking it and being at the right level. But I think also very much encouraging people, just open the pull request and we'll sort it out later is a very good way to go.
Yeah. We've also added a bunch of linter type tools that catch, and auto formatters that catch a lot of stuff and that can make the code review process quicker, in part because there are a lot of auto fixes, which I'm getting ahead of myself. But yeah, so thanks. How do I get to? Could someone know who has easy access to the chat?
Does plasmapi.particles database include things like atomic energy levels, internal structure info for doing collisions? And then he wrote out an equation.
And the what equation?
H plus E P, like here, I'll just show you.
Oh. Oh, okay. So we don't currently have things like energy levels, though I did start working on that and then got distracted. That is something that we do want to add, like ionization potentials and things like that. Sorry, not energy levels, but ionization potentials is what we'll probably add. We don't have detailed collision data for like atomic data, but Fiasco, which Will Barnes is the contact for, and just had a 0.1 release, has an interface, or is an interface to the Chianti database, and it uses Plasma Pi under the hood. So I'd say Fiasco is probably the best thing to look for. We have thought about adding functionality for like a class to represent particle interactions. We have set it up so that if you do a proton object plus, well, so let's say a deuteron plus triton object, and then the greater than sign, and then like HE-4 plus N, and that'll give you the nuclear reaction energy. But we want to have classes that represent particle interactions, but that's something that which is going to take an effort. So, okay.
Just have one more question. Does Plasma Pi cover or have any intent to cover plasma wave analysis, e.g. Stokes parameters?
That's not something that we've talked much about yet, but if you wanted to create an issue on GitHub, we could see if there's anyone who's interested in adding that. So thanks. And it's been 20 minutes. I'll try to hurry now. Good questions. We'll have to skip the sea shanty. True. So we ended up getting a table at the APS DPP meeting last year, and that ended up being pretty fun. It was a great excuse to not go to any talks, which is probably the best part of doing this. But we did end up getting into a lot of conversations, and one of the interns who's working with me now, I met through the tabling effort.
So we do that at the agency. It could be bigger than PyHC. It could be HRL. It could be something else, but have a persistent place where people can go. Oh, here's this.
Oh, microphone.
We should do a booth at the AGU, maybe larger than PyHC, but a place for people to show up to make a little progress in learning about this community and the skills that we're talking about here.
Yes, I think a booth at AGU and maybe SPD. I haven't been to SPD in a while, but cool. So I will be kind of quick about this. We have a bunch of GitHub actions, and if there are projects that want to add GitHub actions for like the release workflow, adding comments on pull requests, you can use Plasma Pi stuff as a template. We don't have a setup.cfg anymore. We'll miss you. And I think I'll mention the other stuff next time. So I'll mention briefly that we did just switch to calendar versioning. And the reason why is that calendar versioning is a bit more intuitive for plasma scientists. And we're going to have API changes in most releases, especially because we're adding functionality all the time, and the new functionality is going to change. And so semantic versioning isn't as useful. Also, most plasma physicists don't know what semantic versioning is, which makes semantic versioning less useful also. And it's also nice because we didn't feel the pressure to do like a monumental version 1.0.0 release. So that took the pressure off. And we launched Plasma Pi into space. We taped a SD card to a rocket payload, which I don't remember what it did. It measured something, plasma, something or other. And yeah, it was a CubeSat. So you can do that for other packages too. I mean, it gets beamed into space through the internet a lot, but I don't know. And I will put up the sea shanty just for fun. Yes, but without metadata, it's all just tragic. Cool. Any questions?
How do you keep getting funded? How does this project continue funding wise?
Oh, we have a NSF CSSI award, and that was a 5-year award. So we're in like the 4th year of it. We'll probably get a 1-year no cost extension, but we did get one NASA HDEE award a couple of years ago, and we also need to apply for funding from DOE because NSF, the plasma program, doesn't like to support fusion energy research. And that is like a huge area of plasma physics, which is really underdeveloped in Plasma Pi.
Right, good to know, just because that's a critical issue with packages that are stable.
Yes. Yes.
Do you have a contact for talking to DOE people?
Working on it.
Okay,
I
I'm
know-
going to throw Steve Morley under the bus here. I mean, either him or Brian Larson. Obviously, it's a different part of the complex, but they might be able to give you some insight. Into
They're at
working-
Lanel?
Yeah. So you know we do the very quick fusion energy. And I presume you're working more of the sustained fusion energy angle, but they can probably help you figuring out DOE bureaucracy, which is its own special thing.
Cool. Thanks.
And I'm gonna. This is how I know if Steve is listening, because my phone is going to blow up in about 30 seconds.
Where is Zoom? There's Zoom. I don't know how to get there.
Well, I'll unmute myself. I am listening. Feel free to drop me a line. We have a lot of different DOE programs that we work with across the lab. And if I probably know someone who knows the right person. So,
Okay.
you know,
Are you Steve Morley? Okay, cool.
sorry, yes.
All right, cool. Thanks. And
I'll pass it on to whoever's talking next.
Oh, that's gonna be Will with Senpai. So. Stop. Okay, Will. Whenever you're ready, take it away.
Yes. Can you hear me okay?
Yeah.
All right. See if I can share the screen. Okay.
Clap the neck. Thanks, Will. Go ahead.
All right, great. Yeah, all right. So thanks for inviting me to give this talk. Sorry, I can't be there in Boulder with everyone, though I have seemed to have caught a cold this past weekend, so maybe better that I'm not. So apologies for any coughing that happens. Yeah, so my name is Will Barnes. I'm one of the primary maintainers of the SunPy project. And so this is just a kind of a quick update on the status of the SunPy package and the project as a whole. This is on, of course, I'm the one giving this talk, but all this work has been done by many other people, largely and an entire community that we built here. So this is on behalf of the whole SunPy community. Okay, yeah, okay, great. And it looks like the slides are changing. The other thing I was going to say is I can't obviously see the chat. So if there are comments or questions, feel free to just, someone just grab the mic and interrupt me. I'm totally happy to take any questions during this. So what is SunPy? I think probably most people, especially in the PyHC community are aware of this, but SunPy is the community developed free open source solar data analysis environment for Python, which is a bit of a mouthful. But the basic idea is that this is a toolbox built in Python for you to do solar physics data analysis, provide you with kind of the core components for doing solar data analysis. So the first part of this obviously is downloading data. So John mentioned earlier in his talk, FIDO, which provides sort of a unified interface to a lot of the really common data providers in the solar physics field. The Virtual Solar Observatory, the VSO, is a big one, as well as JSOC, or the Joint Science Operations Center, which serves a lot of the data from SDO. And using FIDO, you can search these, a wide number of data providers with sort of these common attributes. So things like time, wavelength, or the instrument that you're looking for, and there are many others. And the kind of the selling point of FIDO is that it's extensible, so you can add data sources, and you can actually in other packages extend FIDO to search other data sources in addition to the ones that SunPy supports. And I'll make a few comments about that later on in the talk as well. The other kind of core component of SunPy are containers for the different types of data formats that we support. So these are the map data structure for 2D spatial image data, as well as time series data, where this is a single one-dimensional quantity varying over time. And so what these data containers do is essentially couple the data with the associated metadata, as well as provide a few operations that you can do on those data products. So metadata-aware operations that you can perform on those data products. So the last core component of SunPy is our coordinates package that allows you to do sort of transformations between solar coordinate systems. And I'll say a little bit more about that in a slide or two. So just one quick note about our data containers. So we have the map data structure, and the basic idea is that you can feed. There's various ways to construct a map, but the easiest way is to stick in a FITS file, and this allows you to visualize your 2D image data with the accompanying coordinate system, as well as to extract. It also provides sort of a high-level interface to the underlying metadata, so you can use these properties like the observatory or the wavelength, and then you could also access the sort of raw underlying metadata as well. And our time series container works similarly. I can feed it in the name of the file. In this case, is the netcdf file from the GOES XRS instrument. I can do some visualizations of what that time series data looks like, and then I can also access the underlying metadata through a series of derived attributes. One thing to note is that our time series work, as people probably know from some traffic on the mailing list, I think that David Stansby had put up, that there's an effort to kind of reassess the best way to construct our time series object. So currently this is backed by a pandas data frame. This was a decision made 5 or so years ago. We're currently exploring, what are there better ways that we can construct this time series object, either through something like an AstroPy table or Xarray or some other sort of backing data structure. So the other component I'll talk about really briefly is coordinates. So it again, I know this was brought up a bit during John's talk, and I will again echo Rebecca's advertisement of the session on coordinates at the Dash meeting in October. We can have a lot more discussion about that there. But just briefly, the SunPy coordinates works by extending the AstroPy coordinates framework. So AstroPy implements coordinates as essentially nodes on a graph, and then the transformations between those coordinate systems are edges on that graph. What SunPy does is extend that framework by adding solar specific coordinate frames as nodes to the graph, which allows you to transform from the kind of more general AstroPy coordinates into these solar specific coordinate frames. And it means we don't have to rebuild an entire coordinate system framework. We can just add to the existing AstroPy coordinates framework. And then we can, the only code that we need to support is the code that actually implements these solar specific frames, things like the heliographic Stonyhurst frame or heliographic Carrington or helioprojective. So this is just it's a code snippet that basically shows, I can implement this a coordinate using this AstroPy SkyCoord object as in the helioprojective frame, which is the coordinate frame that many of our images are in, and then I can transform this to an AstroPy coordinate frame, specifically an alt-as coordinate frame centered on Greenbelt, Maryland, and that this just works because of the way that we implement our coordinate system on top of AstroPy. Another one of the benefits of this is that we can then transform any coordinate we have to the pixel coordinate system of an image, also using the kind of underlying AstroPy machinery, and that we can do these coordinate transformations for different observing viewpoints. So these are magnetic field lines I'm showing overlaid on images as taken from different viewing angles. So the SunPy project, I've been talking about code, and I'll mention a few other of our affiliated packages outside of kind of our core SunPy package. But it's not the project is not just code. It includes people, which are the maintainers, and then people that occupy these sort of specific lead developer, deputy lead developer, which is myself, these community roles. Then we also have sort of many contributors from the larger community, both from the larger scientific Python community and the solar physics community. And then we have users, which are also part of the kind of wider project. The other kind of component of the project is a kind of engagement with the wider community. So this is going to community meetings or science meetings, things like SPD or AGU, or more focused scientific Python meetings like SciPy, which is held every summer. And then also, of course, engagement with Python and heliophysics, like we're doing right now, either through meetings like this or through the summer school, which happened in Madrid last year. So just a quick note on this affiliate package system. I mentioned this briefly, but the kind of the way we the project now operates is that we have these kind of core components, things like coordinate systems and getting data and data structures in the SunPy core package. But then we kind of leave the kind of instrument specific or more analysis specific tasks to other affiliated packages. So one of a few, I'll just quickly mention a few of these. One of them is IndyQ, which I think several people are aware, which is for n-dimensional data with an accompanying WCS or World Coordinate System. Another one is PFSSPy for performing potential field extrapolations that's maintained by David Stansby. The SunPy SOAR client, which, sorry, was there a question? Oh, okay, all right. Which is is an extension of our FIDO system for searching the Solar Orbiter archive. SunKit Instruments, which provides kind of a sort of grab bag of instrument-specific functionality. SunKit Image, which is a package for specifically for image analysis, and then AIAPy, which provides routines specific to the atmospheric imaging assembly instrument on SDO. So things like calibration of images to correct for degradation and things like that. So the kind of model that we're developing is this model where we in the SunPy package, we have this sort of these this core functionality, and then instrument specific or analysis specific tasks are spun out into these affiliated packages. And then there's more on our affiliated package page here. I think I've talked about this at previous meetings as well. So this is just a quick illustration of this. So if, say, you wanted to do an analysis of a particular active region as observed by these three instruments, AIA, another EUV instrument on Solar Orbiter, and then another EUV instrument on Stereo A. And in this particular observation that I'm showing here, these three instruments all observe the same bit of the sun from three different viewing points. And what I'm kind of briefly illustrating here is the derived magnetic structure from the magnetogram shown from these three viewing points. This is what these green lines overlaid on this last row of images here. And so to do this type of analysis, we actually need several pieces from this ecosystem that I've just described. So the first part is the SunPy package to actually query the HMI data and the AIA and stereo data. To actually get the solar orbiter data, we use the SunPy SOAR package, which enables us to search the solar orbiter archive with FIDO. We can then also use AIA-Py to prep our AIA images. And AIA-Py, because it depends on SunPy and is an affiliated package, it understands these map data structures that are implemented in SunPy. And so it operates on map data structures and then returns map data structures. And the last bit of this is using PFSS-Py to derive the extrapolated potential field from our magnetogram observation. And PFSS-Py, because it depends on both SunPy and AstroPy, returns these sky chord objects that can then be overlaid on top of our map objects, and then we get all of the coordinate transformation functionality for free because they are already AstroPy coordinate objects. This is just a quick illustration of how all this works, and this is described more fully in a paper that we published in the special issue of Frontiers. I think a lot of people in the PyHC community also published it, so there are a lot more details there. So just a quick summary on kind of the status of the project. So these are stats that I pulled up like right before I started this talk. So this first one is on the top is just the number of unique contributors with different number of PRs merged. So you can see that there's a lot of contributors that we've had that have just merged a single PR. And then we have, many fewer contributors, and this, you can see this is almost power law like-ish that have merged a lot of PRs. So this just sort of illustrates, I think, the bus problem that a lot of our projects have, that we have, a lot of the effort is kind of rests on the shoulders of very few people. So we want to change that. We want to increase, these numbers farther out here. We want more contributors with larger numbers of contributions. But looking at this kind of plot in the lower left over time, that we see we have an increasingly and there are a few spikes, particularly around our release times, where we have a number of merged PRs, and then there's kind of a moving average here. So just all this to illustrate that we see continued growth and activity on the project, and all this data is actually on this dashboard that's provided by the Scientific Python organization. One other comment, just kind of related to our kind of use in the larger solar physics community. Our paper that we published on our 1.0 release back in February of 2020 continues to see large numbers of citations, and actually is up to nearly 150 citations. Of course, we know that things like citation counts are not accurate metrics for many things, but it's one sort of proxy we can use to say, okay, is our software being used in people's analysis workflows? And actually, just as of today, we've released our first release candidate of our version 5.0. So you can go and download that from PyPI through via pip, and I think it should be also on CondaForge within the next day or so. So just to briefly, quickly mention that we had our first in-person coordination meeting last year in Dublin, Ireland, at the Dublin Institute for Advanced Studies, who graciously hosted us. Just a few brief things that came out of this. So we talked about a lot of things, but one of the points that emerged from this is that we have a lot of documentation. That this goes back to the things that Nick was talking about as well during his talk, but that our docs really needed reorganizing. The other thing that I'll quickly mention is that we developed a roadmap of things that we wanted to do kind of in various various points in time. And a few of these were, we want to support spectral data, and we want some better support for higher dimensional data. So do data procs beyond just 2-dimensional images like I showed. And then the last one was enabling sort of workflows with SunPy at scale, specifically in the cloud. So since our meeting back in that was August of last year, we've done a lot to overhaul our documentation. So this is just what our landing page sort of looked like at version 4.1, and this is what our current landing page looks like in our upcoming release of 5.0. But this sort of overhaul is not just aesthetic. I mean, of course, aesthetics are important. You know, what the especially new user sees when they first come to your landing page is important. But actually, this documentation overhaul follows this kind of philosophy of a separation of documentation depending on the needs of the user that's using your documentation at that time. So this is not an original idea. This comes from this idea of a documentation diataxis, which is at this webpage. And I'll add a link to these slides in the chat when I'm done, so you can click on these links. But the basic idea is that you separate your documentation into these kind of 4 categories. So tutorials, how-to guides, explanation, and reference. And the lines between some of these categories, as we've learned over the past sort of 6 months or so, can be very hard to distinguish, especially when you're taking existing documentation and trying to fit it into these new categories. So, you know, looking at those kind of nice badges that we have on our new landing page, we've actually built, completely refactored our new user guide into a more proper tutorial that sort of walks a new user through how to use each component of the SunPy package in a sort of a linear and especially new user-friendly way. We've also tried to take a lot of our to refactor a lot of parts of our documentation into sort of short, more focused how-to guides. So these are things that answer like in a very straightforward manner, how do I do this very specific task? So these are things when a user is, you know, in the midst of doing their scientific analysis, they want to know how to do a thing with SunPy. Let's say how to, you know, parse a date time into an AstroPy time object using SunPy. We have a very we advertise very clearly how to do that specific task, for example. The other portion of this is explanation. So these are more things that give sort of the more background or theory behind why things are built the way they are in SunPy. So these answer more why questions as opposed to our how-to guides, which more answer how do I do this thing without the explanation component. And then the last portion of that is reference, which largely consists of just the API reference, but can also consist of other material. So I'll wrap up very, very quickly. It just one of the last things on our roadmap is that we want to have better support for multi-dimensional data. So this includes things like stacking 2D images in a time series. And one of the tasks on this roadmap is using NDCube, the package that I mentioned earlier, to actually rebuild our map data structures so that extending map to higher dimensions is easier. The other component is support for spectral data, and this also kind of intersects. This is almost sort of a specific subset of this generalizing to multidimensional data. Is that currently within the kind of SunPy core, we don't have support for like things like slit spectrograph data, which are heavily used in solar physics. Things like Hinode ice or the IRIS spacecraft. And so that's sort of a key area that we wanted to target within the next year. And then I will just briefly say that we're also focused on ways in which SunPy does not perform well at scale. So this is in the context either of in HPC centers or in more kind of cloud environments, things like the Helio cloud environment. So where are the pain points when someone wants to use, for example, SunPy to do some analysis on, you know, a terabyte of data with 100 compute cores or something like that. And we actually have a talk at the upcoming SciPy meeting about this, and a lot of this work is covered under the funding we received from the OSTFL program through NASA. And I'll go ahead and there and just have these links up there for the various ways that that you can get in touch with us at the project. So thanks very much.
Any question?
Yeah, nice talk. This is John Vandergriff. What are the prospects for having SunPy be more of a full replacement for the IDL, SolarSoft? I know there's some things, so many instrument pieces in SolarSoft that are going to be not really possible to bring across, but what's your view on that now?
Yeah, I think that's the difficult question to answer. Initially, kind of the early days of the project, I think, when it was first started, the idea was to kind of have, SunPy be a wholesale replacement for SSW. But for people that aren't aware, SSW is essentially like a monolithic repository of every single piece of IDL code you need to be a solar physicist. And it's, that there's a lot of advantages to it being a monolith. But the kind of model that we've adopted, as I mentioned, is that SunPy, the kind of SunPy core package provides these kind of roughly three pillars, the kind of the things that sort of span different analysis workflows: data containers, getting data, coordinates, and that then other packages, kind of affiliated packages that depend on SunPy, implement that more specific functionality. And so a key piece of that, as you said, is a lot of these instrument-specific analysis workflows. And what we really need, and I think what we're trying to facilitate, but that is still very much work in progress, is sort of dialogue between different instrument teams and the SunPy team to kind of facilitate development of these affiliated packages. So this is happening. So the one I mentioned, AIA-Pi, which is developed primarily by the Lockheed Martin, who runs the AIA instrument. The other examples are XRT-Pi, which Nick and Joy are heading up. And we've worked really closely with them, such that there's interoperability between XRT-Pi and the kind of wider SunPy package. But it's really it's almost more of a community building exercise than it is a technical one, if that makes sense. Yeah, so it's much harder.
Yeah, no, I agree. And so what it was several years ago now, but Solar Orbiter adopted SolarSoft, right? And so what can the community here do to help the next mission sort of not do that, right? To go with SunPy. What is it that we, PyHC, can do to help with that?
Yeah,
or
I think
should we ask NASA? Should we ask NASA to weigh in, or what's your vision for the future? How do we make it better?
Yeah, yeah, I mean that it's hard. I think knowing like why instrument teams are choosing a particular technology over another, so I think there are actual gaps in the functionality that we currently support versus what they need, and then there are perceived gaps, right? There are things that they think can't be done with SunPy or Python. Both of these happen, but just because we don't support it currently doesn't mean we won't. And I think we want to kind of, I guess, close the the feedback loop, especially between the kind of core SunPy contributors and instrument teams, such that we are aware of what those like actual or perceived gaps are, so that we can work on filling them before they start developing the software either in IDL or reinventing something that already exists.
Cool. Jack.
Hello, can you hear me?
Yes.
Yeah, so at least for the older missions, then, you know, a SolarSoft plus lower level data equals higher level data was the model. But going forward with, we have things like, you know, open science requirements. That previous model doesn't really work with open science requirements. So I think higher level data products that don't require any particular environment, including a Python-based one, just as long as you can read the data into the data analysis environment, I think those are the way forward for solar physics. So I'm hoping that the open source, the open science requirements will change the game going forward.
Any other final questions for? Looks like not. Well, thanks again, Will.
Thanks.
Okay, technically the break was ending now, but we're gonna go ahead and give ourselves 5 to 10 minutes to rest and not stare at our screens. So we'll be back shortly, all online.
Let's see. Yes, yeah. So it's actually fairly straightforward. It's EA works. I'm not a few years on, you know, just check it out. Yeah. I think it's actually. If we end up having like 10 billion scheduled overruns, my talk tomorrow is highly compressible.
Okay,
So-
sounds good.
Or if that's,
Sounds good, sounds
So-
good.
yeah, I did no problem.
get back to it. So we're gonna start up with a SpacePy overview by John Niehoff. I will share the screen now. Okay, should be good to go.
All right. So Julie, can you keep an eye on the chat in case anybody? So given the amount of conversation we've had, what I'll probably do is just blow through really quickly. And so call to have the brakes slammed on if you see something you actually want to see more about, rather than having this be some sort of AGU talk. So yeah, talking about SpacePy, give you a little bit of a overview of what it does for those who haven't seen or want a refresher and kind of where we're at. So we really emphasize the fact that SpacePy is just one tool in the box. We're not trying to be one-stop shopping. We're really building on NumPy and SciPy and Matplotlib as part of this whole ecosystem, and leaving things that are very general, such as in Matplotlib and SciPy, to those general packages. Let them do the work of maintaining it. So we're kind of a mid-level package, does a pretty wide range of things, not necessarily meant to be a fully integrated environment, but hopefully help support some of those fully integrated environments. Open source, of course, under the PSF license, which in retrospect was a mistake. We should have done BSD, but that was what people were doing at the time. That involves getting Los Alamos tech transfer on board. So yeah, so it took a year to do that initial release. Well, I'm not sure. So I don't even want to open the can of worms because we got, oh, this is being recorded. We got permission to do the initial release, and since then it's been based on, look, we're getting contributions from all over the place. It's open source. It's and I don't think we want to invite lawyerly attention at this point. So, but the good news, PSF is of course fully BSD and GPL compatible, and so it looks a little funny, but it doesn't cause any real problems. So as I mentioned, we're mid-level. Most of our domain is kind of ionosphere out. So MI coupling magnetosphere out into the heliosphere, because that's where we are as developers. And the development's driven by what we need to do scientifically or operationally, or what other people need to do scientifically or operationally. So it's hopefully beyond us. We have a very lightweight data model, which is basically NumPy arrays with sprinkles on top. And we can pull in a number of different file types for that. Now we'll talk more about that. We've got Sphinx documentation. This is not news anymore for anybody. Support a lot of models. We have magnetic field models backed by the Urbam library. We can pull in the 89 AP9 model, plasma pause models, other empirical, and processing of space weather model framework outputs. And then the Urbam library gives us a whole pile of things. Bunch of things we do tool-wise, have CDF reading. We have time and coordinate conversions, which are internal in pure Python, but we'll let you go out to AstroPy so you can work between that. Superposed epoch analysis, a bunch of other stuff. So here's the real motion sickness portion of the presentation. Just one slide for a bunch of publications that have been done using superposed epoch analysis to look at GPS particle data. So Steve did. So we're using our empiricals, using L-star and that superposed epoch analysis. This is some of the PyBat's work visualizing space weather modeling framework outputs, both visualizing, doing some of that field tracing, being able to pull in the Omni data. This is some of my thesis work, looking at associations between specific events. We have a transform library based on using quaternions. So this is just using some MS data on that. Some binning and plotting of spectrograms. about from time series to a spectrogram representation. Our Parker Solar Probe ESIS data processing is Python soup to nuts. We've got 16 releases. Orbit 15 got released yesterday. So you check that out. Some other papers doing some storm predictions, doing some a radiation sensor on a CubeSat and mapping down. This is a modeling paper, a response to a pure northward to pure southward BZ for a very extreme storm, so kind of a synthetic case. Again, all of the visualization then being done with PyBats. It's a new combined electron flux product for ECT on Van Allen probes. This is a pitch angle resolve one. It's backed by SpacePy. Doing modeling of the HOPE instrument response. L-star mapping down to ground magnetometer stations. This is fun one. This is North American Power Symposium, if I remember correctly, and looking at modeling of power grid failures due to geomagnetic storms. And the latest RAM SCB paper, which again, PyBats will helps visualize the output. Response in the radiation belts to CME sheaths, most recent. And so the DOIs are on most of these, so feel free to jump in and take a look at these. It's interesting. So in terms of development of the package, so since the last update a year ago, about 200 commits. We've had one of those from a non-developer, thanks to CCMC. And honestly, in general, it has been really useful to have Komodo using our coordinates backend, because there's nothing like a user for helping you find everything that you thought you had right. So it's very much appreciated. We're managing to keep ahead of the issues and PRs, and we've got 2 releases. I was hoping to have another release before now, but we'll get into why shortly. So that one release was a little bit of functionality that we have a neural net based L-star simulator that we managed to rewrite and drop the dependency while maintaining the same output. Added one set of coordinates to the coordinate support. And the big thing was getting the Apple Silicon support lined up, which involved John opening up his wallet and just plain buying one. So that involved quite a bit of overhaul of the Mac installer. So if you're a Mac person, haven't looked at this in a while, this should be a lot more straightforward and getting easier going forward. And then 041 was basically just some more installer stuff going on that. Wrote a new software paper. This is the first actual SpacePy write-up since the SciPy 2010 conference. So that went in the Frontier special issue with a lot of other things from this community. And really kind of having 2 main thrusts. One is introducing the way SpacePy and the rest of the ecosystem enables science. So showing some examples of that for folks who are looking to get stuff done. And then also discussing how, from an engineering perspective, SpacePy fits into that ecosystem, fits into this community. So there's the DOI for that. We did get a little bit of NASA support, managed to get about quarter time for a junior developer. The main goal here was to focus on responsiveness to issues, working on standards compliance with PyHC, where really it's testing coverages, where we're a little bit short right now. Do the installer updates. So when we put that in, I actually had a person identified, and before they actually started working on this, they left the university. So we're back to square one on this. So I'm trying to take care of some of this myself, and hopefully I can get some undergrads on it this summer. But it's just the ongoing thing that with the level of support that we're able to have, it's hard to have people really dedicated to this. And I think all of our projects have that problem. Okay, so what's coming up? So we have an 0.50 releases, what's going on. Our data model is format agnostic in the sense that we don't impose an interpretation on it, but we're starting to put in a lot more. If you're using ISTP metadata, then you can do a lot more with it. So making it very easy to just pull in primarily out of a CDF and get a plot right away. And the target here is the data model work really that John was describing earlier, to be able to pull stuff out into indie cubes and time series. But then you have some of that visualization. So John already mentioned this. Skip over that. So I have a fork of SunPy right now. I haven't opened the PR yet because I'm still shuffling data around to again pull SpacePy data straight out into time series, similarly out into IndieCube. Nothing quite so exciting as seeing IndieCube plotting particle flux data in terms of stretching things beyond where they were meant to go. But it's there, it's cool. And then similarly, working on some inputs that Jeremy Faden and Sandy Antunes did to pull in from Happy and from the time series into that. Was anything showing up in the chat? I'm seeing like numbers pop up. I just want to, okay. All right. This is Dan Welling, can't turn around a plot with 1 hour notice. So merged is being able to do per fluid parallel and perpendicular velocity calculation out of a SWMF model based on the simulation. And then we got two big blockers really for 050. One is finally stabbing distutils in the back and moving to setup tools, including edible installs, because I know people like those. And the other is finishing up this data model work and getting that merged. So once that's done, 050 will come out. Other stuff that's going, Dan is working on full 3D space weather modeling framework support in PyBats. And then going forward, so we no longer support Python 2, but we're basically ripping out the Python 2 code kind of as we trip over it. So that's always fun. Nothing like deleting code. Right now we deliver binary wheels for Windows. Honestly, probably with 050, I should be able to get those for the Mac as well, since that ecosystem's changing. And eventually with Linux and such. And basically, if you need something binary, we're going to try to get stuffed into the wheels, including like the CDF library. Eventually do a documentation overhaul. And in general, all of this stuff lives on GitHub. We've got issues, we've got projects, we've got discussions. So what we do is right there. And the slides are up on the meeting page already. So yeah, so things that would be great to discuss here. One is just where the heck do we put large sample data sets when we've got tutorials and notebooks and such? And sorry, Rebecca, do you? Somebody throw a microphone.
Helio Cloud.
Well, yeah, but then I need to ask. So that's for people running them in Helio Cloud, but if people want to actually do stuff locally, we can also have this conversation elsewhere. I'd just be curious to see what people are doing.
Ask Brian Thomas to get on Helio Cloud. Say pretty please.
But then is that going to be accessible to folks who haven't said pretty please get on Helio
Yes,
Cloud? Okay.
because we can put them in S3 buckets. However, in SpacePy's case, that means you have more to add to your next
You're
release.
getting ahead of me.
I'll be quiet.
So then the other thing, which I did put in as an on-conference, so hopefully people will vote for that, is to talk about how do we do interface design for cloud-enabled analysis, right? Do we say everything that takes a file should also be able to take an S3 reference and a happy URI and an HTTP URI, and we have this stuff threaded through, or do we figure out some way of doing an appropriate interface layer that makes this hopefully as seamless as possible, but without shoving acquisition code in the middle of our analysis code?
You're probably in a good spot to make like a permanent URL for your sample data sets that then redirects to something that you can configure each time. So that, this year it's on Helio Cloud, maybe one day Helio Cloud refactors and the ID needs to change. You can change that ID in your redirect, and then your code from previous versions still works.
Yeah, so the tricky thing is, where do you set up the redirect such that it goes through cleanly, and what to use for the backing?
This is HTTP redirect. pretty much anywhere.
Sorry, go ahead. Yeah, this is John Vandergriff with a comment. There's talk of federated registry development at the idea level. What can we do internationally to make a federated search work? And it could return S3 references for Amazon. It could return, other things. And as things move around, the registry would hopefully still know where they are. And then your application, I think all the core packages should be able to handle S3 references so that if your search is happening in the cloud and you want to go cloud to cloud, it can, oh, that's S3, I'll get that in the cloud. So, a lot of people are putting this cloud enabled analysis. That was one of the future things in Happy I didn't have time to get to, but we're trying to look at that too.
So, not wishing to sidestep, well, no, I'm totally wishing to sidestep the S3 discussion. I don't actually think that we necessarily need to have that in relation to, say, large sample data sets for tutorials, right? Like, so for the cloud-enabled analysis, sure, I think we need to do that. For the large sample data sets, honestly, your tutorials probably aren't changing at a very high cadence. And you realistically don't want them to either, right? So something like, Zenodo or Figshare or DataDryad, like one of those data repositories that will issue a DOI and then actually provide you a way of just downloading the file. Is probably, that would be my recommendation for large sample data sets for tutorials. Get the tutorial finished up, put the data and the tutorial on Zenodo, and then have your tutorial without the data, but pulling the data from Zenodo, like linked to your project or in your documentation. That's how I would do it. I mean, it makes it more persistent and citable.
But Steve, does Zenodo actually host the file? I thought it just minted the DOI and did the linking.
No,
okay.
Zenodo is a data repository. They'll let you store up to, I think it's something like, it's not huge. It's something like 20 or 30 gigabytes per entry. If you need more than that, you can get it. You just need to specifically go, like there's a help desk you can go to handle larger entries. But they are an archive.
Steve, when it's on Zenodo, that you would have to actually go to the Zenodo webpage and click download. There's not.
No, you can access that programmatically.
Okay, so you could have like a feature in your library, like .download sample data, and it would pull it automatically. That's great.
Yeah.
So this sounds like something we should document somewhere and maybe slap up on PyHC page, or which actually gets to, I forgot to put the other on conference I want to talk about is, we can talk about tomorrow, but ways of capturing best practices and suggestions and that kind of thing without always reopening our standards document. So, but we'll talk on conferences tomorrow, right? Okay. Anything else? Cool, I managed to give you back 2 minutes. Thanks.
Okay, I'm pretty sure, Russell, you're up next with PySat.
Yeah. Is that coming across?
Yep.
All right, great. Thank you. Hello, everyone. So my name is Russell Stoneback. I'm going to be talking about the Python Satellite Data Analysis Toolkit, or PySat for short. And then, of course, I'm not working on this package by myself. Also, it's has significant contributions from Angeline Burrell, Jeff Cleansing, and Jonathan Smith, as listed. All right, so There we go. So the technical summary, PySat implements a general data analysis workflow for arbitrary data sets, providing a consistent manner for obtaining, managing, analyzing, and processing data, including model and observational ground and space-based data sets for the space sciences. So the short answer is that PySat's interested in the full life cycle for data analysis, from getting the data to doing everything you need to do with it, as well as publishing. And it's more than just for scientists taking data that already exists and analyzing it, but for people that need to generate it, either manning a ground station, processing instrument outputs, and things like that. So another way to think about PySat is kind of like GarageBand, which is audio recording software that's included with Mac software. It gives people like a recording studio on their computer. And within the software, recording engineers and musicians can do pretty much anything they want. Once they record a sound, they can do anything to it. And that's because GarageBand and programs like it are based off of a plugin architecture, right? You have a main program, the GarageBand itself, that the user interacts with, but then it has a defined set of methods that other people can write that modifies the data. And this kind of structure gives programmers and recording engineers the versatility to literally do anything to the data. So PySat tries to have that same type of versatility, in that we want scientists to be able to do anything to data that they want in a way that's rigorous and versatile and easy on the user. Help out in all the areas that we can. So PySat's goal is not to necessarily do everything for the user, but make it very easy for users to modify the data in arbitrary ways and within arbitrary data flows. So there are two main classes that users can access. One is the instrument class, the other is a constellation class. The analog for the instrument class is like a single audio track. This will load a single type of data. Data can be loaded into Pandas or Xarray. PySat manages metadata, so that way there's a consistent experience for users and tracking metadata regardless of the underlying data format. There's a variety of ways to load the data via the PySat itself, as well as iterate, break it down, modify it, engage all kinds of other options, and apply custom processing. On the other side, there's the constellation. The analog is like the recording console. So the constellation is for a collection of audio tracks or instruments. So it doesn't have to be the same instrument or the same type of instrument. It could be some space science data, some space weather indices, some model data, arbitrary other data. And it gives the user a way to combine all those data sets in a way that's both flexible and rigorous, and hopefully accounts for all the different kinds of situations that you encounter when you're analyzing multiple data sets at a single time, right? Okay. We started just with PySat. We've since expanded it to the PySat ecosystem. And we just published a paper with this topic, with that title, on the Snakes on a Spaceship special issue in the Frontiers that everybody's been talking about. The DOI is up there. So this is our second publication. The first was in JGR some 4 or 5 years ago. 2018. There we go. So the paper kind of covers why is PySat the way it is, right? So as I've noticed, PySat is going after the full life cycle for data analysis, which includes data production all the way through analysis, and distribution and all of that stuff. And it's also built with the assumption that despite everyone's best efforts, it's just really not possible to get everything onto a single standard. It may be possible to get a single group, or maybe NASA can get on a single standard for new data, but then if it's different from the old data, then then there's work involved in perhaps translating those old files to new ones. Obviously, there's different places you can put that type of translation. But even if, say, NASA sorts itself out, NSF might be doing something else, NOAA is doing something else, Air Force is doing something else. And then in a more expansive view, where it's not just science data that we're going after, but any data a user has, in the wider world with commercial entities and all kinds of things like that. Just don't think there's any way to get everybody to agree on doing one type of thing. So PySat is designed to be able to accommodate any kind of format or whatever, so that the translation happens in an intermediate layer, so that the users get a consistent experience, but it allows them to get that consistent experience regardless of where the data comes from, whether it's from a funding agency or self-created or, what have you. And then, of course, it's also focused on instrument processing and other things like that. So there's a certain generality and versatility to the data that is built into the way just PySat approaches it, approaches the features and its and its path to data analysis. The paper then, of course, covers the features and the workflow and what we've been calling the penumbra environment. So it's all the supporting ecosystem packages that go along with it. So I mentioned before that GarageBand is a plugin design. Well, so is PySat. PySat provides the core interface for users to work with, but a lot of the data support and other things actually come from these penumbra modules. And it's designed like that to help form a community engagement and make sure that users can also add whatever kind of data set they're working with in their own environment. The paper then covers a variety of the supported data sets that PySat covers, and we include a variety of examples. So I have the first one on the screen here. So this is kind of a canonical example, and that it'll imports packages that you need. PySat manages data for you, so you have to set a place on your system or on the cloud server that you're working on where the data is going to be. In this case, we're also registering a module that we're going to be using. The data directory and the registering modules only only have to happen once, but since this is an example, we're including it here. The core part is where it says ACE is equal to PySat.instrument. Here we're instantiating an instrument class. In this particular case, we're using data from the sweep'em instrument off of ACE, but the path or this code that we have here will work for any instrument. In this case, you just have to put, instead of ACE, you'd put a different instrument name. Instead of sweep'em, it would be, instead of ACE, it would be a different satellite name. Instead of sweep'em, it would be like a different instrument name. Next, the ace.download, it downloads it from wherever the data is hosted. In this case, we just want to load everything, so we do ace.load. And then the final one is just general code that will it'll iterate over all the variables that have been loaded, provide an informative title, include units and all that using our metadata support, and it'll provide a plots of what's going on. So on the right is just an example of what the plots come out from ACE sweep'em for 3 of those parameters. So here's the PySat ecosystem visualized. So again, the PySat is the main user interface. So it's like the GarageBand or the Logic Pro, whereas all these other packages are kind of like the different audio plugins or things like that other developers can write that will then interact with GarageBand to modify data in ways that the user wants. In this case, so something like PySat and NASA, mostly will be a data provider. So NASA has a ton of different missions. In this case, PySat NASA groups support for all our different NASA data sets in one location. The reason being, once you figure out how to download data from NASA, it pretty much applies to most of the other instruments. And one of the recent things that have been incorporated by Jonathan Smith is, and I don't remember the name, but there is a NASA API now for downloading the direct files and locating them off of the SPDF server. So PySat NASA is now transitioning to using that whenever possible, and then just falling back to our old behavior as required. So PySat NASA includes support for finding NASA data, downloading it. If you have a NASA data set that's not currently supported by PySat NASA, then there's already a lot of support there for adding new data sets. So we have had some contributions from Luis Navarro recently on the gold data sets that have expanded gold coverage and things like that. PySat CDAC is similar, but instead of NASA data, it's data coming from CDAC, Cosmic Data Analysis and Archive Center, or something like that, I believe. PySat Madrigal is again similar, but instead of from CDAC or NASA, is coming from the NSF Madrigal database. So in this case, there's support for DMSP satellites, as well as ground stations like the Hickamarco Radio Observatory down in Peru. PySat space weather includes a variety of indices, that are just common for space weather. And PySat models provides support for models. So it's got support for TIGCM, SAMI, DyneOS, which is a model that I've been working on. So these things aren't usually interacted directly with the user doesn't directly interact with these packages. Typically, what will happen is the user may want a data, an instrument that's coming from one of these. So when the user says, hey, PySat.instrument, and puts in, the data set and stuff that they want and tells PySat download, PySat is then going to go to one of these packages, the plugins over there, and said, hey, the user told us to download. So, download. So that way, what it does, it provides a consistent experience for users kind of wherever things are going, and it makes sure that the framework and support for coupling external packages into PySat is top notch, because that's the way all the developers, that's how we interact with PySat. So if you're a user and you want to do something with your own data set, add support to PySat, then the tools are well formed and well supported and documented and all that kind of good stuff. That's most of these packages. And then from there, you can build analysis packages on top of PySat, because PySat will provide any kind of data set in a consistent and instrument independent format. So you can do things to build on top of that. So PySat missions is to help plan a mission, either for a proposal or during reality. You can couple it into orbit propagators and other things like that. And the data from that orbit gets expressed in the same way any other data does in PySat. And then kind of outside of that, there's a package I've been working on, OMMBV, which provides an orthogonal basis for multipole magnetic fields. So it's crucial for analyzing plasma behavior, electric fields, the dynamo, fundamental space science stuff. So that in itself doesn't use PySat, but to couple into satellite missions and stuff, it does provide a PySat interface and some functions that couple into the PySat system, make it easy for a user to add all that type of information for a satellite mission or anything like that to their own data set. And PySat and OMMBV and other things like that are all being used as part of the ICON mission for the processing of the ion velocity meter instrument on there. And it's the same type of instrument on the Cosmic 2 platform as well. So that's a constellation, and there's 6 of them. So there's a CubeSat out there, or there was. They had a mini IBM that also had PySat ion velocity meter processing as well. So the developers were using PySat for our everyday science, and so far the data sets and the type of functionality that's expressed by PySat reflects our scientific needs. And we're primarily ionospheric scientists, but PySat is not really an ionospheric package, right? It's general data, and we're just using it right now as we can. And to just cover some examples from the manuscript, here we have instrument independent bin, instrument independent bin averaging. So I'm sure everybody has seen some kind of plot like this in space science before, right? Where we break up a 2D thing and it's a little bit divided into a bunch of bins, dump the data into a bin, and then perform some kind of statistical average on there. So PySat allows you to do that for any data set or any instrument product that's supported by PySat. So it's very easy now to do these type of statistical things in a very rigorous and robust and validated way, very generally. So this is just a simple example as I'm looking at the ion density from the ion velocity meter instrument from the ICON spacecraft. So ICON is in got an inclination of about 26 degrees and an altitude of around 500 kilometers or so. So it's kind of an equatorial-ish ionospheric mission. So it's going around, it's got the ion velocity meter on the front, and it's running in the plasma, making measurements of plasma density, temperature, composition, and velocity and things like that. So this is just a reporting of the density, looking at the average density over 31 days in early January of 2021. And what we can see here that there's increases in the density. It looks like there's a wave structure. And this is a known signature for equatorial-ish physics. It's called the wave 4 signature. And most of the time when it's present, you'll see 4 bumps. And the source of this is thought to be the fact of the distribution of land and water across the globe, that the land and the water, right, heat differently. That heating ends up impacting the ionosphere. So most of the time it's 4, but during the winter months, sometimes it's 3. So here we can see 3. So this is a demonstration kind of not only of some functionality, but it provides in and of itself like a physical validation of the data set. So one of the things that sits here. Another common thing to do for equatorial physics is investigate how often plasma bubbles occur. So there's also generalized support for determining the occurrence fraction, how often something occurs in the data set. In this case, it's plasma bubbles, and we can see here in the 300 degree longitude sector near local midnight, There's plasma bubbles about 25% of the time, but not very many other places. So this is just for a few months here in 2020 from ICON. So again, but this occurrence fraction thing will work for any data set or any instrument supported in PySat, whether it's an instrument or a constellation. It also supports model data comparisons. So here we've got JRO, which is a Hickamarco radar observatory, and a model. So we've got a model distribution of points here, which is all these black points here. So right, this model's got a range of altitudes that it support, and because it's a model, right, it's got data at all the different times throughout the model. Hickamark is the ground station observatory. It's only on at nighttime, basically. And when, you know, it takes a lot of power from local generators, so it's not on all the time. But when it turns on, it takes altitude profiles. So if you want to do a comparison between, right, the model and Hickamarka, then you need to know, hey, what are the locations where both Hickamarka had data and the model had data? And those are the red ones. So this is just a plot coming from the paper, just showing how PySat models provides functionality for doing this comparison in a very general way, so make it easier for users. Can also be a common thing if you have a model and then a data set you want to compare against the model, is that the data set locations and the model locations are, you know, generally they're not going to be the same. So we've got some interpolation support in there as well. So this interpolating MLT example is just showing some interpolations of a regularly gridded model. Either it's a nearest neighbor or a linear interpolation. So you can see, right, the linear, you know, does a smooth linear interpolation between, whereas the nearest one just grabs the nearest one. So that's why as the nearest one changes, you get a stair step pattern. But commonly, you know, for the model, it may not be regular. It may have an irregular grid, or it may be regular in one parameter, but not in the but irregular in the parameters that the data set's over. So this lower right example here, this is interpolating like a PyGCM model. So PyGCM is regular in pressure, but the altitude of a given pressure level is going to vary based on atmospheric conditions, you know, and just most generally, you can have the local time variation, right? So it can be difficult to interpolate PyGCM onto a satellite data set, which is going to report things via altitude. But I found a way to get a regular like interpolation out of an irregular model, particularly for PyGCM, and that's what this example is showing here. So if you try to do irregular interpolation, I mean, the computational cost is just crazy high. So it just becomes overwhelming super quickly. This backwards method that I got is accurate and is so much faster. So it's actually practical to use. Right now, it only works for 1D PyGCM type stuff, but with funding, I believe this could be generalized. And finally, a mission like for an example for mission planning. So this is, I just want to demonstrate here, if you want to have like some simulated data sets or other type functionality, it can be expressed via PySat in the same way as any other data set. So if you compare this against a canonical example, right, it's the same. We import some stuff, we register a model here. In this case, I want to go through the data set by orbit. So we want to use the orbit iterator within PySat. So this is just telling PySat what to do. The equals PySat.instrument. Right now it's selecting missions. That says it's telling it, hey, go to the PySat missions package. And it's going to pull out a particular propagator, the SGP4 propagator. We give it some information about that orbit, a 10-degree inclination, 500 kilometer constant altitude there. And the next line, we've got in stock custom attached. In this case, we're going to add some custom information to it. So we're invoking a function that's already been developed within PySat, which is generally, you know, what's the solar local time. More than one person would need that, so we went ahead and added that in there. Inst.load is going to load a particular day using the orbits that are generated from SGP4. Right, and now it's here plotted out. The last bit, I'm just showing how you can iterate over orbits. And in this case, the orbits, right, they don't respect file boundaries or day or file breaks. So I was just demonstrating here, the first time is at around 2300, the day before January, you know, so it's January 1st. The last sample's around, 30 minutes after the beginning of the day on January 2nd. So because of the way PySat works and the whole data flow and process that it's got, it abstracts away a lot of the challenges of, hey, on these different days, we've had to do 2 different simulations or multiple file loads or whatever it is. That all happens in the background but it all works out across a wide variety of data sets.
Just
So
telling
it's
you
not
that you're
just
almost out of time, Russell.
okay. I'm almost done. PySat also has support for research operations. We've been using it like that. So because of all the different data model support, and we've also made sure with a lot of testing and other types of documentation and stuff like that, it works well for operations. We support a lot of data sets, and we've got a ton of online documentation, and in addition to our manuscripts. We've got an upcoming release. A lot of stuff has happened, but I just wanted for the community to point out, we ran into an operational user that was using an older version of Python. And because of the NEP 29, right, we weren't normally testing that version anymore. So the kind of Python, num-focus, NumPy, that kind of release cycle of a couple of years or whatever, and it keeps going. It seems a bit aggressive compared to science users. So satellite missions aren't going to be, progressing that fast. Operational users aren't going to be progressing that fast. So within PyHC, we might want to designate some long-term releases so that across the community, we can try to maintain support for that. So for users, satellite or other operational users, we can help them. And if we're helping them, then they, might be more inclined to be using our stuff. Thank you, since I'm out of time.
Thanks, Russell. Do we have a quick question or two? Yeah, you do in the room.
Hi, Komodo can do a lot of that in your interpolation you were doing for TIEGCM and handling that the variableness of the grid and whatnot. Komodo can already handle that, and then can handle it for all other models that we've ingested. So if you want to do it for GITM or CTIP, whatever, it's already there. And so it could be something that you might want to then make a call to the Komodo tools to do that rather than having to invent something new.
Oh, well, thank you, for the comment. Technically, the functionality in PySat models is not new. We also do have coupling with Komodo. And there's right now there's a PySat Komodo package, which I believe is just on coupling via data frames. We could also, with funding and all that, we could improve that coupling and extend it to X-array. And then, Komodo functionality may be available, vice versa.
So this is John Niehoff. Russell, with respect to the support in NEP 29, which I had to look up to make sure I got the number right. I think there's some misunderstanding about that because I think some people interpret it as a mandatory cut that you're not compliant unless you chop off at 3 minor versions or whatever. I've always interpreted it as a support at least that far and do what you can to support further. On the SpacePy side, what we kind of settled on was, well, let's try to support the last 2 long-term support releases of Ubuntu as just a thing. But I like the idea if there's things that we want to specifically target as, hey, that this is something across the community we want to support, that would be great.
Yeah, thanks for the comment. Apologies if I made it sound like that was NEP 29 was saying you couldn't support. But as far as I know, we don't have any other documentation within our community saying, hey, NEP 29 exists, but we think, plus statements A, B, and C or whatever.
Yeah, and I wasn't pointing the finger at you on that. I've heard that from a number of corners.
Yeah.
Awesome. Thanks again, Russell.
Thank you.
All right, next up we have Darren, presenting on Komodo.
Okay, I'm going to give a brief overview of Komodo. I think a lot of people understand what it is. I'm going to have to go into quite as much detail, partly just to save some time here. and then go over a lot of the significant updates that we've done recently. As far as what is Komodo, it is an official open source package supported by NASA. It's been developed and maintained by the CCMC, and as a tool for both all of access, interpolation, visualization, kind of a complete analysis package. And it allows model developers to represent their simulation data as a function, which then we can and because we've done it that way, we can apply a consistent tool to it and apply it to a wide variety of models with a consistent interface to working with it. It handles, unit conversions transparently and supports a lot of things. It's all available through PyCon and through Python, and the source code is available there. One note, little caveat there is, again, we're providing an access to model outputs. You have to have access to your model outputs somehow. And again, that whole discussion about where do you store data is certainly an ongoing discussion that will be continuing. So what can Komodo do? Komodo again supports a function composition, so a way of representing your data set with those functions, and then you can apply a lot of things to it. It handles automatic unit conversions, and so you can work with whatever data set the output is stored in, but yet do head-to-head comparisons with things in different unit conversions. This is really handy to have that kind of built in and behind the scenes. Coordinate transformations, again, it came up. We depend on SpacePy for some of the coordinate conversions, AstroPy, other places, and again, that's included in Komodo behind the scenes. Interpolation is really a core feature of what we have in Komodo. If you're bringing in a data set, in order to functionalize it, it has to have an interpolation scheme so that we can interpolate in all of its dimensions accurately and be able to handle that. And so that's a core functionality there. The output, again, we have nice interactive plotting that we can do with this. And then we use APIs. And so again, we talked about, Happy is a part of a lot of these packages. We depend a lot on Happy to pull in a lot of information as well. And so Happy is just one example of an API that we interact with a lot. When we have these features available in Komodo, then what can we do? Okay, so how do you apply these things? And so satellite fly through is a huge thing that we can do, because again, like we talked about with coordinate systems or data structures, a grid might be in pressure levels rather than altitude. To fly a satellite through that, you've got to convert all that stuff into a like system to be able to do that. And so the satellite fly through system handles those conversions, those transformations automatically behind the scenes, and we can do that. That satellite fly through is really powerful. And then because we can do that, then constellation mission planning tools then are also available for us. And so you can start to fly a constellation through it and see, okay, here's this data set. What would this see? And a mission planning to be able to do that is really invaluable, and was really important for the GDC mission that they use Komodo to help analyze their system before they got to the final stages. Data model comparison analysis. So again, this because you can pull in lots of things, you can pull in 3 models that all model the same region and pull in whatever data sets cover that region and do those comparisons and do that all on the fly. And then model driver swapping, I'll mention that in a little bit. That's another new application using Komodo to use it for doing science. So just a couple of quick snapshots of what Komodo can do. Again, this is taking GITM model output and extracting at a given surface. Now, so 500 kilometers. That's not exactly a grid point in the system. So again, it's doing interpolation on that position. It's doing coordinate transformations to display this in different ways. And this plot, again, we're adding some value-added things. We're putting the continent outlines in here. And so you can plot the data in 2D, but you can also show it in 3D. And what I've shown here is that the one on the plot on the left is in geographic coordinates. The plot on the right here is in GSE coordinates. And you can see that the 2 little black lines up top, one is the geographic pole and one is the pole in GSE coordinate system. And you can see all those transformations could all happen and you can display in whichever way you find best fit to do your science analysis. Again, our satellite fly through, we can fly through multiple satellites and start to lay over a bunch of satellites in a position and see how they compare with those satellite extractions. This is extractions from a global magnetosphere run and seeing what it can do. But then especially when we're getting to data model comparisons, and so you can actually fly. So we're fly the Cindy instrument. We fly that. We actually use Happy to go to SSC Web to grab the positions in its coordinate system, get the data in its coordinate systems, transform them, fly the satellite through it. Then we can also then jump back and use Happy to go to CDOT and pull in the actual observed data. And then we can make these plots and look at the data versus the model and look at the difference plots. And so the analysis you can do with this, with all these, by pulling in other tools as we go forward, is really useful. Up on top here, this is the global magnetosphere simulation. Again, it's flying a GOES 12 through a simulation and looking at what the BZ values are compared with the simulation versus the data that, again, we pull in from CDOT through Happy. So what's new in Komodo, especially in the last 6 months? A huge part of what's new is massively upgraded documentation. Really proud of that. Rebecca and I put a lot of work into this documentation, and we're really, it covers a lot of things, right? It's a thorough description of what it can do and how to use it and apply it to things, but it also has quick starts. You can drill down to what you need. We've got a quick start thing. If you want to just jump in and go, you can jump in and get that short recipe to get you going. But if you want to dive in and say, well, what do I really need to do to, playing with satellite trajectories, it'll dive into that and show a lot more detail. And so all of these break out into a huge outline. And so there's a lot of new documentation available that we can jump into a look at. We've also added a lot of new testing notebooks. They're not automated through GitHub yet, but that is a plan going forward. But it allows you to not only to verify that a change to the code didn't break something in the past, it's also then a little recipe sheet for somebody new coming in saying, I brought in my data set. Let's run this little 5-cell notebook and see if it works on my data set. Well, then I know I've gotten at least that part of it right. It's not my data's problem. That little recipe works. And so it works as a really small sample set for allowing you to testing things. We've added a lot of tutorial notebooks, which go into more detail. So these are Jupyter notebooks with a huge amount of documentation embedded in them. And it's really describing how each step goes through and working through how to do things. And so again, documentation has been a big push recently and have that big upgrade. Adding more model readers. So currently we have this long list of models available. There's a number of new models we're working with. We started a lot of ITM models were what we started with going in. We're adding some more global magnetosphere models, but filling in some cracks with some other models as well. And so that's a big push, because at the CCMC, we have, a lot of models, nearly 100 models that are available on run a request. And our goal is to eventually accommodate all of those models, right? So that's a big push, is to add in these model readers as we develop things. And especially I want to call out the SWMF, the global magnetosphere, as the first model that's got custom C code as their interpolator. So again, the data structure for that model is complicated, right? And we know, SpacePy, we're using SpacePy to ingest it because it's a binary format, right? So we're using that to ingest it, but SpacePy didn't have 3D interpolation built into it or using the tree. And so we're actually using C code that rebuilds the tree and can very, very quickly, and again, performance is important at this point, to do the interpolation at these various points. So we can extract slices, surfaces, wherever we need to be through the simulation output very, very quickly. And so this has been a big new advance. So again, adding C was important, but adding other languages to Python complicates things greatly. So we've added C and we got that to work. Fortran, unfortunately, is harder. And so there's still issues with that. And so there's the whole issue of, other codes, C and Fortran calling Python and Python calling other languages. And so that whole ecosystem is still not Doesn't function as well as it should yet, unfortunately, but we have implemented calling the C libraries. That's worked quite well. Python version support, we're upgrading right now from 3.7 to 3.10. Again, Komodo being a Python package is dependent on a lot of different things. And so we're trying to figure out that interdependency, does everything else that we're dependent on work well in 3.10? And working through that, we had some issues with Plotly and a couple little things and figured that glitch out. And so we're working through that process right now to make our package officially a 3.10 package rather than the 3.7 package. We have a PyPy pip install that has been created. I describe it as not fully functional in that it doesn't yet have, I don't have a way to build the C reader for the SWMF reader. And so setting up Python packages, that's been a complication, and setting up how to set that up. Doing it for the first time has been rather challenging. And so we're still working through that. We'll be upgrading what we have on PyPy when we have 3.10 fully ready. We'll upgrade our pip install there, but we also need to do some upgrades to get the C code in there. And then once we have that one kind of figured out with the C code, then we'll also add the Conda install as well. But rather than having two partial installs, we're trying to get all the bugs out of one, and then we'll expand it out to the other. Komodo is being used for model driving. And so if a model needs a certain parameter on a specific grid to drive the model as a boundary condition, for example, and quite often it'll use an empirical model to drive that thing. Well, we can use Komodo to read a different model that can output values that can be converted into the right kind of driver. And so it'll read in a different model, do whatever interpolation, unit conversion, coordinate transformation is needed all behind the scenes, and create that driver that the other model needs. And so then we can have a more interchangeable model driver chain for what we're doing at the CCMC. And that's a new exciting thing that we're doing. And then finally, the cloud support. Again, it's already come up that cloud support has some complications. S3 data buckets. We had problems with our readers with reading some of the data sets that were there, and so we switched to some different packages to read the data sets. And we're working through testing and debugging making sure that they work in both environments has been complicated. And so working with that, and Rebecca will bring up the new executable paper coming up soon, but a lot of this is working on improvements to Komodo in the cloud so that these things can happen seamlessly when we get to those needs. Quickly, future plans, kind of where we're going with Komodo. Again, we're trying to enhance our open science support for what we're working with, like these papers, like other things. More cloud presence and tools. So we're trying to figure out, even at the CCMC in general, how to push more of our data into the cloud and then have the tools in the cloud to be able to access and read and analyze and visualize as well. And so that's certainly an ongoing thing that we're working on. Performance enhancements, there's always room for improvement to parallelize the intensive functions of what we're doing. We'd like to develop some line of sight integration tools in Komodo and what we're doing. Vector field visualization and vector field tracing is something we need in Komodo right now that we're working toward trying to better be able to trace through. Again, because we've got a generalized package, we want to do a generalized vector tracing algorithm in that to be able to extract things that the scientists want to look at. And then also looking at potentially what we can do with images and model data comparisons for images. How can we handle that? Whether it's laying images with data or actually doing synthetic images and data and looking at that. And so that's something else that we're looking forward to working on. So try to keep this quick. I know things are going long, so I kind of kept it short. And so I'll leave it there and ask questions.
Here it's on. Hi, Darren. This is Rebecca. Could you elaborate more on what you mean by more open science support, please?
So there's a couple of things here. So one is kind of the broader thing is how CCMC at NASA can better support open science, right? How can we make things more accessible? whether it's data sets, whether it's things like that. And then specifically with Komodo is how do we make these tools more open and reproducible, like a cloud service where you could actually go back and reanalyze things in the future, right? And so, and to be honest, looking forward, because this is still an evolving thing, where this goes is somewhat unknown. We might find that 3 months from now, there's kind of a community push to do this with data access or do this. And so we want to be able to respond to that and be ready and be open as possible. NASA has momentum to it that's hard to sometimes change direction, and open science is a hard shift sometimes for where we're going. And we're trying to be as open and flexible to those changes that are coming as we can.
I have a question. At one time, I heard you were adding support for LFM, but I think I didn't see that on the list, and I didn't see it on the list of upcoming models. Is that still in the plan?
So LFM, it was originally on a list. It's kind of switched over to being the Gamera, the new version of LFM, is really what's on our list of being. We're working right now with them to bring Gamera in, which is the next generation LFM. With LFM, with the original version of LFM being kind of a legacy code at this point, it's slightly lower priority. We do want to get to it eventually, and if we get the Gamera, and if there are enough similarities with that, we can then roll in LFM later. But right now, we're focusing on Gamera at the moment.
Thank you. Yeah, it's still good, even though Gamera is the new version. The reality is that not everyone has access to the Gamera code, and APL kind of, keeps it close to heart. So until it's made available to the public, a lot of people are still working with LFM.
Yeah, and CCMC is onboarding Gamera to start, doing runs on request with that also sometime soon. And so, but that we focused on that at the moment. But yeah, LFM is not falling off the list. It's just not imminently next on our list. It is something we definitely want to include.
Thank you.
Yeah, this is Lutz Wasseter. Yes, I think when Gamera is supported, then LFM will come as well, because the grids are very similar. So I'll be working on a common grid interpolator for both models.
Thank you very much.
Yeah, so LFM will come along, and we have a lot of LFM runs in our database, and so that support is very important as well.
Thanks again, Darren. All right, last talk before the lunch break. We have Jim Lewis with PySpeed S. All right. Can you all shared for you? Boom.
Okay, thanks. Good to be here. See everybody in person finally. So I'm going to talk a bit about PySpeed S and where we are and where we're heading with our development in the near future. So I want to call out some of our key contributors besides me, Nick Hatzigeorgiou at Berkeley Space Sciences. Eric Grimes has done a ton of work on the MMS tools. Sasha Drozdov, our PI, Vasilis Angelopoulos. And also I want to call out Brian Harder, who developed the PyTplot package, which is used very heavily. Last week at ISTP, we saw this slide so many times, the Heliophysics System Observatory, and this is sort of setting the context. We have all these different missions, and it's what we all want is to be able to bring them all into a common environment and use similar tools on all of them and not have to worry too much about the implementation details of each one. For a long time, we've maintained SpeedAS, the IDL version of SpeedAS, to do this. And now, for various reasons. We would like to move to Python and implement as many of those tools as possible, get those ported over to Python. And so we want to provide a uniform interface to all these different data sets that are out there. We need to give people a rich set of analysis and modeling tools to work with that data. And we want them to be able to generate publication quality plots and other visualizations. And in particular, we want this easy to pick up for students and researchers and citizen scientists. For many of these people, having to buy an IDL license to run the full version of SpeedAS is really prohibitive. So yay, open source. Just call out a few of the types of missions we support. Of course, there are a bunch of satellites in Earth, Moon orbit. So Themis, MMS, RASE, Van Allen probes, Discover, GOES, POSE, Cluster. They're all available in PySpeedAS. For solar missions, we have the Parker Solar Probe, Solar Orbiter, and Stereo, which can be used with PySpeedAS. We have a lot of ground-based data sources we also support. So via the Themis module, we support quite a few different ground magnetometer networks. And there's the MIC induction array, and some geomagnetic indices like the Kyoto DST index. And we have tools for working with SEX EICS data. In terms of analysis tools that are currently supported, we have an interface to the GeoPack field modeling library. And not all the libraries are supported yet, but that's something we're going to be working on. We have particle tools now for 3D particle distributions. So if you have a source of calibrated 3D particle data, we have sort of generic tools that can generate moments or energy, phi, theta spectrograms, or take 2D slices. So right now, MMS is sort of the most complete implementation for these tools. For Themis, we don't have our calibration tools ported to Python yet, but it's coming soon. And we are putting together new data products. You could have, so you could take calibrated 3D particle data and pull it, have that directly in CDFs. And so when that is available, we'll, in very short order, we hope to have a port of these tools for Themis data. We have a number of coordinate transforms available, most of the standard geophysics ones. We've also recently added the capability for field-aligned coordinates and minimum variance analysis. We also recently implemented some lunar coordinate transforms, SSE, lunar ecliptic, forget what the other S is for. And then SEL is the rotating version of that. So those, that was by request for some people who wanted to use PySpeedAS to work with Artemis data, which is our moon-based component of the constellation. And then we also have support now for Themis spinning and despun coordinates. And those are going to be very important for implementing the Themis calibration tools, which are currently in progress. And then we also have some tools for doing wave polarization analysis and dynamic power spectra. So just calling out a few of the more recent developments. So we've done a lot more cross-validation testing to compare our PySpeedAS results with IDL SpeedAS, and that's really an eye opener sometimes. You think things are working because you get output variables out, and then you find out that they don't quite match up what we're getting in IDL, and then it can be a bit of a puzzle to figure out why. IDL has its own library of analysis tools, And sometimes when you convert that over to NumPy, sometimes different assumptions are made, different algorithms. And so it's a bit of a challenge sometimes to figure out, like, is this little difference we're seeing, is that really, are we doing something wrong? Or is that just because of choosing one algorithm versus another? But yeah, we're hoping to increase our coverage of those sorts of tests so we can be a lot more confident that that PySpeed-S is giving useful results compared to IDL. We've cleaned up the code a little bit. As we were developing, we had all kinds of progress, print statements in there, and it was if you did anything substantial, you just got miles of console output. So we've cleaned that up quite a bit, and we're actually using logging calls for most of that now, so the users can have some control of their environment and what detailed logging they want to see. Another big one we've added is support for master CDFs. So this is actually in PyTplot in the CDF to tplot routine. So what's driving this? I think somebody requested that we add the capability work with wind 3DP data, and so that data is available through CEDAWeb, but they have almost no metadata. So so you can't get what you need just from the data files themselves, but CEDAWeb also maintains master CDFs for most of these missions, and that's what allows them to do their plotting tools and other utilities. So yeah, we have code now in CDF to tplot that there's an option now to supply a master CDF. And I imagine that's probably going to take a little more work to get properly sorted out, because it's only been tested on really on wind so far. And, every mission does things a little different. This is sort of a re-implementation from scratch rather than copying, like porting the IDL version of this. So I'm sure there are places here and there where we're going to find little differences in like how this mission, interprets the metadata requirements. And but anyway, the framework is there, so that's available, and that gives us access to the Wind 3DP data set and many others. We're also trying to clean up some of the duplication between PyTplot and PySpeed-S, and just having tools split into the two different places. So for most of the like low-level tools, like if you just want to do math operations on tplot variables, we decided most of that stuff should probably live in the PyTplot package, and then some of them got implemented, like Brian did some routines, and we went ahead and without knowing that they existed, we re-implemented them in PySpeed-S. And so there's some things that supposedly do the same thing, but different implementations. So we have to do a little bit of work to either merge the two versions in one tool, or either pick one or the other to be the standard version, and have that be the PyTplot version of it. So we're going to continue one by one, porting the IDL Speed-S tools and features to PySpeed-S. As I mentioned, there's still some work to be done implementing some more magnetic field modeling tools from GeoPack. The whole library, I think, is not available yet. In particular, we're very interested in the TA15, TA16 models. And we don't have field line tracing yet. So I know there's some other tools out there for doing just general field line tracing for vector fields, and so we're sort of interested in taking a look at maybe leveraging some of that rather than rolling our own. But some people may be attached to the GeoPack implementation of those tools, so we're going to try to make that available as well. Then, as I alluded to, we would like to have some mission-specific calibration tools included in PySpeed-S, and especially for Themis, because we have level 2 data products that have been calibrated and put into good, usable coordinate systems. But there are a lot of assumptions that go into it, like how you do your background subtraction, or which sets of calibration data you use, or which corrections you turn on or off. And so people would like to have access to explore the calibration space a little bit on their own. So we're going to try to provide full set of calibration tools for FEMIS and perhaps MMS. And then for future development, as I mentioned, we want to have some wrappers for more emissions particle data. So we have the generic version already, but each mission does things a little differently. So once the data becomes available, we have to massage it a little bit into the format that the generic tools take. Of course, we're going to do, we do pretty frequent webinars. Sometimes now and then, just sort of general high-level view what tools are available, and then sometimes we take some deep dive webinars. Like Eric Grimes has done a number of them for MMS tools, and focusing on even just MMS particles and how you work with them in SpeedAS or PySpeedAS. We're going to have a couple of tutorials at the upcoming GEM meeting in June. And we're really working on expanding our online documentation and writing a lot more example notebooks, giving people some pointers on how to use all these tools. We have a few people who are working with us to translate and caption the existing documentation, make them available in other languages for non-English speakers. We're interested in developing more GUI capabilities, probably not in the core PySpeedAS package, because we don't want to have like the GUI frameworks tend to be pretty heavy dependencies, and they cause problems with dependency conflicts and so forth. So we would probably at some point have like a SpeedAS or PySpeedAS GUI package to host a lot of these more graphically oriented tools. Oh, it looks like I didn't finish that slide, we've had a lot of requests for more interactive plotting tools. Like once you plot something with PyTplot, you can't really like mouse around it and click on things and see what the data values are at that point. And so that's something we want to add in the near future. So I'm going to, next couple of slides, Sasha is going to explain a plugin he's working on for some the MTH5 data sets.
All right, thank you. Yes, as Jim mentioned, we're working on the new plugin, and the idea here is to add more ground-based magnetometers access to via PySpeedAS environment. And like I have this, I don't know if you can see my, I have this motivation here from the Engelbretson a paper that's there are a lot of basically ground-based magnetometers, and in comparison to space, the data is just a vastly covered and continuous. And the problem is that to access to this data, you have to go through the complicated process that people who are working in the global scale of magnetic fields, they don't really need that. So we need to some sort of way to simplify this access. And here in a nutshell, what we do, we pull up the data from FDSN, which is a standard for seismographic networks, because all of this data is pretty much comes from the studies of earthquakes, but it do have meteorologics data and magnetometers in them, some of them that we can use, and they already been used and proved to be useful. And this data is packed into a format that is MTH5 format developed by USGS. And on the next slide, I'll show you that's, I don't know if you can see it, but the structure of this MTH5 is quite complicated. So basically, for each measurements, it's built into the surveys, and each survey is built into the stations, and the stations have different runs. And for this seismological community, it's very important because the work with the particular setup of the instrument, but for us is less important. And what we need as a time series of data, just continuous data from this particular station without like worrying too much about surveys unless they change drastically. And typical boilerplate for MTH5 access is basically this code. And what we want to convert it into just basically call a few lines, get the data, and they visualize it for me. And this is similar to what other instruments in PySpeed does right now have. So in a nutshell, we want to have easy access to the large data set via PySpeed, and a lot of people in space community, space physics community are already familiar with this interface. And that's it. Our lunchtime is soon. Like, get back to you.
Thanks, Sasha. So I have one more slide here. I want to show something that is coming up in the future. This is from Tomo Hori from the ERG Science Center. And this is a tool that exists already in IDL SpeedS. It's a 3D visualization tool for particle distributions. And they are producing a Python implementation of this. And this is a really great tool. As you can see, you take a 3D distribution, you have your look angles, and then your energies coming out from the center. And they have several different visualizations. And you can also, as you can see, you can have different cuts through the data, different planes, and then you can move them around. And then on those cuts, you could project contour maps or 2D slices onto them. And so they're working on this. I would expect in the next few months, we'll have that available either. This is probably one of those things that would fit into a PySpeed-esque GUI package, because I know they've done this in PySide 6, and I know that's a heavy dependency. So, so that's something that's coming. And that's all I have. So maybe we can open it up for questions. And I know Eric Grimes, I see you're online. If you want to expand on anything you want to mention on what's been done for MMS recently, feel free to chime in. John?
First, a quick comment. The tutorials and everything that your team gives are great. I think other projects should emulate that. Like you're at the GEM meeting, you're at the AGU, the mini GEM. Yeah, so I think we should all try to learn from that. The other comment is similar to what I was asking about from SunPy. Are you expecting a full conversion over from SpeedOS to PySpeedOS? And what is it that the community here could do to help facilitate that? Or what kinds of things? Like you mentioned the particle data, it's all a little different from every mission. There's something that I think we could band together and try to come up with a standard way of representing that, or an API that we could always get out the same thing, or something that would make SpeedOS job easier.
Yeah, and I think that would be a great opportunity for some of the people that work with these different data sets, or people who are maybe, in the proposal process or developing new instruments, get together and discuss our experiences. Like, well, how did you shoehorn your data into the CDF and ISTP metadata? And what do you wish you had that would have made it easier to design those data sets? And to your comment on the tutorials, that's been super helpful for us as well, because every time we do these, we get great comments from the audience, and they come up with some great enhancement ideas, and but we get bug reports right there at the sessions, and it's so it's really helpful for us to have an idea. Like, we know where we want to take a development, but what does the community want? And this is a great way for us to get feedback. So yeah, I would highly encourage other developers, put themselves out there, do webinars, go to the meetings, and give tutorials. Yes.
Okay. So kind of a big picture comment question thing. I I've noticed that like SunPy has had a trend of not supporting specific missions, but making it more generic and having it go to like mission teams to focus on developing functionality. And it seems like PySpeedOS has the practice of supporting lots and lots of missions. So I'm wondering what the trade-offs are that you've experienced with that.
I guess the trade-off is, I mean, for a lot of these missions, you could go directly to C2Web, and the data is archived there. So in theory, that endpoint would cover a lot of different missions, but a lot of times, there are mission specific analysis tools that sort of come along with that. And so when that's some like, more options with the load routines or different ways to specify what exactly you want to get back. And so those things that are not directly supported by C2Web, that's why we have a lot of mission specific load routines and so forth. And then, any mission specific analysis tools or coordinate systems, those really belong in mission specific plugins. But yeah, we would love, we do support Happy. We do have a Happy interface, so that's something we're working on. And that's another route that's available for more generic data access. But sometimes for if a mission wants their data to be used in PySpeedS, sometimes the easiest thing for them to do is just give us a load routine for us and let us put it in. Yes, Sasha?
Yeah, I have a comment about this discussion. So the benefit of having all the missions in one place is basically coming from the first principle: why do we need PySpeedS at all? So people can download data and use it. But for the most of the researchers who are not very familiar with Python, but can use it on the sum analysis, they just need some easy way to get the access of the data and then work with them, like interpolate or plot and analyze. And if you have to figure out like how to access data through some other plugins, and maybe it's not available and it's not universal, that imposes difficulties. And that breaks the whole idea of why SpeedS exists in the first place. Because again, the putting efforts and creating this kind of like a bridge between like the figure that you actually see and the data itself through like developers who like use just one single line to get the data. That's what makes it important.
Thanks.
So I'm going to pick up on Jack Ireland's comment. This is Rebecca Ringett speaking about trying to abstract away the language that we're using. So I think the GUI implementation that I'm seeing here is a really great way to pull in the community that doesn't really want to switch to Python, but they're familiar with pushing buttons on the web interface. And that definitely fits in with the next generation infrastructure for PyHC packages. So definitely just wanted to encourage that push.
Yeah, and we're very keen to get that GUI implemented, because that's been the entry point for a lot of people into SpeedS. For the people that don't have ideal licenses, we have a distribution license to pre-compile SpeedS and then just release it as a virtual machine executable. But since you don't get access to the ideal compiler in that tool, it means they only get access to things that are exposed through the GUI. And that's enough to give people a taste of what's out there. And also, I think it makes things really more discoverable. Like, if you bring up the IDL GUI, you bring up the load panel, and you could see you have a bunch of different tabs for all the missions that are available at a glance. You don't have to go diving into the code to see what load routines are there. And then the same thing, if you bring up the analysis panel, you can see, there's buttons for wavelet analysis or coordinate transforms and so forth. And so it's so much easier for you to see like what options are available to you and make them discoverable and sort of ease people into using the tool.
One more quick question. What does PySpeedS use under the hood for coordinate transformations?
We've ported our own routines that were in IDL SpeedS, and I know we would like to leverage some of these other projects. I think SpacePy and AstroPy both have coordinate transforms in them, and we might be better served just making calls out to those packages rather than our own. But just just for the sake of getting things up and running quickly, we just ported what we already had from IDL. And I know we also have a request open to incorporate AstroPy units into, I think that would come in at the PyTplot library level. So give an option that to have the metadata that comes out in AstroPy units, and then be able to work with them elsewhere in PySpeedS.
Online ones too, people can just jump in. Steve, Will?
I have a question about this IC3D for velocity distributions. Is this available on the web right now, or is this like an internal demo?
It's under development right now. I don't think they've released it. I think it's ERG-SC. They're on GitHub, so this might be already available on their GitHub, but they haven't released it yet formally. This is just a preview from a different presentation meeting I had with those developers.
Thank you.
Will, your hand was also up.
Yeah, I guess I kind of had a larger question about the sort of the philosophy of developing tools that are targeted towards the user who doesn't want to learn like Python, or who just wants the quick look plot. Like I guess I can see, and I'm not coming from a community where like SpeedS has been a thing. I can recognize that it has like a lot of heritage. People are used to that sort of interface. But and I see the value in replicating that in Python. But I guess by doing that, I guess my sort of question is, to what extent are we like putting up a barrier between like those kinds of tools which do a really targeted thing really well and offer a kind of a specific interface to that? To what extent are we like building a wall between that type of analysis and like the rest of the scientific Python ecosystem? So things like, visualization with Matplotlib, or, like parallelization with something like Dask, or like how, to what extent are we locking ourselves out of the larger scientific Python ecosystem by building tools like this? That's kind of my question.
Okay, Rebecca.
Hi, this is Rebecca again. I have thought a lot about that problem, particularly like having these individual tools as GUIs, which I think is what was being talked about, right? Okay, on the right track. Having these individual tools don't lock us in. It gives us pieces to put into a bigger analysis environment. And the user is going to need these specific tools to do what they already do, but have it alongside, say, 5 other different tools that they want to plug in, maybe from different packages, without having to actually install all of this junk like I had to do.
Yeah, and I would hope we're building a bridge, not a wall.
Yeah, I'm just going to jump in on that too, because there was comments about, reducing the amount of code between the data and the tools. And because I developed particle analysis tools back in the day, and they don't age well. That code, if the more you have to do to the data to get it into your tool, you have to calibrate it. You have to run it through this. You have to rearrange it. The less we have to do that, the more durable the data is, the more durable the tools are. So we're trying to, reduce how much we have to do between there. And so that's where standards come in, getting the right metadata in there so that it's interpretable, getting the right APIs on it so that lots of things can read from it. So a lot of the pieces that we have here are contributing to this. And what we're trying to minimize is our jobs, right? Less software is easier to maintain. So pushing it into things that are longer lasting.
So I'm just going to jump in because it seems like a good time. One thing that I did want to add to the discussion about the link between, say, GUI-based work and kind of working more directly with code is that there is a hurdle in essentially reproducibility of GUI-based work. And so, for example, this ties into the question I was actually going to ask, which was about visualization and export to VTK. But if you look at some of the leading VTK GUIs, they let you essentially export your visualization as a script. And so, you know, if you have a GUI that is under the hood, every time you click a button, it runs some command in the underlying Python library, you can capture that and export it. And that might actually be a really nice thing to do and to encourage for open science so that you can actually have reproducible workflows. It makes loading somebody's, you know, the person using it never has to look at it. They can just, you know, save a file, pass it to somebody else, and that person can then reproduce that analysis. I'm going to leave my question about visualization. I'm just going to keep on topic.
Okay. Yeah, I should mention that in IDL Speed-S, we actually did have that feature. So you can, like if you go to the load panel and do some load operations and then go to the analysis panel and run some operations on it and then plot it, all the steps are saved. You could save that. And I forget what we called it, a Themis GUI document, something like that. And then you could send that to another researcher. They could load it into their Speed-S so that it has all the steps, but not any of the data in it. And then they would follow, by loading that document, they would follow the same set of steps and get the same, hopefully the same results. So so I take your point, and that's something that maybe we'll try to also incorporate in PySpeed-S once we get a GUI.
I have a question about the interoperability. I noticed that in the API design for PySpeed-S, it makes like a heavy use of global variables. And I know, like, my impression is you did this because Speed-S does this and it's a familiar interface. But does that limit your ability to interop with other systems? Is that going to ever be an issue?
I don't recall it ever being an issue. I guess sometimes I've wished, like, okay, so the global variables, I assume you're talking about teapot variables. They're sort of like the work. Yeah. There were times that I've wished I could just spin up like a temporary teapot environment. So I'm not, like, if I want to do something else and then come back to the first thing, I don't have to clobber all my teapot variables. So it is a bit awkward in some cases. But in terms of interoperability per se, I don't think that's really hindered us. On the IDL side of things, we could work with, say, autoplot and DOS2 clients, and it ends up being you just select whatever set of teapot variables you've been working with, and then sort of export them into the other system. But yeah, there is potential for mayhem there, and maybe we can have an option in PyTplot to maybe have different workspaces at least to prevent things from clobbering each other. Sasha?
Thank you. That would be an interesting use for a context manager in Python, like with this context and then your tplots.
Okay, this will be the last question so we can have time to still eat lunch.
Yeah, I think it's a clarification for the global variables. My understanding is it's out of the necessity that PySpeed is using these global variables because the way how the interface was constructed in SpeeDAS and the way how people get used to it. So the access to the variables via strings, right? So basically tplot variable is not a variable. It's not like a numpy array that you access directly. You access through the strings that are located in these global variables, and you can then see them everywhere. So it's just an interface out of the legacy, but PySpeed also supports the direct access as well.
Yeah, and I should say that some of this legacy goes back almost 30 years to when the first IDL, like tplot type tools were created. So a lot of the researchers are quite attached to doing things that way, and it's going to be hard to change. Okay. We done?
Well, thanks, Jim.
Okay, thank you.
All right, we're gonna go to lunch. We've talked through a bit of it. We'll be back at 1:15, so maybe we'll go grab the food and bring it here and eat together. So for online attendees, I'll put a note in the chat. Thanks. Hey, Angeline, I think you're up next.
All right. What would you like me to do?
Share your screen perhaps with your slides.
All righty, let's get that up. Okay. And you can see my screen?
Sure can.
Brilliant.
Hey, Julie, that sounds like.
Yeah, that sounds good. All right. Whenever you would like to begin, take it away, Angeline.
All right. Thanks for coming back from lunch, everyone. I'm going to be giving you a little overview of some geomagnetic and high latitude coordinate tools. There we go. I'm going to be discussing 3 different packages: Apex Pi, AACGM version 2, and OCB Pi. So for each of these, I'm going to be giving you a little overview, a little example, talk about the current development and our future plans. So all 3 of these packages give you details about where you are magnetically on the Earth. The first 2 packages are more standard magnetic coordinate packages that transform between geographic and magnetic coordinates. And then the final one, OCB Pi, presents data or puts data into adaptive high latitude coordinates.
You're doing great. मैले चाहिँ एरोनॉटिकल इन्जिनियरिङ गरेर गएको अनि लाइक यो चाहिँ हाम्रो आइआइसी क्लब हो अनि यहाँ चाहिँ हामीले कसरी प्लेनहरु उडाउँछ ड्रोनहरु उडाएको अनि यहाँ व्हाट इज
Okay. So Apex Pi is first one I'll talk about. Apex Pi provides a Python wrapper for the Apex Fortran library. It converts between geodetic and either modified apex or quasi-dipole coordinates. The geodetic system, as with this one and the other ones, is WGS 84. And this can also give you the magnetic local time, magnetic inclination, and has a few other functions that are commonly useful when you're dealing with conversions between different coordinate systems. Because the code is written in Fortran, it can be a little bit difficult to install, and you need to make sure that you already have a Fortran compiler that works and has all the permissions you need before you try and install the package. Otherwise, you need to uninstall it, do that all in the correct order, and install it again. Which is annoying, but this is the way it works. Things are a little bit smoother now because recently we took the Fortran code, which was written in Fortran 90, Fortran 77, and pre-Fortran 77, and updated the standards to all be Fortran 90. So now it's a little bit easier to work with modern compilers. So once you have Apex Pi installed, you can start playing around with it. Most of the utility is attached to the Apex class object, though there are additional useful functions in the helpers submodule. The example here shows you how to calculate the L shell of the International Space Station at a given time and geographic location. You can see that the conversion function here, the tracing function, and then other useful constants are all attached to the Apex class, which you initialize using a date and time as well as a reference height. Once you have that, you're basically good to go. You do need to have your geographic coordinates in geodetic though, and not the geocentric system. There are other packages that help you convert between geodetic and geocentric coordinates. And I believe we have an example for how to do that with existing packages in the documentation. Currently, Apex Pi is in a pretty stable state. The recent fixes to the Fortran code have improved installation issues, but there are some problems with the command line interface that we found on the continuous integration platform, but not been able to reproduce in real life, which is great when you're trying to fix things. A recent pull request has magic fixed one of these issues, so maybe it will just go away in the future. But if you would like to help us improve things, that would be a great place to start. Some future plans primarily involve improving the documentation, because most of the questions we get involve, well, which is the best magnetic coordinate system to use for our project? So we'd like to provide more of a summary that's a little bit simpler than some of the reference journal articles that have been put out to kind of step people along and choose the right system for their problem. Next, we have AACGM version 2. AACGM stands for Altitude Adjusted Corrected Geomagnetic Coordinates. And version 2 is the most up-to-date version of this magnetic coordinate system. This is the standard coordinate system used by the SuperDARN network of radars, and it is designed to be used at high latitudes because of this. As you can see in the figure, the places where you have larger errors or even undefined coordinates are all near the magnetic equator. So if you have a satellite that crosses the equator, or if you're doing equatorial studies, this is not the right coordinate system for you to use. Should probably go use Apex Pi. But if you're at the high latitudes, they're basically the same. And this program is easier to install, which is great. It also has more tracing options, which can allow you to get into the inner magnetosphere if you push the code to its absolute limits. Additionally, both AACGM and Apex Pi do tracing on top of IGRF. But AACGM version 2 has an additional database of magnetic coordinates that were reconstructed from ship's logs. So you can actually get magnetic coordinates starting in 1590 CE. Unlike Apex Pi, AACGM does most of its conversions in function space. There are 3 primary functions that you're going to interact with: convert lat long, convert MLT, and get AACGM chord. All 3 of them are shown in the example here. Convert lat long just converts latitude and longitude between either geographic, geodetic, and magnetic coordinates. And it will use tracing, a combination of tracing, lookup, or there are several other methods that are available to reach different regions of the globe, should you want to. Convert MLT converts back and forth between magnetic longitude and magnetic local time. And then get AACGM chord says, well, usually if you want a location, you want latitude, longitude, and local time. So let's just go and do that conversion. So that's just a simple way to do that. There are also array versions of convert lat long and get AACGM chord that perform the loops that you need to do within the C code instead of within Python, and speed things up considerably. Unfortunately, we can't accept time inputs as arrays because the magnetic coordinate tracing is basically a lookup table. So the C code has to reset with each new time. So it doesn't speed things up at all when we try to loop that in C. So you might as well do it in Python. There are additional functions in the utils module that might prove useful, similar to the helpers module in Apex Pi. Our current development has some small bug fixes, and then there are some deprecated functions that are going to be removed on the next release. Most of these have just been moved into more sensible places so that they're easier to find. We do have future plans to implement vector transformations to make it easier to transform vector data from geographic to magnetic coordinates. But that is going to take a bit more time, and so there's no release where that new feature is tagged to at the moment. The final package I'm going to be talking about today is OCBPy. This is a pure Python package for adaptive high latitude coordinates. And what I mean by that is that it grids data instead of relative to the magnetic field, relative to physically important boundaries at high latitudes, namely the open-closed field line boundary, or OCB, the equatorward auroral boundary, or both of them. And because these boundaries change depending on the solar wind inputs and the state of the magnetosphere, and not just the internal movement of the magnetic field, you need to know where these boundaries are, and it's a little bit harder to do. So what this package does is it provides a database of boundaries, currently from the image and Ampere data sets that tell you where the OCB is, and then also provides some equatorward boundaries as well. And in this way, you can consider your data relative to physically important boundaries and not accidentally average together data from the auroral oval and the polar cap. Now, you do this through interacting with the main classes. Once you decide which boundaries are important for your study, you choose the appropriate class, which has the boundary name in front of it. If you give it a specified time period and hemisphere, it will load up the existing data for you if it's available. You can also provide your own data, and it's able to work with generalized data sets. Once you've loaded it up, there are helper functions that can help you pair data sets, load generalized data sets to the boundaries, and then convert between either geographic, geodetic, or magnetic coordinates and the adaptive coordinates. There is also a class for doing vector transformations and for taking care of scaling for different types of electrodynamic properties. For example, it could be important to take into account the polar cap potential and make sure that as things are moving, that you maintain what the electrical properties would be for different types of data. So there are functions that also account for that. At the moment, in develop, we have an expanded set of Ampere boundaries, and we're going to deprecate the vaporware package SSJ auroral boundary in favor of using the data set for the DMSP SSJ boundaries provided by Liam Kilcommon that are available in Zenodo. That will allow us to keep this data set available in the future, even when even though Python support for this package is dropped. In the future, I hope very soon to be adding polar boundaries, and we're looking into Goovy and Suzy as well. What we'd really like to do is allow models to provide these boundaries. So if you are working with a model that provides different estimations of where the polar cap or the equatorward edge of the auroral oval is and are interested in working on this, please do contact me. So To summarize, I presented 3 packages that are useful for studying atmospheric, ionospheric, and even some ionospheric magnetospheric processes at Earth. They all have their strengths and weaknesses, and now you know a bit about what they are, so you can pick the right one. You can find them on PyPy or in their GitHub repositories. So thank you for your time. Are there any questions?
Can you hear us now?
I can hear you now.
Okay. Yeah, this is John Vandergriff. Nice presentation. Question on the Fortran code. Is there a plan or any interest, or is it possible to plan a conversion of that straight to Python? And then the meta question is like, okay, how do we create codes that can survive these language transitions over the decades?
There's currently no plans to translate it straight to Python. That would likely require a strong influx of funding. And yeah. Maintaining things over the language switches, that's just, that's an excellent question. I do appreciate, one of the reasons I really do like Python is that it does allow you to wrap these older codes and maintain their functionality without having to do all of the work of rewriting them. I do know that when we, well, for example, just updating the code to modern Fortran was a massive ordeal. And the fact that we had unit tests in place so that we could see where the code might have changed at all as we did the transformation was incredibly useful. So if we were to try and make this code pure Python in the future, we know at least that we would maintain the same functionality. And I would like to encourage everyone to do that and or continue to do that. But short, I am not sure of the best approach of modernizing all of these codes, because it is just kind of a one-off project that would ideally require someone with programming skills. So hiring someone with the right Fortran and Python knowledge to be able to do this for a very short-lived project is a little bit tricky for most institutions. So I'd love to hear more people's ideas on how to make that feasible.
Yeah, those are difficult challenges. I mean, they had an HDEE call for, hey, find old data and go rescue it. Maybe we need that for software, right? Hey, find this software thing and let's rescue it and bring it forward.
We certainly have some older IDL code for the MSP data that we would like to rescue. But again, yeah, finding the right funding call for that is difficult.
Right.
So on the software side of things, I don't want to speak for CCMC because of course I'm not part of them, but I know that they do in the same way that they do model onboarding. They have, for instant runs, they do have things like, you know, magnetic field model evaluations, and having a coordinate conversion tool could be something that they would be interested in. And so setting up that kind of modernization or porting or whatever needs to happen of the code as part of a transition to an instant run capability could be one way of actually doing that.
I have a question comment. Backing out before, I think there is already a NASA Roses call for rescuing legacy code. I can't remember the title. I'll have to look it up. I believe so. But I think it was directed towards modeling code.
I believe it was, yeah.
So that needs to be added to maybe HTM rather than HDEE. I have that as a note. But on what Steve Morley said, so Darren, I should hand you the mic next. But my comment coming from Center for Helioanalytics and tied to HDRL is that, you know, coordinate conversions aren't just needed for model outputs. It's needed for observational outputs too. I mean, you can't get, what is it called? The thing we wrote for Katie. I'm spacing out on the term. The thing we needed the team coordinate system for. Two-line elements. You can't get two-line elements unless you use an AstroPy coordinate system. And then you have to convert to other things. So this coordinate conversion isn't just model outputs. It isn't just observational. It's both. So my thought, my thought is that it needs to live outside and maybe as some sort of interface that Steve was talking about, but hosted at HDRL or even at PyHC, because it is technically a software. But that would demand more infrastructure of PyHC. Let me hand this off to Darren.
I mean, each of these codes are independent. Anyone can use them. Anyone can make them a dependency. And a lot of people do. It would just be nicer if they were easier to install.
Lutz has his hand up. I'll let Lutz answer this one.
Yeah, so I just wondering about this. Usually at the CCMC, once we onboard like an old Fortran code, we try to do some adjustments to it as little as possible to keep the original code as possible. And usually we get it to run with fairly modern Fortran compilers. I guess the issue becomes more severe when you run it in multiple operating system, or you want to make it as portable to the different operating system. So on our Linux operating systems, we usually have no major problems getting things to run. And so I don't know how much effort beyond what we typically do for onboarding would be required. So it might be yeah. And I think it would be good to have it validated and tested against some older versions, so we know that it preserves the data or preserves the output as it originally was designed.
It also comes down to what is it appropriate for CCMC? Is this a standalone tool or something that should be part of a pipeline where you want it elsewhere? And then having it as your Python package is certainly very, very useful. If it's a standard, hey, I want to request this, run this conversion, get a result back, look at it, that's something that could easily be placed at CCMC. It's a matter of your use case. Is putting it at CCMC the right place and the right workflow for how you want to use it? And if so, then contact us, contact Masha, and we can look at whether that is a package that should be onboarded and brought in. But in general, a lot of CCMC is the run request, the science stuff. There is some more science stuff that comes into our ISWA data set and visualizing those pieces. But in general, CCMC is not first a science analysis toolkit. It's more of a hosting things that other people can't support themselves, right? And so we could have that discussion on whether this is an appropriate thing to host at CCMC, though.
Yeah, that's a important consideration. And many of those coordinate transformations, I think we have some version of coordinate transformation. I think AAGCM, an older version already, but I'm not even sure if it's regularly used, and it should be part of a larger package, and it could be even, yeah. So
Yeah.
those Python packages.
So just to
be
confirm
available.
that, Lutz, I just pulled up the CCMC instant runs page, and there is in fact an instant run for AACGM coordinates. It does look like it's an older one.
Yes, it is.
So, you know, I mean, I think it's a good place to have a discussion around whether that can be used to update CCMC's capabilities and also support at the same time the modernization that Angeline was talking about.
Yeah, we can certainly consider that. And the tool like OCBPy might be an interesting tool as well for model comparison with MHD models. They would also calculate the open-close boundary from first principles. And so that would, I think it's an interesting tool to onboard at the CCMC. Yeah,
So
that's
one way to do it.
Presentation.
So one way to do it is if 5 seconds promise. If we're going to build a PyHC coordinate conversion tool, then that could be embedded in all of these other websites without having to install it anywhere. Anyway.
Feel free to continue the discussion in the chat. We got to move on to the next topic though. Joey, XRT Pi. I'm going to go ahead and share that. Share. Okay.
Thank you. Can you hear me? Okay, great. Awesome. So first of all, I want to say thank you for inviting XRT Pi to the PyHC meeting. And today I'm going to give you an introduction about XRT Pi, a Hinode X-ray telescope Python package. To begin, if you see the screen on the left, you'll see our link to read the docs. Here you will find all documentation related to XRT Pi. I encourage you to visit it. At the center, you will see the XRT Pi email. You can email us there for anything XRT Pi related. And at the very end, you will find our GitHub account where you can find all XRT Pi activities that we're currently working on, issues, and etc. So I want to begin by talking about Hinode. Hinode is a solar spacecraft that was launched on September 22nd of 2006. So the Hinode is designed to investigate the sun's magnetic energy, how the sun's magnetic energy gets transformed from the photosphere to the upper atmosphere, the corona, and result into solar eruptions. Hinode is currently following a sun synchronous orbit around the Earth, and it is observing the sun using 3 different instruments. I'm going to briefly talk about each individual one of them. To begin, we have the Solar Optical Telescope, known as SOT, which measures small changes in the magnetic field and investigates how these changes coincide with the dynamic events seen in the solar corona. The other instrument, we have the Extreme Ultraviolet, EUV, imaging spectrometer, known as ISIS, which primary focus is to measure the flow velocity of solar particles and identify the temperature and density of the solar plasma. That is the ionized gas that surrounds the sun, the corona, and beyond. And last but not least, my favorite instrument, it is the X-ray telescope, which takes X-ray images of the sun. So if you look at the illustration on the screen, you will see the elongated, that is an illustration of the Hinode spacecraft. The gold elongated tube, that is the SOT instrument. And right above it, you'll see a dark brick-looking like shape, that would be ISIS. And at the bottom, elongated black tube, that is the XRT instrument. And behind it, you'll see an illustration of the sun. You have 2 different sides. On the right, you see a cooler atmosphere of the sun. On the left, you see a hotter, more active region of the sun. If you are interested in the more information about the Hinode mission, I advise you to visit this book called The Hinode Mission, written in 2008. And the illustration on my screen is the image on the book. So now that we know about
the spacecraft, I want to talk to you about XRT. XRT the XRT captures X-rays images of the highest temperatures of coronal material. We're talking between 1 million to 10 million Kelvin. If you see the image on the right, that is one of the first images ever taken by XRT in October of 2006. As you can see, XRT is able to take full disk center synoptic images. And next, and this is AO poly. Nearly 16 years later, XRT is still observing. This image was taken in October of 2002. It's one of my favorite pictures. You can see cool coronal holes that make a smiley pumpkin-like shape while the rest of the sun is very active. In addition to full disk images, XRT is also able to zoom into particular regions. So I want to show you a video of XRT taking high cadence images using the beryllium-thin filter. These observations were observed with the MAGIC sounding rocket. So what you're seeing is the beryllium-thin, and I don't recall the name of this active region, but this is an example of a zoomed-in active region at high cadence. So now that you know about Hinode, now that you know about XRT, I'd like to tell you the motivation behind XRT Pi. So XRT Pi's purpose is to enable XRT data analysis for Python users. The official Hinode analysis routines were written in the interactive data language, that is IDL, which comes with the cost and some limitations. But NASA and the science community is moving towards Python. So with that, XRT Pi is carefully developed to replicate results from the official IDL routines. I quickly want to introduce our team. We have Kathy Reeves, who is a PI, and Mark Weber, who are some of the initial writers of the XRT routines in IDL. We have Nick Murphy, who is here today. Without the help of Nick, XRT Pi wouldn't really be a package at the moment. So thank you, Nick. He helps with the software background and just teaches so much GitHub and Python related things. So thank you, Nick. And then you have a picture of myself that I took today and John Slavin. Between us two, we review a lot of the IDL routines and rewrite them in Python, write documentation, test them, and make them easy to use. In addition to this, I also want to thank some of the AIA folks. I'd like to thank Will Barnes and Dan Ryan, who have helped contribute ideas and code to the XRT Pi repository. So thank you, Will and Dan, for that. So I just quickly want to spend a minute here, and I will go into more details in just a minute. I'm going to talk about some of the current functionalities that XRT Pi offers. We have channels, which allows you to see the instrument configuration. You're able to calculate the effective area. You're able to calculate the temperature response, including a time-dependent calibration for a specific spectral emission model. That is the Chianti version 10 with abundances, hybrid, photospheric, and coronal. You're able to calculate XRT TEM, which is the temperature and emission measures using the filter ratio method. We offer XRT deconvolve, which sharpens images using the point spread function. And our current code that is in progress is XRT remove light leak, which will be in our next release, hopefully, which is a subtracting light leak images from XRT synoptic composite images. So I'm going to do things a little untraditional here, and I'm going to take us to our site and briefly discuss, show you some of the examples we offer. Okay, so as you visit our site, you're able to follow and install XRT Pi, but I want to focus our attention to this page. So in our documentation site, you can get information about the spacecraft, the instruments, and find some of the code and motivation of the initial IDL routines. Following that, you'll reach our Getting Started page, which talks about the current objects that XRT Pi offers. Moving down, you can see the different filter wheels that XRT has on board and its corresponding filters. And the last place I want to visit is our example page. This is where you find notebooks of how to use XRT Pi. I will review 3 of them with you. So channels, as I mentioned, allows you to see instrument configuration. So you simply import the package, define your filter of choice. We call the channel objects, And with that, we can investigate or look into anything related to the spacecraft. For this example, we'll look at the focus filter. I should note that there's 2 focus filters. So we document how to identify which filter. And here you can see the name of the filter, the material, its density, and thicknesses. I encourage you to visit our site to get more information about channels. The next one I want to show you is the temperature response. Same idea, we import XRT-Pi. And for the temperature response, we define a filter, date and time, and we reference the temperature response fundamentals. This is a class that holds all the functions to calculate the temperature response. So as seen here, we define a filter. In this example, we have carbon poly. We define a date and time. This date and time is nearly a year after the launch date. And here we can call the temperature response function. And below we have our data with units. And to quickly get to the end, here I am showing you a plot. So in the red, you'll see this is 2006, which is near the launch date of XRT, and 2007, a year after, in the blue. And we can see some differences. So the thing to point out here is that this is due to contamination on the CCD. And the main thing I want you to take away is that you're able to do XRT analysis using XRT-Pi. And the last example I want to go over is one of our newest ones called XRT-TEM. So you can in this example, you can directly import the function. And for this case, we are using fit files, and this is data taken from XRT level 1 data. And to use XRT-TM, you need 2 fit files of 2 different filters of nearly the same time. And we use some Pi maps. After reading in our data, I'm gonna skim through it. We're able to output some of the sun maps using the fit files from XRT. So this is our way of trying to use other solar Python packages. Okay, and I want to bring this right back. So with that, I just want to say thank you. And the core of this presentation is to encourage Python and XRT users to use XRT-Pi. We are offering the ability for XRT analysis using XRT-Pi. And we're a fairly new package. And for future works, we hope to make improvements to our documentation, our testing, and user interface. We want to offer the ability for users to input their own abundances. As I mentioned, we only offer the Chianti version 10 coronal, hybrid, and photospheric abundance. And the last thing we look forward to is interoperability with other solar Python packages. Thank you.
Cool, this probably was working. Okay, with regards to the interoperability point, one possibility for an unconference session and hackathon topic would be to create a shared temperature response object that can be used by AIA Pi, XRT Pi, Iris Pi, and other missions. So, yeah.
Question on that. Would that be different for different instruments? Because it's calculating now I'm coming from X-ray on this background. So if you calculate the response, it's very specific to an instrument structure. Is that the same for temperature?
So as I understand it, it would be having the interface be similar so that you don't have to like write code in a completely different style for AIA Pi as for XRT Pi. Andrea, did you have anything more to say about that?
Yeah, so no, that's fine. I know we're short on time. Okay.
This is Will. It just basically the idea would be you would have like a common like Nick was saying, you would sort of have a common object for expressing what the wavelength sensitivity of your different filters, and then the sort of underlying spectra that then you would feed to those filters could be exactly the same, because that's what represents like the sun. or what some emitting object, right? And then you integrate that like emission over those different filters, whether it's from XRT or AIA or some other instrument. And then that's the thing that produces the temperature response of those different instruments.
Thank you, everyone.
Thank you. All right, Daniel, I think you're up next
Right.
to CCSDS.
Thank you. You sure? Coming through?
Yep.
All right, thank you. So I wanted to talk to you today about CCSDS Pi, which is a set of I/O and related utilities for processing binary spacecraft data in the science data processing stage. So when you have binary data that gets transferred from the ground station to your science operations center, and you have a bunch of code to turn this into level 1, level 2 data product, how do you work with that binary spacecraft data? So you can focus on your science and focus on the data processing algorithms. So I've been working on this package with Stephen Christ, and in the past, Stephen Kotrescu has given some great contributions on GitHub. So binary spacecraft data usually comes from the ground station and is transmitted to the Science Operations Center, where it's processed as level 1 and level 2 data. The format that the binary spacecraft data is in the CCSDS data format. And that's a low-level binary format, essentially just a packet frame specification. And it has a lot of low-level kind of formatting to it, in the sense that the bits are very tightly packed. So you might have an 11-bit integer next to a 9-bit integer, next to a 2-bit integer, and so forth. And while you can, in theory, mask out all of them yourself for each individual field you want to look up, that's a very involved task. And what this package does is it automates that decoding procedure so you can focus on your science. So I developed the first algorithm to do this in the general purpose, where you specify a packet layout. Like this field is this many bits and it's this data type, and this next field is that. And I developed an algorithm to do this around 2016 very efficiently. You specify the arbitrary packet layout, and it does vectorized data processing, which is about 100 to 10,000 times faster than the naive pure Python solution that you might do with an off-the-shelf library. I open sourced this in GitHub in 2017 and wrote documentations, unit tests, and website for that. And we now have a DOI for citation. It's under the BS3 license to be as broadly applicable as possible. So brief tour of the API. At the top here is the packet definition, and the bottom is the method you would call to load from a binary file. And when you load from a binary file, you get back a dictionary that maps string field names to the NumPy arrays, where the array is repeated over each packet in the binary file. So it has this kind of method in the code of writing out the individual fields using a list of packet field instances, where you specify the name, the data type, and the bit length. And the idea is that this is very readable. You can glance at that and see what the fields are rather immediately, without having to encode it into a kind of difficult to read data structure. You can also load them from files on disk in a CSV format if that's desirable. So we have a couple additional modules here that I won't go into too much detail on, but there's post-processing data conversions. So for example, if the spacecraft has an analog to digital converter, say it has like an integer, an unsigned integer that corresponds to the temperature, but it's just in digital values, you can apply a transformation to convert that to Kelvin using your own calibration curve. And there's a utilities module for miscellaneous debugging kind of things, for managing, for debugging and seeing, is this file valid? How can I find the nth packet in this file and see what the 8th byte in it is, and so forth. Just handy things to help you as you work with your data. So since open sourcing, it's been picked up by a number of NASA funded projects. I'm just going to mention the heliophysics ones here. The GOES-R Space Weather Suite, they're reprocessing at NOAA in Boulder, used the project. The PUNCH mission at SWRI, developed by Marcus Hughes, has been involved with the project and is using it for their ground data processing. Every instrument on the Hermes Lunar Gateway mission is going to be using this, and they're using it for the redesigned ground system from the MMS Fast Plasma Instrument at Goddard. And these are just the ones we know about because it's in the top few results when you search for CCSDS Python on Google. Oftentimes I just find that someone stars the repository and I'd say, oh, there's someone there using that. And then we have to reach out to them to figure out, what are they doing? So it's community developed right now. The users contribute code and tests. People have come to us saying, hey, to make this work with our code, we would really like this small feature that would make our life a lot easier. And then we implement that for them. And they submit bug reports and so forth. Try to give as much one-on-one support with people as possible, because when their project depends on a library for such like a critical aspect, they kind of want that kind of support, like you might get if it was like an official company like MathWorks or something. So thank you to the contributors here that have contributed: Stephen Christie, Goddard, Marcus Hughes at SWRI, Stephen Kybreski, formerly at Ceres, and Ezra Books, was formerly at Goddard. To talk a little bit about the way the software development has been approached, because it's a decoding library primarily and associated. I'm sorry? It's a decoding library primarily and associated utilities. We put a heavy emphasis on testing, kind of combinatorically, all the different things you could decode. Can we test as many of them as possible to make sure that for data that we didn't anticipate, are we still going to work properly? So we have 96% test coverage with over 90 individual tests. Our testing strategy, we tried to test individual classes and functions as kind of units. Does this input and output work on like a functional level? But also, does this integrated use case, something that we imagine users want to do, does this use case work? And does it work with the amount of code that it should work with? Long term, we're adding a sub-package to automatically generate synthetic data. So this will allow us to do this like round trip testing, where we can like randomly generate synthetic data and then decode it and then test that what we put in is what we got out. And we can do the technique called fuzzing to detect edge cases, basically kind of combinatorically sampling the entire space of packet definitions and then doing this round trip testing. For the user's guide and the documentation, we have a detailed set of pages that go through the different aspects of the tasks that one might want to do and the concepts one might to do, and show the different examples of code that people would want to do. So kind of we have the API documentation where you can look up a specific function, but also kind of a use case like, I know I want to do this thing, how do I do this thing, kind of approach to documentation. And between those two, I think it covers pretty much any way anyone would want to interface with documentation. So I'm wrapping up here. Where we're going, in the last release, we released this converter system for post-processing data. We added support for variable length packets and these miscellaneous tools for debugging. And where we're going to go from here is we're going to add tools to generate synthetic data, so you can generate fake packets to feed in as they come down from the spacecraft before the spacecraft is built, so you can test your data processing system and really just begin your development lifecycle earlier. The Europa Clipper data systems team at JPL is hiring an intern to work full-time over the summer on this project, and they'll be adding whatever features they identify would be useful for the Europa Clipper data system at JPL. In the long term, I want to move to a community governance model, ideally where there's representation from multiple centers, where people can say like, hey, we have these kinds of projects coming into our center, And these kinds of requirements would be very useful for us. So that's where I want to go. Obviously, getting the people involved to do that is a major hurdle, but if you're interested, let me know. So thank you. That concludes my talk. Are there any questions?
Hey, Daniel, thanks for that talk. I'm just curious, do you know what the biggest difference between your package and Gavin Medley's, the space packet parser package that was just recently presented a few weeks ago is?
Gavin's package is designed around these XML files where you specify the packet definition in XML and then decode it that way. There's a number of differences between the API design between Gavin's package and my package. My package decodes entire files at a time, and it includes a number of utilities for debugging. Gavin's package is more of a bare bones decoder, and I think he intends to keep it that way, and rather than it be a broad community developed framework.
Okay, thanks for clarifying. Cool. All right. Well, thanks, Daniel.
Thank you.
Okay. Alec online? I think he's up next. Alec Engel. Are you there? I see you. I'll ask him to unmute. Yeah. Are you there, Alec? This thing's lighting up, but I don't hear him.
I work with Alec. I can message him and see if he's online.
I cannot hear anybody on my side.
Oh, there you are. We can hear you now.
I'm on a stupid Windows machine.
Yeah.
Guess we should keep talking. We won't know whether he can hear us.
Yeah, that's true. What a nice day it is outside. I don't know what all to talk about. I suppose while Alex figuring that out, we could just swap real quick. Sean, did you want to bring up the topic? You're right after Alex.
Oh,
Yeah.
I could do that. I don't need, but just a few moments.
Yeah, sure. Exactly. So maybe we can just, while Alex figuring that out.
I mean,
Would you like a mic?
well, hold on. Alec is reconnecting. I think he's figured out something on a different account this time. It looks like.
Hey, can you guys hear me?
Yeah.
Yep.
Can you hear us?
Yep, sorry about that. I had to join another call because I think we're running behind, right? So I
A
had
little
to
bit, yeah.
drop.
Sorry about that.
No worries. So sorry, I had to drop and come back in, and then my Windows
No
decided
worries.
to take a bathroom break on me. Okay, so I will share my screen. Sorry about that, folks.
No worries. Thank you
I
for
share my
hanging
screen
around.
on my other account. Let me know if you get feedback, because when you do Windows 11 with two screens, it seems to not like life. All right, so here you go. Should see my screen, yeah, coming up. I'll check on my other computer too, actually.
Yep.
All right,
Looks good.
beautiful. All right, let's do this. Okay, so thank you for the opportunity for us to present this effort. This was under the NASA B19 HITS program, Heliophysics Innovative Technology, I believe software or science or HITS, the HITS program there. So NextGen teamed up with Anaconda here to do extending open source software to streamline heliophysics data analysis. Bit of a mouthful, but that was the title of the proposal we submitted and got funded for. The project scope, we will enhance we did enhance software libraries that will streamline how scientists access, visualize, interrogate, and analyze heliophysics and astrophysics imagery and time series data. So some of the libraries that we extended their capabilities to make more practical with large quantities of remotely accessed heliophysics data, including Bokeh, FSS Spec, and Kerchunk, as well as the HoloViews library, Data Shader, and a couple of others as well that Jim Bednar and Ian Thomas, who are on here from Anaconda, that can answer more specifically if there are questions regarding actually what was done there. The dashboards developed to prove these libraries were effective was done in sprints, which is a cloud native AWS GovCloud environment. And really the idea eventually is to make this stuff useful in HDRL for folks. So it's not just using in our environment at all. Please ignore the proprietary markings here. Okay, so overall goal and application here is to investigate and enhance the Bokeh and the Kerchunk software and apply the improvements to heliophysics imagery and in situ data to streamline access, visualization, and annotation, which is a critical part for data analysis. So the data sets that we used, that we looked at, were GOES X-rays and particle data in situ from 1986 through 2022. And then ACE Discover 1997 through 2022. And then there were also events such as flares and associated events such as flares and SEPs that were used as annotations. And you can sort of see that on the right there with that plot. So the tables, the table 1 there identifies the different formats and types that we use. So the Parquet time series was used for the GOES and ACE Discover data sets there. And then for the imagery side, which is the next box below, 7 hours continuous AIA data from September 2017. During that X9 flare, I believe, we used FITS compressed, which is sort of the legacy data type, and also what is being uploaded into HDRL HelioCloud. And you can just see the volume associated with that. And then we also translated that into the ZAR compressed format, and you can see the volume for that as well. So that's a summary of the overall goal and the data used in this. A couple of screenshots. We're going to give you a demonstration of this in a moment. So I just have a few slides here. So on the top here, you'll see 2 panels of these newly created dashboards. We created these dashboards originally in sprints, but using the Parquet formats, you are able to really streamline the ability to visualize lots of in situ data. So on the left there, you're viewing, for instance, an entire month of data. On the right there, you're viewing an entire year of data. And you can see these in situ measurements come up in front of your face in a matter of seconds, which is super useful. And so the community may consider translating some of these data sets that you have in NetCDF or whatever into a Parquet format for that streamlined visual analysis and other capabilities. On the bottom there, you see more of another dashboard example there, but with an image there, with an annotation box around an active region. And from there, you can do a calculation, for instance, of the total flux. In that case, it's 94 angstroms, looking at AIA image there, but across all 6 EUV wavelengths, and run a calculation, again, using these different library forms. I'm going to skip over these benchmarks. You guys can take a look at them over in the Google Drive folder where all the presentations are. This is something I'm probably going to get more in discussions with Brian Thomas and Jack Ireland and others involved in HDRL to have a better understanding of the performance of this type of stuff and if it is useful for users of the Helio Cloud ecosystem to get some of this up and running. So next steps and conclusions before going on to a demo for you guys. There's what we're calling the lazy world coordinate system evaluation, and that we found to be useful for analysis on the cloud. A couple of things that we'd like to see done, parallelization should be implemented, and then also adoption and also improvement by the communities such as AstroPi and SunPi. Ian Thomas is on the line here, and he can answer questions about that at the end. The Kerchunk FSS spec works well with the compressed FITS SDO legacy files. So that's also a good thing to consider if you're using the cloud to do your analysis. And then consider visualization of SDO and other solar imagery without WCS, simply to explore the data and then potentially activate this lazy WCS calculations when you actually want to do an analysis of the data that you know, in arc seconds and all that jazz. Both Parquet and ZAR are extremely powerful as cloud data formats. If a data set is consistently used by the community, it should be translated, such as the example I gave earlier with GOES, ACE Discover. Other ones certainly exist, Omni, what have you, because it is very flexible to be used. Helps limit what you want to download, what you need to download from the cloud, because that's costly. I've heard some feedback from the community in terms of using the cloud. A lot of concern from the community is, hey, I want to download the data. Why do you want to download the data? Because I can do a better analysis on my local. Okay, well, how about this software help you out? Do that analysis on the cloud, and that's the idea. So we want to steer people away from downloading from costly AWS services. And then the dashboards created under this effort can be treated as a quote gallery type of examples for the community to be further extended, or potentially just create your own type of dashboard. And then lastly here, before handing it over to Harold for a couple of demos, these are the libraries that were updated under the effort. If you're familiar with Python, you'll see that these are core Python libraries: Bokeh, FSS Spec, HoloViews, HV and Data Shader. So I think with that, we'll shift over to Harold demonstrating. So Harold, I'll relinquish the screen here over to you. I can figure that out. I'll share. I'll share. Stop share.
Alrighty, let me share my screen. Screen one. All right, can you see my screen?
Yep, thanks, Harold. Got it. So this is the original dashboard of Sprints. If you requested Sprints to pull up this particular date time of September 2017 for this X9 flare, it would take some time to pull up, maybe 20 seconds or so. It's using a timescale database on the back end. And it also has these annotations, as you can see. And if you were to click on the table on the right here, you would see that flare is associated to that solar energetic particle event. And so a lot of this effort with Anaconda was to update this using the Parquet data format. The Parquet data format could act as an intermediate data source between a database like Timescale, PostgreSQL, so you can be more engaged with your data because it's a more reactive type of experience for the user, and therefore your analysis could also be considered streamlined. All right, Harold, why don't we pull up the new and improved dashboard that uses Parquet? Okay, so it's already pulled up for us here, and you can see the annotations, same date, but it is using the Parquet format on the back end. It does have a SQLite database that helps with some of the annotations here and some of the event associations. I think it's a pretty useful tool if you're part of the community that is concerned with events. I think it also can help this community align with describing events and things like that. All right, Harold, you want to zoom out to a month-long period here and just give the audience an idea how long it takes to visualize a month of this data? Okay, so super quick. All right, and the annotations come in. The annotations do take a little bit longer here. So they're fully populated. So we could have a toggle switch that says, nope, I don't want to see the annotations that you put in there, and it would be that much faster. All right, let's go for a year, Harold. Let's view all of GOES, X-rays, protons, and I guess this would still be Discover solar wind. And this takes, so you can see it readjusted. All right, so it looks like we got the X-rays coming in, and you can see the top right progress circle there. Okay, so long and the short are in there now. Now we got the 5 proton channels, 1 MeV, 5, 10, 30, 50, 100. That looks like populating the 100 there last but not least. And there's the solar wind. Again, it's just BZ, BT. And then the annotations come in last, and those will take a little bit longer, of course, depending on the number of events that you have in that year. Right, so flares, you certainly have hundreds of events in a year, so that'll take some time. So that may spin because the annotations, that's something that we can look to improve. I know Anaconda, Jim and his team have some ideas on how to improve that as well. So there you can see the solar wind and the X-rays are populated, as well as the proton events, at least according to our catalogs. You have that additional one back in July. Okay, so I think that does it for the time series data dashboard. Again, a really useful type of ability here, I think, with Parquet and these type of dashboards for the community. Let's shift over to the other example one, Harold. The one with the image. Okay, cool. So this one here is we're pointing out about, like I said, 7 hours of AIA data. We're visualizing the 94 angstrom in particular. You have the ability to do a drop down and select any of the wavelengths on the left. We have a drop down for the time there. We can change that into a time slider. We just ran out of time in terms of project execution. We just concluded the effort last week. But you can see, based on Harold's selection of this active region that produced this X flare, it created a time series of all the different wavelengths. This did take quite some time because of the world coordinate system being calculated. We did this both on the ZAR files and on the FITS files compressed. And again, I'll refer to the benchmarking of that access type of deal. But if you want to do analysis of post-flare loops and you want to see how they cool over a period of time after a flare, you can still calculate this and let it run in the background, and also walk away with your analysis without having to download any of the data needed to do so. So I don't want to take up any more time, and I want to leave some time perhaps for Jim and Ian to add anything additional here that I may have missed. So Jim and Ian, maybe over to you, and then we can open it up to questions.
The only thing I would add, thanks for that, Alec, is that the particular dashboards that you showed are meant to be kind of an advertisement for the underlying tools, and the underlying tools are meant to be fully general. And when we were working on this project, we encountered various obstacles and like, oh, that doesn't work very well. And instead of making the dashboard be much more complicated, we tried to make the underlying tool be better so that things would just work better in general. And so what these do is demonstrate a certain level of capability. But if you want a different dashboard with different data in a different way, linked in a different way, that's also meant to be easy. The further away you get from what's already been shown here, you might encounter new things that are not as easily done. But these are just now implemented on top of fully generic tools that anyone can use in any scientific domain. But we just pushed in on any of the things that were harder to implement for this particular case. Hope that makes sense.
Thanks, Jim. Ian, anything to add there? And I see we got a couple of hands.
Not particularly. I guess we should probably go for the questions and see what people want to ask.
Okay. Will, over to you. You're at the top here.
Yeah, I was just wondering if you could, on the, I think it was your second to last slide on your, that when you were showing your slides, there was a couple points about, I think, the parallelization of WCS, and then something else about things that SunPy and AstroPy need to address. I was just wondering if you could expand on those.
Yeah, so
two
I'll let Ian expand on that, since the lazy, as we call it, the lazy WCS evaluation was on his court. But he does have stuff out there in the SunPy community. Like, I think he's got tasks, or yeah. So go ahead, Ian.
Sure. Yeah. Thank you. Yeah. So essentially, so we're not we're storing the attributes to work out the WCS coordinates on demand rather than the actual coordinates, because that would be a ridiculously large amount of data, and we evaluate those lazily as we require them to be on demand. At the moment, if you like, that code is bespoke for this particular setup. So it only works with a particular shaped data structure, particular length, so on and so forth. So the reference to AstroPy and SunPy was, I guess it's sort of come across as a demand. That's not quite right. There are two ways forward, I guess, if we were to continue with this sort of work. One is we keep this sort of bespoke solution for a particular data set that we've got here, and then somebody comes along with a slightly different arrangement of data, we have to have another bespoke solution. Or if there can be a generic solution that fits multi-dimensional data, which fits within one of the existing frameworks, such as AstroPy or SunPy. That's the sort of the summary.
And you do have something, Ian, in GitHub, or some comment, right, over in SunPy's court, right? So this is something that their community is aware of. I think we advertised to them early on in the project.
I think we've had a few exchanges on I think it's a SunPy issue. I think, yeah, I mean, Will himself has been involved in some of that.
Yeah, I think it's an open issue on the IndyCube repository where that discussion has.
Yeah.
Okay, all right. And then I just had one comment about this dashboard that's up here. The coordinates on this image are definitely not right. Like the
yeah,
there's
the units,
no way.
the units are off, but it is
Okay, all right.
It is correct. It is correct. We didn't change it in time there, but yeah.
Gotcha.
Thanks, Will.
Okay.
Yep.
All right.
Good eye. Yep. They're not, advertised correctly. Kathy. Hey, Kathy.
Hey, Alec. I was just wondering if there was anything keeping you from using the same tool with XRT data.
No, nothing. Give me the de-jitter IDL routine in Python from XRT Pi, right? And then rock and roll with this.
Yeah, the level 1 data is already de-jittered, so you should be able to do it.
Yep. So it's, can be done.
Cool. Thanks.
John?
Yeah. Hi, Alec. This is John. Yeah. This is great. Converting to ZAR and making these things more cloud accessible and more performant is great. And we're looking at doing some of that for Helio Cloud too. But one of the questions is, okay, are scientists going to accept a data product that's not theirs? Like, we transformed it to something else. So, what steps do you think are important for like verifying that we got the transformation right? Or is it just that, okay, it's so straightforward that, we're just changing the format, we're not changing the numbers, or, what do we provide for, scientific kind of assurances or whatever that, okay, we transformed this, but it's still the same thing?
Yeah, it's a great question. I think we're sort of not lucky, but we picked these foundational sets like GOES, X-rays, and things, so we didn't have to worry about that. But honestly, that's the importance of working with software engineers and scientists together, right? Okay, the software engineers tried to develop these tools, and here's what we have. Hope you like their functionality and things like that, but please, pound on them and figure out if they do meet the requirements that you have. So I think it is a communication sort of chain game that has to go on, and again, hopefully the a cloud ecosystem on top of other ways of communicating this type of stuff will streamline that to get these types of things used. So I think it's a bit of an open question there, John, but yeah, melding of the minds between the engineers and the scientists and the
And I
people who
think-
straddle both. Go ahead, Jim.
Yeah, I should point out that in this project, we work simultaneously with 2 cases of data, either convert it all into the best, highest performance, just perfectly appropriate data type for the type of things we're doing, but also leave it in its original format and make readers that access the data where it is. And we look and we see the performance implications. In some scenarios, you don't need the latest and greatest. Working with where it is fine. Sometimes you see huge performance benefits from doing that. But you can work with either one, and you can set up automated routines that compare the results to make sure that it's okay. We are helping to, Martin, who's not here, was involved in that, and so I'm kind of speaking for him. But anyway, basically, they're trying to make it as accessible to do cloud computing on the original data as is possible. But at some point, it's not possible. At some point, there are some things that you do have to really reorganize the data. You can't just re-index the data. In that case, we have the other alternative, but you should be able to switch back and forth between them as appropriate, compare their performance, compare their accuracy.
So can that comparison be automated? I mean, that comparing the accuracy, or, do we get the same answer here and there? If that can be made generic enough, then there could almost be like a certification process. Hey, I went through the PyHC approved way to verify my ZAR files. I can now use these in the cloud. They're scientifically the same.
Well, there could always be some bit of metadata that we didn't anticipate. So I don't know that you could do it blindly. You have to say that for this set of files, yes, this is the correct, this has been validated. There is nothing that's missing. We checked every bit of metadata in here. It is available in the new one. It's being respected. And so it depends on the file format. Some file formats you can be very clear about. Other file formats have certain conventions that are used in the field that generally apply. Those are much less easy to be authoritative about. But you
So it
can
might not be
certainly
worth
automate it.
automating, you're saying. It still needs a sanity check by somebody to make sure, and some kind of, knowledgeable eyeballs to confirm.
You basically have to have a human who says, this is the universe of things that we are going to consider from over here. And then if you say that and you pin that down, then you can automate the matching. But somebody has to vouch for it, and there won't be anything surprising in those files. No, it's going to be these things.
Right. Great, thank you.
And anybody who's interested, check out Kerchunk. That is how we can access legacy file formats in a high performance chunked way that is cloud friendly. And it's amazing. It very often works almost as well as converting everything.
One more question. This is Rebecca Ringett. Are there any plans to compare what your team has done here to a method that uses netcdf files as ZAR instead of converting them?
That is definitely what Kerchunk can do. I don't know who in this community is working on that. We're working on that with a bunch of people who are not sun scientists, but earth scientists. So we have a lot of workflows in that area already. And generally netcdf can be treated as if it were native ZAR in very many cases, and it works quite well. So I don't know who's going to validate that for this community, but we're certainly working on that in other communities.
Yeah, one comment on the netcdf, it does work well compared to ZAR, but the file volume is quite a bit larger in our experience compared to ZAR. So at least that's one of the downsides that we've found, as opposed to ZAR is a lot smaller.
But if it's already on disk, then what does it matter?
Yeah, you're right. True. All right. Thank you guys very much.
Thanks, Alec. Okay, short little discussion led by Sean on PyHC packages in our organization.
See if I have a demo loaded up on this computer here, and I do, in fact.
Cool.
Cool.
Do we want to connect your laptop?
At the risk of entirely breaking our audio visual setup, yes, I think I would like to plug in my laptop.
I vaguely recall how this was done. Give it a shot.
All right. Give it a shot. Okay, looking good. Just unmute myself. I'm assuming people are hearing me through my laptop microphone, but do I come through okay?
I can hear you.
That's a maybe.
Sounds good.
Not getting confirmation that my audio is actually going through. Anybody in the participants list remote, can you confirm if you're hearing me?
Yes.
I'm hearing you clearly.
Okay, okay, it's just no one wanted to speak up to let me know I'm audible. Glad I'm audible. Okay, so anyway, I'm just gonna be leading a very quick discussion about what to do with project evaluations, and maybe this will turn into I'm just announcing a decision, but maybe if anyone has any input, I would love to hear it. Somebody says, yes, we can hear you, but you can't hear us, I think you're right. Maybe if I unmuted my laptop and don't have it turned up all the way, I might be able to hear you and it might just come out through my laptop. So anyway, now that I've entirely broken the sanity of the audio visual setup, we are here to talk about how we've been evaluating PyHC projects for standards compliance. If you've seen this projects page on our website at any time at all, you'll recognize these little grading badges we've been using for a few years. You know, they talk about, you know, how well we've done things like setting up our repos for open source community building, how well you've documented it, tested it, how good is your software, do you support Python 3, and do you have a license? Pretty basic evaluations. We're not actually going through every single we have like 15 requirements in the standards. We're not going through every single one of them, but we have a lot of unevaluated projects. And the question has been, what do we do with them? And this has some fun backstory because right before the pandemic hit, we had a real big community meeting and we all decided that the start of 2020 was going to be the hard cutoff date. If you had not self-evaluated by 2020, you were not going to be allowed to remain a PyHC package anymore. You were going to get the boot and we were going to play hardball. But obviously all bets were immediately off once 2020 actually hit. And this has been on the back burner for a while, actually. I think we even have documentation somewhere that still says if you haven't self-evaluated by a certain date, we're going to remove you. And we just haven't been living up to that. So we're not trying to kick anybody out of PyHC. We are trying to politely encourage self-evaluations while I have not been doing very many project evaluations on my own time as tech lead over here. But one of our members has kindly put together a pull request of what it would look like if we added a third table to our website. If I scroll all the way down here, unevaluated packages. We have this idea of we could just have a third category of project on the PyHC website
sort of like a use at your own risk section. These are all the packages where you do not see community badges. And in fact, it would probably make sense to just remove these columns from the table altogether if we had this table on here, but then you would see all these projects, most of which were made by Michael Hirsch. So that's fun. And you would, be able to still access them, but you would feel like they were less a part of PyHC, and you would be more weary to bring them into your ecosystem. That's sort of the idea. Maybe people in the room get priority opinions. Does anybody think this is an awful idea that we should not pursue?
Yeah, the online folks don't get to have an opinion. I think the first thing we should do is poke these people and see what's going on. Because I think there's a question of, if you want to be part of the PyHC community, quote unquote, and you're not feeling up to this task, whether because you don't care or because it's too arduous, those are two very different responses we should be having as a community. Those are there, but I think we should find out why. And then I would lean towards, rather than having this in with the other things, shove them in a different corner. Maybe we do a different, maybe he's a similar back end, but I could also see us as a community wanting to suggest or point at other packages that are useful that maybe haven't been, so people can either say, hey, I want to be in your other stuff, or we put them in there. But there's a very clear distinction between PyHC packages and other ecosystem packages. I would agree that keeping them around in some sense as a resource for the community rather than pretending they don't exist is probably a good idea. But then also it means that including them on that list is kind of at the discretion of, well, probably you.
Yeah.
But I think it just moves into here's a bunch of other stuff that might be useful to you, use at your own risk.
In a lot of ways, this is like the, page 2 or 3 of a Google search. Sometimes those are the obscure solutions you're looking for, and you haven't found them in the main things. All right. So you've still got a collection of them, but I agree with pushing them down your priority list in how well, they've been incorporated into the community. But having some collection of these might have some use is still a valuable resource to me.
Thank you.
Yeah, I agree with that. I mean, I think having the PyHC brand mean something is good, but we also do want to collect things that could be useful to people. And, if it could just be that you don't have the funding anymore to do this or whatever. So I like this solution. Unevaluated packages. These are things we're aware of, but they haven't met all of our community standards, but they could still be useful. It's just, like the CDF lib one in there, that's, probably a lot of people are using that. So that's probably pretty useful still. So, I would probably feel comfortable using that. I might want to check with the authors, and one thing that could be useful would be a last updated date or something in here. When's the last time this was, modified? Usually people look at that, oh, good, this is being updated, or, oh, wow, 3 years, no updates. Then I probably wouldn't even look at that one.
I wonder if I could scrape that just directly from the GitHub commits. That wouldn't be too hard, I don't know.
Oh, and the Python version is what Rebecca was saying.
Yeah.
I think it's available through the API of GitHub.
Oh,
say that again.
Say that again. Someone said something online we couldn't hear.
Sorry, I think you can access that through the GitHub's API, and it should be there. The question is, do we want to go by the main
like the main branch or the release branch, or like, you know, how do we know which branch is the one that we really want, that, you know, that it's actually like we're updating the stable branch. We're not just following people's experiments.
Yeah, I guess it would have to be maybe a last updated on any branch. If you have to specify a branch, that might automatically become an issue.
I think it's really about having a pulse on the project. Like, has anyone thought of this in the last 6 months? And if they're doing some work on some branch, that's still a pulse.
Yeah.
Very good point.
Angeline, you've had your hand up.
Yeah, I just, I really do like the idea of being able to scrape perhaps like the last updated date in order to help people identify vaporware, because that is just always going to be an issue in our community. But I do like the idea of moving these things to a separate table or a separate page, because, you know, these people have interacted at some point with the community, and whether or not they're interested in meeting the standards or not, having a place to put that there kind of lowers the bar for entry, which I think is a good thing.
And I guess on the topic of lowering a bar, I've had this Michael Hurst search up on my screen for a little bit here. I did a quick count. Only 9 of the projects that have been unevaluated are not this guy. So in theory, I could actually reach out to 9 different people and get their opinions individually on how they felt about whether or not they were going to evaluate at some point. Yeah. He is somebody I talk to every week, so I'm sure I could. Yeah, I noticed PyTplot is in this list too, and whoops, I would have actually done something about that before I stuck it out in its own little corner like this. Sorry, PyTplot. But so I think that's what I'm leaning toward doing, is I'm leaning toward reaching out to the people who aren't Michael in this list and seeing the level of involvement they have with their own packages and what they want to do with PyHC and stuff. I like this idea of having a last updated column, and I'm going to give myself like a JIRA ticket to look into that. These columns are already getting pretty long, so I'm not.
Well, there's one you can drop, I hope.
Yeah.
Python 3, I would hope it. Although honestly, some of the unevaluated stuff that might be applicable. But when you contact people, like, feel free to make the offer on the behalf of the community that if they want somebody else to evaluate it, you know, if honestly even just doing that. And then for last update, I'd say last release is probably the most relevant.
Last release.
So you can pull that potentially from the GitHub releases or from PyPy.
Last release. Ooh, even better.
Actually, I don't know if that would work for PyTplot, because the one we're using is not the master branch. So if you look on PyPy, it's not PyTplot, it's this other like matplotlib version.
I think there are 2 issues here. One is the project itself forgotten? And second, if PyHC forgot about the project. So technically there are 2 release dates, and everyone can go on a GitHub and see immediately if the project is abandoned or no. But what I'm interested, like, for example, looking at this table, when this table was updated, when this partial emit, this banner was switched from good to partially emit or all the way around.
Yeah.
So I think that is probably better metric to understand, like, are we keeping track of the project and not if the project itself was updated?
Absolutely. Well, all of this gives me actually concrete actionable things I can do that I was not thinking of before I brought it up, which was almost already more than I expected to get out of jumping up here and talking about this. So that's awesome. I've been following along everyone's chat messages in here, and I don't disagree with anything that's been said. I do like the idea of going ahead and removing this Python 3 and license thing. I don't think we need to be advertising that per se. I definitely check for that when people submit new PRs for new PyHC projects. And lately I've been saying you have to evaluate. Like there's been 2 recent examples where someone submitted a PR to add their package to PyHC. And I said, nope, I'm not clicking merge until you self-evaluate. And then a couple of days later, they added their badges and then I added. So that's already a thing for adding new packages. I can just ensure that no Python 2.7 reliant packages get added here, and I can remove that column, clean it up a little bit. And I can think about considering displaying recent updates in some form, either release or GitHub updates, although I need to keep in mind, as I think it was Will just said in the chat, that for a very mature but small use case package, it might not need to be updated ever again. So that might be an unfair metric for some packages. Anyway, I don't know that I need to belabor the point anymore. So I might go ahead and call that good there and say decision more or less made. To-do lists added to my to-do. Cool. I will end it there then. Thanks, guys. Oh, don't applaud me. I did nothing. Yep. For anybody who didn't hear that, we're taking a quick break and starting again at 3 o'clock Mountain Time.
Hey, Julie, are you there?
Sorry, can you say that again?
Are you there?
Yeah.
Yeah. I wanted to follow up about your comment about Gavin's project. You said that he had presented at the PyHC a few weeks ago?
Yes, that is correct.
Hey, stickers. Thanks, man.
Okay. Yeah, I had been a little bit concerned about the overlap between our projects, and I had reached out to him in the past about combining the projects, but unfortunately, he decided that he didn't want to do that. And there's still so much open source work to do. It's not really ideal for 2 people to be working on the same thing. Do you have any advice on how to approach that? What does PyHC recommend?
Oh, yeah, that's something we thought about for a while now, of how best to handle duplicated efforts. In this case, I would I'm happy to reach out and connect you 2 and give him a more compelling reason why it might be worth combining packages. In the past, we haven't necessarily discouraged people from, having a different way of doing things, but if there's significant overlap, then it wouldn't really make sense anymore to have completely separate efforts. Yeah, maybe that can start with an email from me, since I know him personally, but
It's a delicate, to be honest, it's a little bit delicate issue. I did offer.
Core field model. The core field model here. So the simple case is just this IGRF. So I'll go into a little bit more about IGRF, but it's really very simple model. It's just set of coefficients that you actually have them here. Yeah. So if you look at here, it's just these G and H coefficients that you multiply by all of this stuff. So the way that these get determined is really through an averaging of many candidate core field models that go into that are more complicated in their parameterization. So just get rid of that for a second, and there's a series of other spherical harmonic models that they're really analogous to this case, but a bit more complex. So this one's the mid-latitude ionosphere. So it's showing these two cells from the SQ system and the magnetosphere. So this is kind of fitting the data from ground and from LEO to these sort of low degree focal harmonics in the GSM coordinates. It's a bit more complicated than that, but these are the ones that are really highly time variable. So from one hour to the next, they're different, right? And then underneath all that, you have the lithospheric field, which is essentially static. And these models also have induced counterparts. So there's, if I go back to this picture, you have secondary fields that are induced in the mantle. So they really what you sense up here is a combination of this kind of field, this kind of field, and their induced counterparts. So time variations up here will induce currents down here, and those currents in turn create a magnetic field up here. So yeah, and then down here is another example of one of these focal harmonic models that's more complex. So this is the AMPS model, and so it's still focal harmonics, but in this case the coefficients there have a lot of different parameters on there related to solar wind conditions, and you see like this 10.7 there and so on as well. And I think the beta is about the or at least where some of these are to do with the dipole tilt and the solar wind conditions. So one way that you can get some familiarity with these is in the VIRES service. So if you go there, just reset that. So just to give you a quick tutorial how you would use this. So if you just changed the globe view and then go to layers here, you can disable the data. And if you just want to look at the model, you can select that there. And then when you click this button here, then you will see the settings here. And this is where you can choose which models you want to visualize. So we have, say, the IHRF there. And so, yeah, the chaos MMA, that's that magnetospheric model. So this is the effect at Earth from magnetospheric currents. And this is all time variable, right? So you slide it around and it will change. Yeah, it looks like that because of the these are not updating the color range there. But you get the idea here. You can actually look at some of these different models all in a unified interface like that to get some idea there. Part of the reason I'm showing this is because this is backed by a separate Python package called eoxmagmods that contains these models, and there is an embedded IGF model in there. And this is all being evaluated on the fly, so you can kind of tell that it's highly performant. So in cases where you really want very fast model evaluation, it's there, but we need to do more work to make it more usable. Yeah, next I wanted to say a bit more about magnetospheric models, but they're really not my area of expertise. So I don't know if someone else could chip in a little bit to say something about them. Yeah.
This is probably what I was supposed to do, so apologies for that. I abdicated responsibility because I had limited time to prep.
No problem. Yeah.
Yeah. So I guess the most commonly used magnetospheric magnetic field models would be empirical or semi-empirical models, best known being the Sigonenko models. For a lot of stuff, folks will still use older models like the Olsen-Fitzer-Quiet. And so the bulk of these models are essentially just fits to data. You know, so most of the well-known and widely used Sigonenko models are semi-empirical in the sense that they provide a modular set of current systems, and then the parameters for those current systems are what you actually fit to the data. So fit using the data, right? So when you drive the model with your solar wind parameters or geomagnetic indices, whatever goes into it, it'll specify essentially the strengths of, you know, ring current, Birkeland currents, you know, position of the ring current, that kind of thing. Some of the more recent Sigonenko models, you know, they don't specifically work that way. You know, they are more strictly fits to data using either radial basis functions or, you know, kind of similar things to that, which is almost harkening back to how it was done for, you know, earlier models like the Olsen-Fitzer models, but, you know, obviously a bit more sophisticated. And so then I see the next part on here says radiation belts and field light tracing, and I guess that's, you know, what do you need magnetic field models for, right? I mean, so radiation belts obviously is a, you know, everything is dependent on your field model. The field organizes your particles. You know, your particles bounce along the magnetic field lines. They so they gyrate around the magnetic field line, they bounce along the magnetic field line, and they drift in a shell around, like around the Earth. And so for a lot of your applications, whether that's radiation belt, other inner magnetosphere stuff, you know, looking at, you know, kind of mapping of things out to them, out to the tail or to the lobes. This mostly involves a lot of field line tracing. You know, in a lot of cases, you're interested in, well, what's the conjugacy of the magnetic conjugacy of my satellite with some ground station. In order to understand the particle population that you're looking at, you might want to know, okay, I'm probably not at the magnetic equator. Where is that magnetic equator, and what's the ratio of my magnetic field strength locally to that value? And so they're not just a specification where you need, you know, what is the local field. They're widely used as something where you want to specify a more global state, and so you need additional tools for that.
Can I jump in? Just make a
sure,
comment.
please do.
Yeah, so a few basic tasks that to kind of piggyback on the radiation belt discussion that you're having is the calculation of adiabatic invariance.
Yes.
To process radiation belt data.
Mm-hmm.
And there's the Boyd data set for RBSP, which includes those calculations in it. And in addition to that, even not just the radiation belts, but any magnetospheric mission in general, it's interesting to know what L shell you're on, and which L shell you're on comes from a magnetic field model.
Right, absolutely. It's an integral along the field line, and strictly it's a particle quantity, but there's a few different definitions of it. Yeah, I mean, so I was trying to keep it slightly higher level, but yes, absolutely. The adiabatic invariants are exceptionally important for radiation belt uses. So the two, I guess there's kind of three primary tool sets that folks have used over the years for a lot of inner magnetospheric work along those lines. So there's SpenViz, which is, I believe, primarily a web-based service that ESA has. There's an underlying library that I don't think is available code-wise. There's just the interface. And honestly, I haven't used it a lot. There's the Urbum library, which has a long history. It was originally developed by Onera, which is a French institute. And it's more recently come under the kind of umbrella of COSPAR's panel on radiation belt modeling, so the PRBM. And so that's where the name Urbum comes from. And so at its core, it collects together a lot of the different magnetic field models, so the Sigonenko models, as well as some of the other models, older models. It adds in orbit propagators, AE8 and AP8, climatological radiation models. So it pulls in a lot of that stuff, and then adds all of the tooling to do adiabatic invariant calculations. There's more to it than that, because it has to have a lot of associated tools for everything. All of the models are defined in different coordinate systems. Your orbit propagator is defined in a different coordinate system. And so it adds in all of that stuff. And so one of the problems with the Urbum library at the moment is that it is Fortran 77 and it is under-maintained. It is in a reasonably good place. It's fairly mature. It's had a lot of work over the years. The third one, I said there were three. The third one is one called Lanel Geomag. And so that is basically, instead of written in Fortran 77, it's written in C. And that's used so it's used under the hood for example, a lot of the Van Allen probes, processing and magnetic ephemeris. So all of the adiabatic invariants that go into the files that were mentioned. It's used for MMS. And so, that is broadly similar in scope to Urbum and SpenViz. Each has different philosophies. Urbum is, I need an answer and I need it quickly. And it's very good at that. Lanel Geomag is, I'm assuming you want an accurate answer. And if I can't get you an accurate answer, I will fail.
Steve,
and so, go ahead.
I have some code for calculating the adiabatic invariance in MHD model grids. I was thinking about open sourcing it, and I know that Urbum Pi is a part of SpacePi, so that naturally came as something that might be a good fit. Although my package does depend on VTK to do the field line tracing, because the grid is rather, it's an adapted grid. Do you have any thoughts on what would be the best way to open source that?
That's a good question, because like you said, SpacePi from the early days has provided Urbum, like a wrapped version of Urbum. And I don't believe that Urbum has a capability of taking an arbitrary grid and tracing through it, for example, which is presumably why you've developed the code that you have. Lanel Geomag does have that capability, but the Python front end for it is very, very, very bare bones. It's basically auto wrapped, and so it's exceptionally low level, and it only has a couple of kind of higher level user-friendly interfaces. And so I guess the question would be, if that needed a home, I think, is it model specific or is it generic? Is it basically, you know, I can calculate, assuming that I have something in VTK format, then I can calculate adiabatic invariance. You know, I think depending on where it is, it might need a different home. You know what I mean?
So
Yeah.
Steve, this is John Niehoff. We do have some field line tracers for supporting PyBats.
That's true, yes.
And we've been looking at replacing, improving those. So we should maybe continue this conversation offline. But that would seem to be a pretty good match.
Yeah, no, that's true. I mean, it only goes as far as field line tracing though. And so that's, so for the broader group, so SpacePy has in its PyBats, regardless of the name, that's actually support for a full set of models that essentially have some affiliation with the space weather modeling framework. So it's not just Bats or Us, there's, you know, RAM-SCB, RCM, GITM, you know, there's a lot of different models in there. There's no reason that couldn't or shouldn't be broader. It's just that's, you know, those are the contributions that we've had. But yeah, as John said, you know, for that, we obviously do field line tracing ourselves. I believe that's actually one of our C library, C routines that we keep stashed under the hood for speed.
Yeah, field line tracing is really the hard part, is doing the field line tracing and doing it fast.
Yes, or it depend. I mean, it very much depends on what level of accuracy you want as well. I mean, I know that's selectable in VTK.
So this is Sasha. Sasha Drozdov. I want to bring exactly the same point. That's the field line tracing, and not just field line tracing, but basically calculation of K and L star does require a lot of computational power. And like in Python, I don't know if it can be done fast enough. So like this is basically a bottleneck for the data processing, and we have to like enable cadence like every 5 minutes of the data in order to get something from the RBSP or like when we process it ourselves. And in the Urban library, I think it's done in Fortran. And this is how it's like basically possible to calculate diabatic invariance from like TSO4. And the Python there is just a wrapper around the libraries that compiled in Fortran. So like that's maybe not a easy solution just to transfer tracing codes into Python and run them. It's also a question of like, can you do it fast enough for the practical applications?
I don't see that writing like a Runza cutter field line tracing routine in Python is ever going to be the right idea. I think the idea is always going to be something like providing a Python interface to see your Fortran routines that do that heavy computational lifting, which is, I mean, ubiquitous. That's what NumPy and SciPy are all about. So I don't think that should be that should hold anyone back from considering it part of the Python community.
Yeah,
yes,
and I mean,
sorry, yes, I just want to say yes. It should be a wrapper around something that's work fast and provides like easy access to it. And I think, Steve, you're right. So the Urban library does not have arbitrary grid. Like all these codes, I tried to look at them once. They deeply embedded in like in the Fortran structure, the way how the NER was written. This originally was the French comments in the code, so it was difficult to decipher.
Yeah, and you know, while it is in LAN GeoMag because of essentially the need to make it generic, we have a few different approaches that are not specific. They're just like take an arbitrary grid. And so, if you're doing magnetic field models, for example, you probably want to do something that guarantees divergence free when you're interpolating, right? And so essentially what we do is it's kind of like Komodo is doing for most of its work, is it's functionalizing the input data so that and then interpolating. And so we have a few different approaches to doing that, including a radial basis interpolation, where we can include a divergence-free constraint. You don't have to have that turned on, but fitting radial basis functions gets very, very slow very quickly. I think the right answer is to do something in C or modern Fortran and wrap it. And I'm assuming that that's probably what folks who are working on it are actually doing. The problem with things like, Urbum and Lanel Geomag is that they're very large codes that are very interdependent. And if you just want one little piece of it, it's hard to separate that out. Lanel Geomag especially, is like, I don't even know how to build that on Windows, and SpacePy supports Windows. So it's probably never going to be wrapped for SpacePy because I don't know how to build it for Windows.
Maybe we should talk, because I've been doing some of the Urbum library kind of conversion for Windows, and I was able to run it on Windows 10 and other things.
Oh yeah, no, we provide Urbum on Windows, like through SpacePy. That's not a problem. It's Lanel Geomag's build system is a little more complex. If you want, if you want to talk to, if you want to chat about that, we can absolutely do that. John Niehoff is probably a better person to talk to about the build system for that, even though I know he doesn't want to.
Yeah, we can do it offline.
And so I guess to come back to this slide, right? I see somebody added the TS07, so thank you for that. And earlier on, I think we also had some of the RBF-based models, like the TA16, that had been mentioned as well. And I recently actually rewrote that in C for Lanel Geomag, which was quite an ordeal. Although it did correct an error in Sigonenko's code, so he's actually updated the version on his website to fix that. So if you were using TA16, make sure you've got the corrected version. And then for working with the models like Batsaras, Gamera, Vlasiator, OpenGGCM, if there's any of those folks on the call. I guess this is where you either need the tools from the team or someone like Komodo to actually read that model output into a useful format, so that you can then get into, now how do I do my tracing, adiabatic invariant calculation, or even just at the core of that, evaluating the field strength at an arbitrary location, right? Or field vector. Are we done with this slide? Does anyone have things about this slide?
So the last point there was that the IGRF feeds into these. I suppose I have a question for you guys there. Like, what could be done, like with the publishing of IGRF, or that would improve the way that IGF interfaces.
So since I'm already unmuted, I'll give my opinion first. So I all I really do with IGRF in terms of like, how it's like, I use the reference implementations, the Fortran code or Noah's web calculator, basically to provide verification that the implementation that we provide in LanoGeoMag and the tentative version that's in SpacePy is correct. Beyond that, I am very, very, very pleased that they provide the coefficients now in a separate file with a defined file format, so that when a new IGRF comes out, you just grab a new coefficient file.
Yeah, just dump it in there. Yep.
Yes. And so from my perspective, that's what I need from IGRF is I need some reference that implementation that is not hard to use, and where the coefficients are independent of the implementation. And so, in Urbum, I believe, every time you want to update IGRF, I think you actually have to go in and touch code, because I think it's hard coded into data tables, which is it's a minimal ask, but it's fine. LanoGeoMag, there's a default table which gets updated, but it will read from the files. SpacePy just reads the files. So that's what I want from IGRF. I mean, I have more thoughts, but I'll kick it over to, I guess John's got his hand up.
Oh, yeah, thanks. Is this on? Yeah, okay. I mean, one thing all these mag models have in common is at this point in space or along this line or whatever, these points, I want a 3-vector, right? So should we have a generic representation that we ask people to map to for field models? If you want to be a field model, well, if this was Java, I would say implement this interface in your code. There's a Python calling signature that if you have this, you are a field model, and then you can drop in whatever model you want, and then the codes can be built to do the tracing and the whatnot that don't care what the model is, and then the models just are, pluggable. They're modules that you load in. Oh, I want this model. No, I'd rather try that model. I mean, that seems like a PyHC community thing. Sorry, go ahead.
I think that would definitely work, and I've created like a similar interface like that for my adiabatic invariant code. Part of the nuance is that some models are gridded and some models are not gridded, and you need to do that grid interpolation behind the interface. So if that field line tracing code which calls the interface is in C or Fortran, you're either adding a call to Python every time you iterate in that field line trace, which could be a little bit slow, or you're asking people to write C or Fortran code.
Or you could have different implementations of this sort of key model interface for different types of models based on the way you were expecting them to be used or the efficiency. Right, yeah, that you have, yeah, Rebecca says that's a Komodo concept. But yeah, you have, you just acknowledge that there's different types, and then, but you have a limited number of interfaces that can represent the different types of models that are there. And then, oh, I've got another gridded model, I'll try that here. Or, oh, this algorithm works great with gridded models, so I need a gridded model for this. Or, there are ways of structuring interfaces to indicate these kinds of options.
So honestly, I kind of think that the gridding of the model is almost a red herring here, because fundamentally, if you want to do anything with a model beyond just whether it's, coefficient based or evaluated on a grid. If you want to do anything, you need to evaluate, like you said, the 3 vector of the magnetic field at a location. And so fundamentally, your interface has to do that. You want to trace a field line, you have to be able to essentially evaluate your field at an arbitrary location. And if it's gridded, that means a little extra work to turn it into a model, rather than a data field.
Right, and that's what Komodo has done, is we've functionalized this. So we've removed the gridding, the data structure dependency completely. We've now got a function where we can interpolate wherever you want, right?
Right, and yeah, no,
there's not
absolutely.
a tracing algorithm that works with that yet, which is why we're trying to add that piece onto it. But we've tried to abstract that away so that eventually, if we're loading in, these empirical things as well as all these simulations, it's just a vector that you can evaluate anywhere you want. And then if you have a common tool behind the scenes, you could do that for anything you throw at it.
Right, and that's exactly how we do that in Lanol Geomag as well, is you basically, you don't have like a routine for tracing in a particular field model. There is a tracing routine, and you just assign a function to, your structure has a function for the B field, and so it just calls get B, right?
Right. So you're saying function, I'm saying interface, because I worked in Java for a while. But yeah, that same concept of there's this calling signature that represents the field, and what's behind it, there are tons of routines that don't care what's behind it, whether it's gridded or based on parameters or somebody's hard-coded thing or a toy dipole or whatever,
Exactly. You need to be able to call get B vector.
And probably you want to offer a parallelized version where you give a whole bunch of points and you compute it at all of them. Maybe there's some optimizations for that, or exactly what that interface or that function has to support. That's what we have to standardize on and debate on, because once you commit to that, you're stuck.
Yeah, so like you could pass like a callable or something in Python, like pass a function to get B at this position, right? That's the kind of idea that you had.
I mean, that's how we've implemented it on the C side in Lanol Geomag. I mean, for the urban wrapper is a lot more direct, and so yeah, I mean, in theory, you could actually say, look, we can do this. So you could very easily re-architect things. I mean, I say easily, it's not a small amount of work, it's a lot of work, but it's a lot of straightforward work. You could re-architect things such that, because under the hood, Urbum is doing something very similar. It's basically just, you pass it B. So on the Python side, like, you ask for B. So I think if you want to combine, your IGRF or one of the swarm models with something else, you absolutely would need to do that. I think that's maybe the place to look at it, to look at standardizing is, just say, is there a callable that returns B?
Yeah, and again, I have a comment on this. I think it's generally a great idea to have a standardized interface that returns you B from each model, but it's again the problem of the performance. So if you have to have like a single call and the original code is written in Fortran and you're trying to pass it to Python, you can get 1 point and trace, and the tracing field still has to be done somewhere internally. Otherwise, you will not going to have the same performance. So maybe there can be more to it. So the standard interface, not just for the actual B, but for other things like the field line or like some basic tracing, that would be, I think, better for at least for the space community.
Yeah, to elaborate on that performance thing, which was, I think, my initial thought. I don't know at this level of thinking whether it would be a problem or not, but every step of that solving for the field line trace, you'd have C or Fortran code calling Python code, and crossing that boundary into the Python interpreter can be expensive. Whether it's going to be so expensive that it makes it a no deal, I can't really say right now.
Well, I tried this, but it was fair to say it was several years ago. I did create a library, like compiled library that was returning me something similar, just a single value. And basically was minimal operation on the client side, on the Python side. It still created a huge overhead. If you do something like the passing information from one library, even through the memory to another library, it's already expensive. Maybe it was just a problem with operation system. I don't know. I didn't go deep, but I end up realizing that this is not a solution. So everything should be done in one code. So essentially the for loop should be running on the Fortran, and then you have to get a result. That's how you get the maximum performance. But to be fair, I did it a long time ago, so I don't know if it was my problem of coding things, but seems like that's not going to be cannot be a solution, at least what I think.
I don't want to catastrophize the situation because in SciPy, when you solve an ordinary differential equation, you can pass it a callable to evaluate the derivative of the function at each point in the iteration. So it does work sometimes because the ODE solver in SciPy is ubiquitously used. I think it's a little too early to say whether that's like a prohibitively game-changing challenge.
Yeah, I mean, so the way that we handle things in either LanoGeoMag or in UrbanPy is, if there's a call for evaluating the field as in the underlying language that we wrap, right? So if you want to get the B field, you can do that either with LanoGeoMag directly, or you can do that with Urban directly. There's a Python call, and that essentially evaluates the field model in the native language. If you want to do tracing, then you have a tracing routine written in that native language, and you essentially wrap that tracing routine, right? I mean, which is, I think, what Sasha's probably suggesting, right, as the most efficient way to do it. And I would tend to agree with that. I mean, I think you would ideally want to expose both on the Python side, right? Doing the evaluation in another language and then doing the trace in Python, I think will be slow. There's a limited amount of parallelization that you can do. There is some, we have UrbanPy does parallelize multiple calls to say, for example, like get L star, right? Because if you have the cause, you might as well use it. In LanoGeoMag, we do parallelization in the C. It's a hard problem. And I think, at the most fundamental level, everyone who uses a magnetic field model needs to get the B vector. So I think that's kind of the more important part to kind of get right, I mean, and if everybody wants field line tracing, then maybe we add that. Not everybody needs adiabatic invariance, and honestly, oh boy, there are a lot of algorithmic hiccups in actually getting those right.
Oh yeah, absolutely agree. I started with this: the every magnetic field model should return you the B at the arbitrary location, preferably. And if it's a gridded model, then it can be interface on top of it, similar to what Komodo does, that actually returns you the field at the arbitrary location, like a 3-vector at the arbitrary location. And the problem is I don't know the bottlenecks in the field tracing, and I know there are different methodologies, and it's if there is a specialist among us who knows how the math works behind the tracing and where the bottleneck comes from, that's probably what we should be identifying. It's not what I'm saying. It may not necessarily need to be a field tracing code or field tracing function or interface that field model provides, but something that's is required to perform an efficient field tracing, not necessarily in like within the field model itself.
Yeah, so I guess Lionel Geomag and Urbum and SpenViz, like none of them have model specific tracing, right? I mean, I don't think I would advocate for that at all. But they do all do their tracing different ways, you know. So Urbum uses I believe it uses a fixed step RK4. VTK was mentioned earlier. I think, you know, that gives you the options of doing an Euler step or you know, RK45, which is and actually I forget whether that's adaptive or not. It certainly has adaptive error control. In Lionel Geomag, we actually don't use a Runge-Kutta method. We use, and I'm totally blanking on the name of it. It's the Bullish-Stower method with Richardson extrapolation. And so, you know, but there's a lot of ways of solving an equation, right? Like, I mean, ultimately what you need is something that's going to minimize the bottlenecks of, you know, actually passing data around, reformatting it. Because evaluating a model, it might seem cheap if you get the vector at one location, but say you want to trace a field line, now you have to do it 1,000 times. Like you want to calculate a drift shell. Now you might even be calling it a couple of million times. And so, you know, there's even just evaluating the magnetic field, the magnetic field model itself, you may think like, oh yeah, well, it's like 1 millisecond to evaluate this model. And it's like, no, that's too slow, because that means that the second you go to calculate a drift shell, you're looking at 5 minutes on a single core. Sometimes it's the model itself is not actually fast enough. You know, they're just slow models. Sometimes you have to say, actually, am I doing too much error control? Am I doing too many steps to trace this field line? Is there something I can do to speed that up? And it's that trade-off of accuracy versus speed. And, you know, I guess there's some philosophical choices to make about what you want for any given implementation. Like I said, Urbum tries to be fast and always give you an answer, even if that answer sometimes is less accurate. Lionel Geomag aims to be accurate, and so in a lot of cases it can be slower. It's also thread safe and re-entrant, so it can be parallelized more easily. But you know, there's trade-offs at every step, basically.
Okay, going back a few minutes, I was wondering if some of the issues regarding passing data back and forth between languages could be resolved by using like Cython or Numba. Is that something that you've considered?
I think if you were starting a fresh project and you wanted to build a field model, that might be a good way to do it. I think one of the issues with that is that it kind of limits access to only Python, because Python getting stuff Python calling other languages is trivial. Other languages calling Python is not always trivial. So if
One
you
side
were,
of let me jump in right there. This is Rebecca. One side of Komodo, remember Ensemble, Darren, they're developing an interactive interface between these other languages and Python. Now, it's not implemented on, say, Fortran or C yet, but that structure is there. Maybe that's something that could be used.
yeah, I mean, you can absolutely call Python from C. It's just,
No, that's a two-way
more.
interface that I was talking about.
Oh, okay. I mean, sure. I guess, you know, I mean, it would be interesting to get an update on what that actually is right now. But yeah, I mean, so I think part of the reason that, you know, so like Urban, LAN, or Geomag have had kind of fairly long histories and have been used in a lot of different places is that, you know, they are kind of a low-level language. They can be called from, like, if you're writing some kind of big numerical code, you're not going to do that in Python. You might control it from Python, but you're not going to do that in Python, and you probably don't want a model that's based in Python, whether that's, you know, sort of made reasonably fast using Number or Cython. You probably don't want that for your heavy numeric application. You want to do that in something lower level, and then use Python as your glue to pull the pieces together. So.
Hi, y'all. Not to cut off a really great discussion, but it is 4 and it's been an hour. So I think we need to move on to Rebecca's topic. But if you want, you could suggest to continue this as an unconference topic and chat more if you'd like tomorrow. So just putting that option out there. But to Ashley for serving as in that discussion.
The first time I'm in person anywhere. I first time meeting all of you.
Okay, then we won't. I guess I can share from my laptop.
Maybe we do this with some But it won't be here.
If she has Zoom on your laptop.
Yeah. I suppose, are you also connected to Zoom and sharing on? Okay, that's cool. Okay.
That's what's funny.
Let's do that. Let's just keep doing that then.
I got that one covered already.
You were commenting on that, our backseat right.
I heard that earlier and remembered that comment. All right.
There you go.
Rock and roll.
Looks good.
Thank you. Okay, so before I start, is Gretchen on the line? Yes, I am here. Great. Your T-minus 2 minutes to take off. All right, so this particular session, I'm calling the PyHC Open Science Experiment, and I need to remember to talk into the mic. Like I've been telling 5 other people today. Sorry, I tend to pace from my teaching days. Okay, so I threw my name up here, but there are a lot of names. If I don't talk English today, I apologize. I'm a little sleep deprived. So I will try to keep this good. All right, so let's dig in. We have an hour and a half to do these couple things. We have an invited presentation from the Open Science Framework by Gretchen. I'm not going to attempt your last name. I'm going to butcher that. So she has about 10 to 15 minutes to teach us how the Open Science Framework enables open science and what that even is. Then I'm going to give a project introduction. What is the Open Science Experiment? Hint, it builds on the executable paper that we published last year, and then a tour of the project. And the second theme here is, well, what is open science? What does it mean for heliophysics infrastructure? And particularly, how can PyHC collaborate with or enable such an infrastructure? And then if we stay on time, I have 45 minutes for discussion. Hopefully faster. We'll see what happens. And there'll be discussion topics that are on different slides. And those are all copied to the Miro board. So I hope you all have your computers open and running, unlike I was earlier. All right, so Gretchen, I'm going to pass it on to you. I have your slides downloaded. Okay. So give me, go for it.
Okay, great. Well, hi, everybody. My name is Gretchen Gigan, and I am a product owner at the Center for Open Science. So that means that I work on our platforms, our software platforms, kind of in the place of the end user. So I'm consulting and giving advice and guidance on like kind of what features we develop and how the whole thing works. So I'm going to talk to you a little bit today about open science and our Open Science Framework, or OSF, which is our main platform. So you can go to the next one. So just a little pop quiz to start, which is not really a pop quiz because the answers are on there and I will also provide them right away. But maybe some misconceptions about open science. The first might be that open science is open access, that those two are the same thing. And in fact, that's not true. Open access involves access to published work available openly, but it's not the whole of open science. Open science includes a lot more types of practices that can be involved. A lot of researchers ask us if open science means that their research is going to get scooped. If they put it out there freely, other people will take it. And actually, open science does the opposite. It allows you to declare what your research idea is and document it in a way that you can prove your claim to it and you can create persistent links to it. And when you're openly sharing data and materials for reuse, others can then cite back to you and lead more folks back to you. A final one is that open science requires sharing everything and everything completely openly. And that's also not true. Data sharing and sharing materials in open science happens on a spectrum. The rule of thumb that you'll hear me say a couple times is share as much as you can while protecting what you can't. So any sharing of anything that you can do is better than none, right? So open science can be a whole spectrum of different of the amounts of sharing. So you can go to the next. So what is it? So UNESCO actually wrote a recommendation in 2021 that has a pretty good definition of open science. So open science are open, transparent, collaborative, and inclusive scientific practices. And they're coupled with accessible and verifiable scientific knowledge that is subject to scrutiny and critique. So really what science is about. It also is a more efficient enterprise. It improves the quality, reproducibility, and impact of science, and in turn increases the reliability of evidence needed for decision-making and policy and increases trust. So I'm going to talk a little bit about some specific practices, but in general, any kind of thing that you do that increases these values is open science. I will look at a specific example. Yes, so this comes from immunology, which I know is very different than what you do, but we were all impacted by COVID, so this kind of affects everyone. So since the first sharing of the SARS-CoV-2 genome sequence and the first prototype of a COVID tracking board from Johns Hopkins, based on those two things, different communities who hadn't interacted before were able to jointly work together to fight the pandemic. We saw a surge in preprints. We saw major publishers making COVID papers open access. And we saw more and rapid sharing of COVID data, including virus genome data and clinical trials, and data curation and text mining efforts that made existing COVID data even more useful to identify risk factors and develop treatments. So, you know, the vaccine was developed and authorized in under a year, and a lot of that has to do with this open sharing effort. And go to the next one. However, you may also know that there were some retractions that happened, and that was related to the rapid publishing process. But what you may not know is that these retractions are actually attributable to open science principles being violated, being not followed in the research and reporting process, particularly in the lack of sharing data openly to allow results to be analyzed and reproduced. So the high profile case referenced here related to hydroxychloroquine. I have to slow down to say that. So the initial paper was retracted because they weren't able to verify the data set. It was a proprietary data set. They refused to share the raw data with a third party for auditing. So even though it was retracted, it still got cited heavily. And that could have been avoided if the data had been shared with the paper and researchers and journals were able to evaluate that when taking a look at it initially. So we can go to the next one, right? So why do we suggest you do open science? So I've talked about, a specific example that benefits the community. The credibility of scientific claims is advanced when evidence is available. But for researchers in particular, open science can help increase citations to your work. As I said, it can help you to get credit for not only like papers that you publish, but also data, code, workflow, materials. For the research community, sharing output and documentation increases the speed at which you can share findings. And it can also help document that provenance in the process of the project earlier. And reproducibility can improve and increase access to research outcomes. Additionally, universities and funders want to make sure the research projects that they sponsor are well documented and available to everyone. So many funders have released policies to encourage or mandate open access publishing at a minimum, and data sharing, which is really a bigger part of open science. And they've also started allowing costs of data storage and curation as part of grant budgets. The next one. So last year, the Office of Science and Technology Policy at the White House issued a memo that requires all federal agencies to update their policy to require federally funded research to publicly share the publication and the underlying data immediately without embargo. So based on that last point, we're seeing more mandates like this nationally. And on the next slide, I previously mentioned UNESCO, which was an international organization that published an open science recommendation in 2021. And that was a catalyst for the European Union to commission policies for requiring funded researchers to make their publications available, open access, and have their data as open as possible. And a lot of countries are increasingly implementing things like this. One last point. Overall, we at COS, Center for Open Science, have seen a disconnect between the perception versus reality. These graphs are from some studies done on flu researchers, because again, we have done some immunology work. 50% of the researchers we talk to think that their colleagues support data sharing, but in reality, about 75% of them did. And so, the actual interest in sharing is much higher than the perceived norm. And from the other side, 25% think that their colleagues would be against data sharing when really less than 10% of them were. So we have observed this in some other disciplines, but this is one stark example of how things are changing. If you want to go to the next one. So I am here from the Center for Open Science, and we have a mission to systematically approach culture change. So we work to scale the adoption of open science behaviors by researchers in a number of ways in a kind of ground up approach. So at the bottom, at the most basic level, we provide an open infrastructure called the OSF, the Open Science Framework, makes it possible to do open science. We also conduct extensive user-centered product development, which is part of what I do. And we do that to make OSF easy to use. So it's not only possible, but we want to make it easier. And even better than that, we conduct grassroots organizing to try and increase adoption and cultivate early adopters to make their behavior visible to the community and to shift norms towards those behaviors. We also offer solutions to journals, funders, and institutions to make it desirable to do the behaviors, to provide rewards for it. And we also provide and promote a policy framework for stakeholders to make the behaviors required, the mandates I was just talking about. So this is kind of how we structure our work. And the one part I'm going to talk to you about today is the open science framework and open science practices. So we've been talking at this point about, what kind of high level open science ideas. Here at Center for Open Science, we support some very specific kinds of open science practices. keeping in mind that rubric that I mentioned before of sharing as much as you can and protecting what you can't. So we have tools to help you with data management and sharing, code and materials sharing, pre-registration and registered reports. I'll talk a little bit more about them if you're not familiar. It's a specific kind of declaration of research. We also run preprint servers, and all of these things lead to more reproduction and replication like results. So the Open Science Framework is our main platform or backbone platform for this. It is a free open source online research platform, and it's designed to support researchers openly and transparently sharing their work at all stages of the research life cycle. So the next one. So OSF has three main components: registrations, projects, and preprints. And move to the next one, and we'll talk a little bit about registration. So a registration is a kind of a formal, transparent story of your study. It describes what the research you are planning to do is, and excuse me, it's useful for certifying that you did what you did in a project, excuse me, in advance of the data analysis. You can also update it at stages, so you can take snapshots of the kind of description of what your project is at different stages to confirm kind of the exact state of where things are when you get to manuscript submission or the beginning of data collection. So registrations can be updated, and the registration pulls together a long, description, or you can do a more open description of what it is you're planning to do, and then you can go in and you can create updates. It won't allow you to kind of change it because it's saving it in time in order to show that progress over time. If you go to the next one, projects are more open component of OSF. So it's a collaborative workspace. You can have a project just on your own. You can share projects across anybody in the world. It's an open platform. So it's not like it's hosted at one institution or the other. And there is space to organize materials, data, information about any part of the research process, excuse me. It does create an audit log of changes, but you can go in and change it as much as you need to as your project progresses. So it's an open working space. It's not a kind of formalized capture of the process of going through a project. Projects spaces can be tied to lots of different storage backends. So if you have stuff in Google Drive and stuff in S3 or OneDrive, you can keep all of those materials in all of those places, but have a centralized link out to all of them from within an OSF project. So it provides a space to kind of organize all of your work in one place. Projects can also be licensed, so you can dictate how that information or materials gets reused, and you can also keep them private. So they're not required to be public. And there's no limit to the number of projects that you can set up in OSF. Finally, we also run preprint servers. I think you probably are familiar with preprints. They're pretty well established by this point. A manuscript shared with a public audience without or prior to peer review. If the preprint is being submitted for peer review, we have in OSF ways to link via DOI to the published version to the preprint. Also, if you store data or have a registration in OSF, we have built-in ways to also link the preprint to the data and the registration, so you can create kind of a whole web of all of your materials and outputs all in one place and have them all referenced back to each other. And we do allow the creation of DOIs, persistent identifiers, for preprints, registrations, and projects. So you can also have that kind of unchangeable location that you can share. So finally, this is an example of many of the different types of tools and standards that OSF works in. So we're kind of really embedded in this community. Some of these tools can interoperate with OSF. We've built various parts of OSF based on different standards. So what we're really trying to do is not to dictate that you only use our platform, but to provide a tool to help researchers and stakeholders use maximize the efficiency of using all of these tools together. And that will hopefully increase and advance openness, transparency, and reproducibility. So I have a couple links on here, and I am sticking around for any questions if you go to the next slide. So if you want to find out more about OSF, there's some links there you can copy down, but I will be around for any questions as we move forward. And hopefully that was quick enough.
Yes, thank you. Does anyone have a burning question?
I have a kind of a question about pre-registration. This is the first time I've heard of this pre-registration concept. So I think it sounds like at a high level, you can claim ownership of an idea, right? So you can say the first thing. What prevents someone from doing it anyway? Or what prevents someone from claiming 50 ideas?
Right. Yeah, I mean, there's no way that we could enforce that, but what it does is when the idea of this, kind of open dialogue around these things is that you can have proof that you had the idea. You're not the other person who claims the idea doesn't have that evidence to stand on. You have evidence documented in the record that you declared that you were going to do this.
Okay, thank you.
Right, so Gretchen is nice enough and available to stick around, so she'll be available for our discussion part later. So let's move on to the next piece. Back to here. Okay, thank you, Gretchen. All right, so now we're going to go to introduce the PyHC Open Science Experiment. So that name is subject to change, but so far it seems pretty appropriate. Okay, so where have we been and where are we going? So the PyHC executable paper that a lot of you were involved in and we published last year, thank you, Sean, for spearheading that, showed a couple of things to the community. First, it showed how to collaborate between software developers, software engineers, and scientists. And on paper, not just kind of group knowledge that's group to group, on paper. It also showed how to use multiple PyHC packages to perform a science analysis, which is one thing we've been wanting. We also showed how to produce an executable paper in heliophysics, the first one. That was pretty cool. So what does that mean? It means there's an article published in Frontiers of Astronomy, and then there's a notebook that you can hit go on in DeepNote. After you copy it to your own username, alter it, and build upon it quite directly. Also in text for that paper was documented how this kind of collaboration, how this kind of technology actually supports open science. All right, where are we going from here? Well, the idea is to build on this and apply, extend the science analysis into a full-scale science problem. So this really builds upon the let me get this right, the magnetopause crossing challenge from 2015 that CCMC spearheaded. So with IWA, that is the one we're pure seeing right here. So the website's here and also later in the presentation. Another spearhead here is that we want to demonstrate how to do open science in heliophysics, not just with an executable paper, not something that's just reproducible, but something that's open, that the community participates in from the beginning, and that participation is recorded and properly recognized for each person. We're also using this as a test case. What improvements do we need to make on infrastructure in heliophysics to make this even possible? Okay, so what are the pieces here? This slide should be familiar to most of you, not nearly the slide itself, but the stuff on it. So we're limiting our use case to this small box here that we can use as a test case. So what's the box? Basically the executable paper. So we're getting the MMS data through PySpeedas. We're using SpacePy to get the calculations from the SHU model. Am I saying that right, SpacePy people? SHU-A, I've got to get this right. We're generating fly-through results through physics-based simulations using Komodo. One thing that was missing last time that I want to do this time, Nick, is I want to have metrics calculation scripts comparing model data and observational data built on Plasma Pi. So that's a piece that we need. Now, the two pieces that are new and quite drastically so, are to provide a platform where all the contributors can collaborate in real time or asynchronously as desired, and search and reuse all of the components, not just the data, but their collaborators' scripts, and so they can build directly upon each other's results. And that's being built on HelioCloud. We also expect multiple members of the community to take pieces of this and lead it, not necessarily the infrastructure, that'll be centered more here and more at HDRL and such things, but more of the science leads. Okay, say this person wants to do a machine learning comparison between 18,000 magnetopause crossings and these data sets. More power to you. Talk to Brian Thomas, please, if that's you. You will want to know first. But say that's one project component, and that'll have its separate project component page on the Open Science Framework. And then there's going to be other project components that the different people in the community lead. We fully expect that, and we're preparing for it. Okay, what's the open science half of this? We want to perform the work in the open from the beginning, particularly the science work, once the infrastructure is ready. We want to demonstrate how to perform open science to the community and the agencies and nations that are watching us. So one thing that's unique is with HRL and all of the collaborators and people under that umbrella, institutions under that umbrella, it's a unique and very large collection of heliophysics resources. So what we demonstrate in open science for heliophysics, other countries are watching us. So pressure's on. Let's try to do this right from the beginning. Hence the session today. So along the way with our limited use case to say inside a little play box here, we're going to be developing a lacking infrastructure along the way with collaboration from the Open Science Framework and our collaborators and HelioCloud. Another important piece for the open science part is to create examples of rubrics. Well, how do we decide who gets the second author position on a given paper? It shouldn't just be, oh, I think you did this and I think you did that. There are actual rubrics you can use where people can decide where they should rank in relation to other people and their contributions. That doesn't exist in heliophysics, but we can pull on what's done in other fields and adapt it. And talk to me in November, hopefully at PyHC meeting, if Julie doesn't kick me out. That's the plan anyway. We're going to work on that then. At the end of the day, separate from any science papers, there will be an open science paper published on this project that analyzes what did we do right, what did we do wrong, what lessons did we learn, etc. That's the goal at the end of the project. Okay, so quick project tour. I'll guide you through the 3 parts that we have so far and then take you to the web pages themselves. You have a QR code on the screen. Pull out your phone, scan the code. So what I need from all of you, especially if you already or want to contribute, is scan the code and do 2 things for me. Make an ORCID account if you don't already have one, and then log on to the OSF, the Open Science Framework page, and create an account. Why should you care? Because I can't add you as a contributor if you're not on the Open Science Framework. I can't click the button add contributor. So you have to do those 2 simple steps. If you don't want to scan the QR code, you can click on the link. And how about I do this right now? And nope, wrong button. I am attempting to copy this into the chat. So you can do that there. And Zoom is here, chat, paste. Done. Okay, thank you. All right, well, I wanted to switch anyway. Well, no, not quite yet. I do tend to bounce back and forth. I am tired. There we go. Okay, the other piece is the HDRL's HelioCloud. So I say HDRL's because there's going to be a network of these. That's the plan. Can I say what that APL? Yeah, so APL has a HelioCloud that they're building. Our hope is to have these at multiple institutions, maybe CCMC. I'll just plant that bomb and let it explode later. But maybe at NCAR, say with the data that they serve, maybe here at CU Boulder. I almost said CU Berkeley. I don't know where I am anymore, but I am here. I'm sorry, I'm really tired. But anyway, the idea is that there will be a network of these things, but we're containing this experiment to be on HDRL's HelioCloud to make sure that that infrastructure linkage to the other pieces gets worked out before we expand this to more. Okay, So what is it? Well, Sandy Antunes will give a much better outline of what this is tomorrow. So I'm just going to say 2 quick things, maybe 4. It's basically a cloud computing environment that's built to just work 9 times out of 10. Maybe that ratio is higher. There's executable notebooks so that you can share to other users on the platform. There are ways you can screw stuff up right now, but they're working on it. We're going to be using large file storage, particularly for the physics-based model outputs in S3 buckets, which will motivate some other conversation later. And right now, the initial compute and storage cost is covered by HRL, so they're being nice and supporting this thing because they want open science to succeed. And we're being required to anyways. There's that. The other piece of this is the GitHub page. That is a complete mess right now because it's in severe development, but here we go. It's basically just loosely organized right now. The GitHub page is linked into the Open Science Framework. All the scripts and notebooks in the current state are in the data workflows directory. So if you dig into there, it's going to make no sense yet because we're still designing it. And the software environment information is in the top directory that you see on the screen. It also has a DOI, so you can properly reference it. So now let me switch to my little collection here. So here's the PyHC executable paper that I mentioned earlier. See, it's on Deep Note. You can hit go. That's what executable paper. And as Sasha correctly mentioned earlier, you can't do that for every use case. So we're going to do that for something we've already demonstrated can work and then expand that piece. So don't eat the elephant in one sitting. So the next thing I showed you was the Open Science Framework web page for our project. Here it is. Again, please add yourself on this website so I can add contributors. We have a project description. It has a DOI. It can now be properly referenced. And all that took was clicking a button and waiting 5 seconds. Thank you, Open Science Framework. That was really easy. It was similarly easy to get a DOI for the GitHub, by the way. Notice I scroll down. You can click on GitHub. You can navigate through, double click if you want to open stuff. It's loading. But you can actually look at the files stored on GitHub without actually going to the GitHub website. So that's really cool. Okay, let's go back. All of these things, what we don't have added yet is a link to the S3 buckets on HelioCloud. That's something that's going to be worked out. I'll get to that in a minute. One thing that we want, Gretchen, I'm poking at you at this statement, is what we really want is to have the GitHub discussions linked. Let me just jump to here. Nope, wrong one. That was supposed to be GitHub. Hold on. Yeah. Maybe 2 seconds and I'll get it. I clicked the link and didn't check it, so that's my fault. But here you are. What we really want is the GitHub discussions linked to Open Science Framework, so you can have the same kind of interaction that we currently have for GitHub files. Because the GitHub discussions, it's organized by topic, so you can really search it nicely and try to follow the idea instead of trying to search the long string of Slack messages. Okay, cool. Well, here's what HelioCloud looks like. I got feedback somewhere. It's not me. Okay, well, here's what HelioCloud looks like. Here's where I've been working. So there's some sample data here, sample model data. There's a complete set of model data testing data, if I'm saying that right, in S3 buckets that are public. You can't see that here because this is a different type of storage, but you can open a notebook, even this PyHC notebook. Any users on HelioCloud can open this notebook. Hopefully they're nice and they save their own copy before they edit it. So it'd be nice. Notice this is a big piece of the work that's been done. This environment where stuff actually works all together and on S3. So that's on HelioCloud. But before I get ahead of myself, let me go back to the slides and go forward. So here's how we envision these pieces linking together. Okay, so we have the main project page on the Open Science Framework that I already showed to you. We're planning on having project component pages, which I didn't show because they don't exist yet. But we want that main open science page linked to GitHub, not only as it already is, like I demonstrated, but also with discussions and documentation and some more links there to really pull in the proper linkage and involvement that we want. We also want those pages on OSF linked to HelioCloud, which doesn't exist yet. We want everybody to be able to see, not edit. We want everybody to be able to see the notebooks and scripts and development on HelioCloud. Again, view, not execute, because execute means dollars. You have to have an account to spend money on HelioCloud. That's only fair. There are ways to make that a fuzzy line, but it's not ready yet. Okay, we also want everybody to be able to see the data on S3, but not spend a bunch of money with these LS commands. So that's going to be accomplished through the shared cloud registry that's being developed by Sandy Antunes and Company. We also want HelioCloud linked to GitHub, which is, we think, easy but not tested yet, simply through the Jupyter Notebook interface with these git pull and git push requests that you can do from those notebooks, because we want the work that people are doing on HelioCloud for their individual pieces to be kept on GitHub. Because what if HelioCloud hiccups and the files disappear for a little while, right? Nobody likes that. But yeah, that linkage from not only main project development to the main GitHub repo, but also from the individual projects to those forked repos. We want that linked. The idea at the end of the day is for people to see all of the pieces that are in development and to have an easy workflow. And if you want details ad nauseum onto what that workflow is, I have backup slides. Let's move forward though. But current status is what I was getting into. The project is posted on OSF with the DOI. We have dependency conflicts resolved on HelioCloud. So if you want to play around with that environment, ask Brian Thomas for an account on HelioCloud. You're counted as a contributor. He will say yes. That will be useful for Komodo and SpacePipe particularly, but also any other package. And the software all runs on data in S3 except for SWMF output because it's fancy. The workflows are being planned and developed. I'm not going to go into them much here, but the path forward is to work out kinks in running PyHC software in S3 buckets, which needs to be a discussion. As Johnny Huff correctly pointed out, I need to add the contributors, so please work through that, get your account on there. We're working on linking all these pieces together and streamlining the workflows. Over the summer and into the fall in preparation for the next PyHC meeting, the plan is to draft contribution roles, participation roles, how to manage people, so on and so forth. I need input because I'm not that. I won't comment further on that, but the goal is to have a draft first I'll collaborate on and finalize at the next meeting. And then hopefully we'll have enough pieces together and ready to present something live so that people can start jumping in and participate at AGU. Any burning questions before I switch gears a little bit? Go for it. Mike. Need a mic.
So the intention is not to actually start doing the science, but to get our ducks in a row so that people can jump in at AGU time.
Yes, we don't want to jump into the fray when all of our pieces are still frayed. We want things ready.
And just making sure we were supposed to create an account with the OSF website, right?
You can do it if you log into ORCID first and then log in. You can log in with your ORCID on OSF, but whatever method you use is fine.
Okay, well, when I went to the website, it gave me a pop-up. It's like, hey, sign up to do whatever. And I just clicked it, made my account, linked it to ORCID. So at least one person's done it.
Go for it. Perfect.
You can also link to your ORCID after the fact as well. And once you do that, you'll be able to log in either with the username and password you create or with your ORCID ID.
Cool. So we're going to talk more details about this in the discussion time, but let me pull up the second kind of train of thought that needs to be talked about here before we jump over to Miran. Okay, so I don't need to spend much time on this because Gretchen already did a very good job defining what open science is. But from a NASA and US perspective, the information on the slide is kind of the guiding principle here. Well, kind of actually is. What you see is the open science definition from the White House that we have to align with here and the arguments for why open science. Basically, it's how science should be done all along. It should be an open collaboration where not just the people that look like you or think like you are on the project. Pulling in people that think differently is shown to make your science solve the more complex challenges. And there are a lot of interesting implications about that. And that enhanced transparency and reproducibility that comes with open science and practicing open science means you get more done as a community because you can build more directly on what other people have done. Okay, so here I'm going to run through a few things I've been thinking about with infrastructure and heliophysics. And I'm going to post some questions that are copied onto the Miro board, but I'm posting the questions in light of what can PyHC do here and what should PyHC's role, what do we want that role to be? So these are more thoughtful, hey, this is lacking, what can we do to help kind of thing. Okay, well, what does open science imply in demand of our infrastructure and heliophysics? At the most basic level, it demands that all of the components be fair. So fair is findable, accessible, interoperable, and reusable. A mouthful in and of itself, none of it is easy. We're making good progress on publications and observational data. We need focused development on model data, which has a lot of caveats there, we'll get to in a moment, and software, which is where PyHC should come out shiny with knight in shining armor kind of thing. There's a lot of exploration that needs to be done for software environments and modeling codes, including on what that culture needs to be. I'll leave that there. The great unknown in my mind is how do we treat people and relationships as research components? And that is being spearheaded by the HelioWeb effort at the Center for Helioanalytics. Jump on, it's interesting. So how do you do reproducible results? Well, some have suggested executable papers like we just did last year, but is that the overall answer? Does that work for everything? No, probably not. So what does it really mean to have reproducible results? How deep should we pursue that? What does it mean to have an open process? What does it mean? How do you perform open science in the open from the beginning? What does that really mean on the culture here? And how do we make the collaborations open? What does that even mean? We understand at the basic level, but we've never done it before. But at the base of all of this, fair data and open source software, it's simply not enough. That's not open science. Those are just the bare minimum pieces. It's fine to start there, though. Those are definitely significant efforts that need to be kept on the table and kept in hot pursuit. But we have to look beyond to really know how we're going to piece all of this together. Okay, some of you may have seen a few of these slides last week, but in a different context here. So for observational data, like I said, we're making good progress. We have some shining examples like the MMS data set here. So let me get my mouse to wake up. Okay, so here we have an MMS data set. It has a DOI that's separate from any publication. It's just referencing that data set. And that means that the person who fortunately was first author in some MMS data paper doesn't get all of the citations. It's that data set and no unbalanced recognition of any particular paper. It's the data set. There's also ways to programmatically access the data set. You can do quick plots. You can get the data and download it from the website or through an API like Happy. And the MMS data set I chose because it's being uploaded to HelioCloud. So it's going to be offered on the cloud soon. So that's the standing, shining example here. Not that way for all data sets, but hey, we're working towards it and there's good progress on that. So the question I posed to PyHC is that how can PyHC better advertise our services connected to these data sets? One thing, well, I don't see a link to an example tutorial on how to use MMS on this page. Can we include that maybe in the space metadata for that data set to just pop up somehow? Maybe. I have crazy ideas, some of them are good. So we'll have some brainstorming in just a couple minutes. Now here's model data. I'm not going to spend as much time on it here as I did last week, but the infrastructure supporting model data is far less developed, and there's a lot of reasons for that. I'm going to touch on it as we go through. There's no modern search interfaces. Well, that's because model data, maybe that's because they don't use the space metadata yet. So they're trying to do all of this from scratch. This isn't just at CCMC. Other people have model data too, like APL, where we are right now. We have proprietary codes that generate model data. How do we share that? Okay. DOIs are not assigned, but then again, what model data sets should we assign a DOI to if some of them are reproducible? There's that debate going on. A few of them are available through a website. What I have shown here is one from Swipsy. And there's some examples on CCMC. There's some quick look plotting capabilities available easily through the website, but it's not easy to understand the interface simply because it's not a modern design on that web page. So younger people like me look at the screen and go, huh? What is this? But I'm not the only one. There are power users that convince me, no, it's not just me. But how can PyHC help with these issues? Should it really be all burdened on one organization trying to tackle all of the domains? Or can we step in as a community and partner on this? I have a lot more ideas on that later. There's a sustained push underway to open source all software, including modeling code, as long as it's developed by taxpayer funds. So keyword, developed by taxpayer funds, okay? Because this is something coming from the White House, coming from NASA. It's not coming from the military, okay? But then again, open sourcing software is not enough. We have experienced this ad nauseum in PyHC. You can't just open source it and use it because that doesn't make it usable. We have dependency conflicts. Just because it's on GitHub doesn't mean you can install it. And just because it's on GitHub doesn't mean you can run it on your machine. We need documentation. Well, how do we do that? That takes time. Hinting on Sean's thing that he's going to present later. I think that was tomorrow or Wednesday. Tomorrow is Wednesday. Okay. Can we run our softwares on the cloud? Should that be a standard? There's the whole maintenance problem. How long do we want to invest in this code to keep it reusable, so on and so forth? I am convinced that PyHC should take the lead here, but not just on PyHC packages, on general programming standards and programming resources. So not just Python, also Python interfaces to other languages. Where is that knowledge in the community, and how can we put all that in one place? What paths forward are the easiest or the best to get a quicker result? Well, where is this all going at the end of the day? What's the vision? Two pieces. We want a distributed data infrastructure system where all of the observational data, model data, and eventually even modeling codes are hosted by different institutions, but searchable through a single interface. So we can find all of the pieces with one search. So, but all accessible with different methods, because people want to be able to choose whether they want to download that observational data to their own machine or run it on the cloud because there's too much data for their machine. They want to be able to rerun that model code if it's simple enough for them to understand and run their own 10,000 different versions of that thing so they don't have to go slap all of this on CCMC and they go, why? We need money for this. Are we burdening the infrastructure too much? Should we spread this out? Okay. On top of all these pieces as they come together, we can build a collaborative analysis infrastructure, such as the one in the PyHC Open Science experiment, where all of the software is already installed. We can, people can reuse and re-execute things that were done before in that environment and build directly on it without having to write it themselves. But again, searchable through connected metadata. I'll pose a hot question because Xing probably isn't listening. And if he is, great. Is space metadata model enough? And if not, what do we need to do this? So maybe that's not a question for PyHC, but how can PyHC prepare for, collaborate with, and enable these infrastructures as they come together? So now it's time to discuss. So let me introduce you to the format here. The board you're about to go to, looks something like this. This is a Miro board, and it's for open participation, not only for the people in the room, but also for people online. I'm going to post a link to this Miro board in the chat. You can create an account if you want to, or you can be the anonymous zebra if you want. Doesn't matter to me. But the idea is that we have 4 different frames of questions to work on in just under 45 minutes to split between them. So the idea is you're going to write your idea on Post-it notes, and we're going to be discussing these things as we go and trying to brainstorm what we can do for each piece. So I have a QR code here. I'm going to copy the link into the chat and then move to the Miro board myself to show you how it works. Where's the chat? I am flipping back right now. Go for it. I'll leave it up for a minute. I just wanted to throw that link in the chat first. So Julie, I will attempt to watch the time, but help me out. Give me a 5-minute warning. Tell me when it's almost 5:30. All right, well, let me go to that link myself. I pulled it up earlier. Okay, so it's loading, cool. So let me give you a little tutorial on how to drive this thing. And this is why I wanted my mouse. If you just click and slide, you're gonna be moving things. You have to right click and slide to actually slide around on here. What I already have set up, trying to do this on the laptop, is some sticky notes here. You can grab one, move it, and start typing by double clicking and type here. For instance, click outside of it to make it stay. You can grab a new sticky note by clicking on this icon here, and they have a couple rainbow colors, whatever you want to do. All right. All right, so the first question, we have a mic somewhere. That's kind of hot. Thank you. Okay, so the first question I want to focus on here, let's give it a couple minutes, probably at least 10, because this is our main topic. Don't move my friend. Control Z is your friend, my friends. Control Z will undo anything, mostly, not on Linux. What PyHC software changes are needed to better support the open science experiment specifically? So this is what I'm talking about is this piece we're building on HelioCloud that expands that executable paper. And what needs funding? We don't work for free. So let me say this here. We don't work for free. Open science and open source software development should not be done for free. So if these things need funding, don't try to do it in your free time. Let's bomb the HTM proposal thing with as many proposals as you need to get funding to get the point across that we need more funding to do this. And then NASA headquarters will get that message. All right, I've said my piece there. So I'm going to let people add sticky notes and I'm going to be quiet for a few minutes. Think about it. I already threw my ideas in there. The link's in the chat. All right, let me get back there. Hold on. I still have everything up. QR code's there. I'll leave it there just in case that's your preferred method. Fair point. And let me switch back to Zoom. Why am I only direct messaging Gretchen? I don't understand that. Some sort of Zoom thing. All right, so now everyone should have it. Thank you, John Vandergriff. I see that in the chat. All right, so everyone should have that in the chat. And QR code one more time. All right, mirror board. Grab a mic. Grab a mic.
So PyHC is separately funded things that have been awarded through various grant processes, right? So they're, unless they signed up for this specifically, they're not really funded to do it. This is bigger than PyHC, right? This is the HDRL level like initiative, right?
I thought about renaming it after I submitted my slides.
Right.
HDRL.
No, it's good for, I mean, this is a community that will benefit from it and likely to engage rapidly because all the things that it takes to do this, people here understand them more so than say people who are more focused on just the research part.
Yeah.
And for whom open science is more scary. So help us with, you know, when you say what PyHC software changes, maybe read the ones that you have there, kind of like prime the pump for us.
Sure, sure. So in the development that I've done so far on Helio Cloud, particularly trying to get the packages to run on data stored in S3 took me the most time out of any of the other tests. Thankfully, I had Komodo experience, so I had that behind me. And Darren and Lutz were great helping me out. But I couldn't get the SWMF global magnetosphere outputs. I couldn't get that to even open when it was stored in S3. So, but that begs the question, what should the global approach standard be for how PyHC packages deal with data on S3? And also, what do we do for data that's on the cloud but not H3, like in Zenodo? I forgot who said it, it's in my notes, but there's more than one option. We want users to be able to choose to download the data to their machine and then run on it. But we also want the code to run on data stored in S3 for cloud access. And what if that's a ZAR format for a crazy example? How do we deal with that? I think John wants the mic.
Yeah, I think it's really important to not ask the question, how do we access stuff in S3, but how do we go beyond local files? Because we've been spending, well, 5 years in this group and more than that in the community, trying to unhook ourselves from RSI, ITT, Harris, L3, whoever the heck they are now. And if we just turn around and say we're going to glue ourselves to the hip to Amazon, we haven't really benefited. So we need to think about how do we use that stuff when it's available without locking ourselves back in a different cage.
And we need a way to test that access.
Yeah.
Put those on sticky notes. Add it to the mirror board. Perfect. Perfect. So the piece that I did in Komodo to just make it work for this example ties it to AWS S3. But it's flexible enough to work on either local files or S3 files. The kind of bumbling way I figured out how to do it, I modeled the approach after what I saw for H5 NetCDF, which Xarray is built on, and also the NetCDF library, because they're flexible enough to take either the file name location on the computer or the name location on S3. I didn't test it beyond that because I didn't have access to those things, but that's what I modeled the approach I did after. Not saying that's the right one, but it at least works this way. So yeah, throw that in the chat. I see a comment. We need funding for long-term maintenance of code. Absolutely agree, but we need to think about what code. What code should be maintained long-term? How do we determine whether it's still being used by the community? What metrics are we going to put in? He's like, did you put that in there? How do we determine what should be supported versus not? Take it away.
Yeah, I think part of HTM requirements is to write what metrics would you use to evaluate the success of the code. And frankly, like, okay, we have number of forks, number of stars. I don't even know if we can track number of clones that has been made, but I think with enterprise, you maybe can, but I don't know, like, what is the good metric of tracing how popular is your code and like how many people actually find it useful, except of like finding someone who acknowledges you or like find it reference in the paper, which a lot of people don't put the reference like on acknowledgement because they forgot.
We need a standard where software citations are required, but how can we cite software that has no DOI? Teacher face here.
GitHub is enough.
Okay, so the process, you saw that the magnetopause crossing GitHub that I made, it had a DOI. It took me 3 minutes to get that. Literally 3 minutes. And I'm kind of, in my own perspective, a bumbling fool on GitHub most of the time. Okay. It was put it on, I followed directions that GitHub has on how to put it on Zenodo, do a release, and then you get a DOI. I screwed it up 3 times, I'll admit it, but it happens.
So I think another aspect of this is to try to see what we can do to figure out practices and infrastructure so the need for long-term maintenance of code bases is minimized. Because, I mean, 100 years from now, people will probably still want to use data from AIA or XRT or what have you. And the original computing environments that were used to obtain and prep and calibrate those data will be completely unavailable.
So the 100-year question, I don't know if we can even tackle that, but we could focus on 5 to 20 years and definitely think through that.
I mean, things like virtual environments, I think, for some sorts of analyses seem like that could be part of the answer.
Throw it on there. We're about to switch topics to the next one. You scan through here. Yep. Oh, here's a question. Should a DOI for the software be a requirement to be a PyHC package? I saw DOI and PyHC and that popped into my head. Maybe that was the same sticky note. Sorry if you're jumping on it. Okay. So in the interest of time, let's switch to the second topic that you see on the screen, which kind of links to that DOI idea anyway. So the second topic is how can PyHC better advertise data access and analysis support in PyHC packages? The things I threw on there was maybe generate a space metadata record for software to better link to that searchability in HRL. Maybe there can be some way to put links on those pages that host those data sets for easy analysis. My pet thing I would love to see at CCMC, like for a given data set, you have all the links to download each file, and then click, I can visualize in Komodo. Or click, I can visualize this data set for the CCMC visualization. Or click, my dream right here, I can visualize the solar physics data in SunPy. Modeled solar physics data. I told you I have crazy ideas sometimes. Some of them might happen. We'll see. But okay, so I'm going to be quiet for a minute or two, and that's y'all brainstorm on the second question. If I see some sort of sticky note that pops up and grabs my attention, I'll poke at it. Julie, this will be a record for you for PyHC stuff too. Other than screenshots. Work on that. So one thing I see on here from that has been discussed before is about improving a keyword usage or search on the PyHC projects page, +10. That may require additional funding. So maybe that's an HDEE thing that could be worked in. Because that's an infrastructure, not particularly Python code or software in particular. I'll add that to my notes. Would anyone like to jump in on some idea they're trying to pull together? Go ahead. Oh.
I can jump in.
Okay.
Go ahead.
Who is this?
Daniel.
Hi. Go for it.
So on Brett's diagram, where the last step before making open science required was making open source rewarding, we should, to get people motivated, we should advertise how it's rewarding. And if we can't really figure out how it's rewarding right now, we should maybe reconsider how we can make it more individually rewarding. I think we're all on board that collectively, as a community, the community benefits, but people act individualistically. And what are the individualistic benefits right now? How is it individualistically rewarding?
You're poking at me. So there are 2 pieces in my mind to this. Some of you may know that I led a white paper that address this topic in the context of research software engineers that we submitted to the decadal survey. Daniel, I don't remember if you were on that paper or not. There was a long list of people. Longer the list, the better the result. But the two pieces I would think is that just like there's a push to cite data sets in journals, there needs to be a push to cite the software, particularly with DOIs. We already mentioned that. But once that push begins, there can be a push to recognize that in the peer reviews and the I think annual reviews that people go through for their performance and contribution. When they get reviewed to get a promotion or a salary increase or based on their performance, that needs to start being included. And to be honest, that's a culture shift. It's pretty strong in the earth science and geosciences. We need to make it strong in heliophysics. Throw that on the board, please. You should be able to just be an anonymous person. Well, create an account. Write it down somewhere if you feel like remembering it. Is the chat being recorded, Julie? You could put it in the chat and it will be recorded. It'll be difficult to copy it over. So if you could get on the mirror board, that's the best way, but chat's second.
So Rebecca, in your reply to what I said, you talked about a lot of things that like it should be this way. You know, people should be citing software and it should be a factor in promotions. But like, what about right now? Like, what motivates me right now to open source my code? Or maybe we're not at that stage where we're making it possible rather than making it compelling for everyone in the world.
Well, what's been handed down for taxpayer funded things is that we're required to from now on. It's a requirement for all NASA ROSES proposal calls. You have to agree to open source that software. So basically,
right. So what makes it rewarding to open source it well?
Ooh, the word well. I like that one. That's kind of the differentiating piece here. How to do it well. For now, it's simply not, because the people at the top of the chain right now don't understand what it means to open source something well. They're reacting to a requirement being put on them from the White House to just do it. So the satisfaction in doing and open sourcing something well, from my personal experience, is when someone else uses it. And your work isn't just it's on a closet on GitHub somewhere, right? When someone else starts using it and really having that deep interaction with the code, it's like, hey, what I did is useful. So I think the word is, well, that's the wrong word. I can't think of the word right now. I'm pretty out of it, but personal satisfaction so far.
Yeah, so it kind of sounds like what you're saying is that right now there's the push to open source, period, and not necessarily identify the identify the advantage of doing it well. And my own prediction maybe we'll just have to wait for NASA to get accused of open sourcing a lot of poor code before people shuffle around to say, oh crap, we have to do this well.
Well, I also think by the time we get there, there needs to be several shining examples of how to do it well. And I'm convinced that should come from PyHC.
Great.
And this is Asha again. I want to just elaborate on the note that I put about advertisement. What I'm mostly thinking is a general awareness of the code, and not about running as like a session where like all contributors of PyHC will get together and share the updates, because that stays within the people who work on no PyHC. But there should be a way to maybe demonstrate like or pitch that PyHC is a great tool to solve this task, right? And then people will think, okay, maybe I should give it a try, because people who don't know or do not work with PyHC, they do science somehow in different way, and they the idea is to find this like intersections between what they're doing and what PyHC is already doing better, and let them know about that.
They will argue with you on the better.
Yeah, of course, like I'm advertising for MATLAB, but let's not go this route.
In the interest of time, let's shift our thoughts on to the third topic. How can PyHC help with accessibility issues for model data? So this is one I threw in here, particularly because I'm convinced that model data that problem of accessing model data isn't just a CCMC problem. It's a community problem. It's across all of the domains. All the institutions that have that create model data need to think about this and contribute to how this is done. I put a few thoughts in there. Here's one. So pulling on Komodo as my background for the past couple of years before I transitioned to this task. One of the real hurdles in getting model data functionalized in Komodo is getting that interpolator in there. There's several models where the basic interpolator in Python and SciPy it's called from C, that works fine. But most model outputs are going to have their custom things they want done because they want their model data represented well in a given package. Unfortunately, those interpolators are not typically in Python. So I think one way that PyHC can contribute to this is to provide, here's how you interface to this language and do it well. Particularly Fortran. Spaceby.
I'm not sure how well,
How do we do it well? So there needs to be some community pull together here where we figure out how to do it well from Fortran, from C, C++, particularly programming languages that are free. So sorry, IDL, it's not free. That's part of the reason you're writing PySpeed as. So that motivation there. But how do we do it well? And can we go both ways? That's something a software group needs to figure out. PyHC.
Yeah, and I think in terms of doing it well, there's really like a minimum viable well that goes pretty far. I recently went through the top cited 20 top cited ML papers in the last couple years, and most of them have open sourced their code, but most of them are just doing the minimal viable open sourcing of code where there's an Anaconda environment.yaml or a requirements.txt for pip. And the versions are pinned, but most of it, the rest is you're kind of on your own, and it gives a big bang for the buck. And they don't have to create a Docker deployment or a fairly involved procedures for open sourcing their code. I just wanted to pitch that idea of like a minimum viable thing that gets people pretty far without detailed involvement.
Can you put that on the mirror board?
By saying accessibility to model data, does it mean model the results of the model, or the actually or the actual like model that can be run like locally? Or
I am particularly focusing on model data, not modeling code here. So until modeling code is open, we can't really tackle that.
So with the data then, it's really a question of like where this data is hosted and how those files can be accessed, because PyHC already provided some of the tools like Happy to access the data. So I don't see any difference to provide the similar access to the model results. Well, if they can be accessible via like HTTP or some other like methods.
So PyHC particularly cannot tackle hosting model data. That's an infrastructure chain.
Exactly, but I think
serving it.
I think before like there is an infrastructure that can host those modeled results, how is it possible to even talk about accessing the data that is not accessible? Like,
because some data is public and you have some data and you have some modeled outputs, so on and so forth. If you work it out for something you're familiar with and plug it into something that already exists, my favorite is Komodo. Maybe that's, well, not opening that can of worms, but that can still be worked out now.
I think finding the science use cases to drive this is important, right? Not
We're
just
doing one.
right. So finding things that I haven't done too much with the model data, and that's largely done by people that are collaborating with the modelers, and there's various levels of that, right? So, you know, finding out, I think this is partly where CCMC struggles sometimes, is to try and connect with the, because they have their own mandate, their own agenda, but it doesn't always coincide with where the modelers really want to go. And so trying to line that up better, that's more of a CMCC thing, right? So PyHC can't really control
Backing
that.
away from that one.
Yeah, I know. That's political danger, even saying that out loud like I did. So
Right, forge the path.
yeah, but I don't think we're going to change that. But the idea of trying to find out what are the pinch points in using the models and addressing that.
Using model data.
The model data, yes, that's what I meant to say. Thank you.
Would it
The
be
model-
sufficient?
Go
Sorry,
ahead.
Would it be sufficient to kind of mandate the inputs to the model? You know, like run this script and you'll reproduce the model outputs. It's not 500 terabytes of data or 500 gigabytes of data, but in the name of openness, if you pull this script, you can reproduce it on your own supercomputer.
So Daniel,
That's very
two
hard.
pieces here. One, I was focusing on modeled outputs, not running models. I do have that idea written down somewhere though. But second, we can't tackle that yet because it's hard to run the model codes unless they are containerized. And even then it's problematic. I mean, this already exists in weather and terrestrial weather prediction. Like Maxim was telling me a couple months ago, their modeling codes are open sourced and containerized on the cloud, but they're complicated to run, so people still get hired to do it for them. CCMC isn't going anywhere, even when the modeling codes are open, containerized, and so on. But this is PyHC. We don't deal with running models, we deal with data. So I was trying to focus that conversation on how do we make the model outputs more accessible. Reproducibility, let's get there soon.
Well, I'm not talking about reproducibility. I'm talking about the science use case. And maybe I'd like to hear what John said. But the science use case is I want to be able to take the model outputs from this paper and do something with it. I can either, and there's two ways to fulfill that. You can download the model outputs yourself, or you could go down the path which has been said to be difficult of recreating the model outputs from like a seed script or something like that. But I don't think it's when we're driving this by a specific use case to say that they're different.
Well, that idea was floated last week at the ISTP Next meeting, of this idea of, oh, we don't store model outputs. They're too big. That's expensive. We'll just rerun it whenever we need to. And all the modelers' eyebrows go up and they're like, what? You can't do that. You know, it's so hard to set everything up, and you need these supercomputer experts and just to support that random, oh, hey, let's rerun this again. Who doesn't have extra Pleiades hours laying around, right? I mean,
well, at least for CCMC models, could you just upload input script to CCMC and fulfill the CCMC models?
Right. So there's different levels of activity here, right? There's some of the like super, I'll say hardcore cutting edge modeling stuff. It can only be done on supercomputers. We are so far from being reproducible that that's not part of this conversation.
Yep.
Right. And even the, I'll say in quotes, simpler stuff of reproducing what CCMC has, that's also even not on the table. That's still hard because you got to capture the model inputs and the infrastructure and computing setup that's needed. That's still really hard. So sticking with, we have model outputs. We want those to be democratized. Lots of folks can get connections to a modeling team and run this event for me. And then that will generate your 40 terabytes. And then that's yours. You can write papers.
And
Should it be theirs or public with a DOI?
well, public with a DOI, but it's theirs in the sense that you put it on this open science foundation and you claimed it and that's your thing. That's what you're doing.
Yep.
You don't own the model, but you got the modeling team to get you a piece that you could work on. That's what most people do. And so I think having PyHC help with that process, that turns it into more similar to what the data analysis thing is for mission data. You don't own the mission, but you got the data and you're working with it and you found your study, you want to do this. So I think that's what you're trying to focus us on. Is that correct?
Close. PyHC doesn't particularly focus on metadata. So that's space, idea, so on and so forth. So, but focusing on how, once that data set is there, how can we make it more easily accessible without just downloading it? Once you download it, what do you do with it? That's the piece. That's the piece that we need to do. And it's not just a Komodo problem. It's a community problem. That's, yeah.
Right. And
last thing before we change
Thank
topics.
you. Thank you for elaborating on the difficulties with that.
Sure.
Yeah, I
Thanks,
probably
John.
have an answer to your question. So I still think the data should be accessible, like not the data, but the model should be accessible somehow. And then CCMC over the years has actually built this infrastructure, collecting all different models. And the initiative should really be like coming, not maybe from CCMC, but supporting a lot. That's the modelers who participate in CCMC, because a lot of them do. And this is how you advertise your model, essentially. Provide an interface for others to work with that data. But this is, again, we're coming to the problem. So if I'm developing something for CCMC for Verb, it's extremely difficult to get something running on the CCMC, so it gives you back some images, versus if you will be able to download something or download the slice and then use any other Python developed software, including Komodo, that would be great. But the first step is to provide this access from CCMC, maybe in some sort of unique like a standardized format. If it's a relation-based model, that's the standard, period. And I'm really hoping that's happen in the future.
I proposed it. We'll see what happens.
Yeah, we propose it too. We're waiting on it. Yeah.
Different pieces. We'll see.
But I think it should come from both from CCMC and PyHC together towards like getting the access of the model results from CCMC in any possible way. And on top of that, there is a layer of Python analysis code.
I'm poking at that Python layer. So before I switch topics, let me throw the curveball. It's not just CCMC that can serve model outputs. There are modeling centers at other places. So let's be realistic. CCMC will never host all of the models that we produce. There are toy models, there are things that are just complex, and some people just don't want to. Let's be frank with that. So there are other pieces that we can eventually stitch together with this distributed system that I talked about earlier. So at the end of the day, it's primarily a CCMC thing because that's the biggest resource we have and a very valuable one. But at the end of the day, it's going to be a distributed infrastructure.
Baby steps. Maybe CCMC should show an example.
Jumping to the next topic. Last topic in our last 9 minutes. Sorry for the short change on this one. It's been a good discussion now. I guess that was a good leading comment, actually. How can PyHC prepare for, collaborate with, and enable the next generation of infrastructure? One thing that Brian Thomas mentioned before that I'm going to reiterate because I definitely want it. I want a PyHC containerized software ecosystem that's referenceable and stuff like that, because that would have made my work so much easier on Halo Cloud, just for instance. But that needs to be a task that's not just on Sean, for instance. That needs to be something that at least the core packages pull together and actually work on, like you did for the summer school last year. That needs to be done at least once a year so that the community has a resource. They download whatever environment it is, and it just works on their machine. That's really where PyHC can do something low-hanging fruit right now. We could even do it at the next meeting up to leadership. Or maybe that's a dedicated summer session we need to have. I don't know. But I've talked enough about that one. So I'm going to be quiet for just a few minutes and, well, maybe it's already populated. Some people jumped ahead. That's fine. That's fine. Let me give you a moment to think about it in context of conversations we had recently. I did, like a week ago.
And there will be a hackathon on
Go
Thursday.
on the mic.
Put together.
On the mic.
Think that one big.
Yes. Just piggybacking off the note of we need that darn Python environment with all the packages. There will be a hackathon on Thursday that I'll be leading to try to do just that. We got a list of 156 versions of the 156 packages that I think are required to pull in everything. And in theory,
You
it
just
should
made
work.
that more complicated.
So I know there's going to be complications beyond just like pip dependency versions, but darn it, we're gonna try on Thursday.
So I suggest a starting point or the instructions I have for the one on HelioCloud. Now that notably excludes SunPy and something else I can't remember off the top of my head, but that's at least works on HelioCloud. Okay. And that's on the GitHub. So I see a comment about funding for a software engineer that focuses on packages and docs and testing infrastructure. Submit a proposal. That's HTM stuff. Submit it. Go for it. All of you. We need these people. We need them supported or they won't stay. Ooh, I like this question. Is Docker a viable package system for prereqs and code to work? I have not even successfully run Docker on my machine. So let me pitch that to the group here.
I mean, to reiterate my point before about like the survey of open sourced machine learning papers that I would looked at, I mean, because nominally, I think most people would agree to some degree that that community is ahead of ours in terms of publishing code. Most of them were not Dockerized. And I kind of have this gut feeling that if that community isn't Dockerizing all of their papers, we're probably not going to get there either. But I would love to be proven wrong.
Well, I wasn't saying Dockerizing all the papers. I was saying make a PyHC software system that's containerized so that people can download it and just do their analysis in it, and it just works. But bless you, containerizing, say an executable paper, that's what Deep Note is. That's not being done on HelioCloud, for instance, so it's not always a workable solution. You need a mic. John Niehoff wants the mic. Take one down, pass it around.
Yeah, and honestly, maybe this should be not necessarily next meeting hackathon, but a Zoom hackathon. I can see it makes a lot of sense for us to sit down and just attack this problem a lot of different ways. Why don't we try Docker? Why don't we work with VNVs? If we have a good virtual environment, we just slam that into a Docker container and have it there. Because again, people want different approaches, and we may be able to solve the problem in a couple of different pieces that can come together in a lot of different ways.
That would be great for accessibility, have more than one option.
Yeah, and hopefully not have to repeat stuff too.
Quick question, where is this magical hackathon happening and can I join?
Hold on, passing the mic.
Yeah, so it's going to be Thursday afternoon. It'll be the PM session part of this meeting and the final thing that we do for the last for however many hours y'all feel like sitting here and working. But it'll be here at last. And of course, there can be Zoom components and we can organize that better, day of and figure out who all needs to be in what areas for that.
Don was trying to say something.
Just a quick comment on Docker. There are some institutions that don't prefer Docker, like for security reasons, because of the way the containers require, like root access kinds of things. They don't let us run it on our laptops at APL.
Singularity would be an alternative.
Singularity is better because it doesn't require root. So that's why more options is better. If you're running in the cloud, I think it's less of an issue because it's just a cloud machine, no one's as concerned about.
Get a mic. Get a mic. There's two mics.
Also, Docker as a company has kind of like pulled the rug from under people.
That's too bad.
By having to charge for charging for like Docker on Windows and stuff like that. I think the variety is the better.
If that's
I
starting
didn't
to
want
get
to say container. Sorry, go ahead.
It's my computer, sorry.
If that's starting to get too onerous, it seems likely that somebody will come up with a more open sourced alternative to Docker.
Yeah, there's one by Red Hat called Podman, which is supposed to be mostly compatible with Docker files.
Can you put that on the mirror board? That name?
Sure.
Like stick that sticky note close to the Docker one. Thank you.
The other thing is with respect to root access, I mean, it's kind of doubling up, but you could just run the Docker container in a virtual machine, right?
I haven't run Docker yet, so y'all.
I mean, a person could.
I have to pay to run Docker on my machine, so that's a complication.
Right.
A lot of IT security that doesn't like Docker also doesn't like you running your own VMs on your desktop. I don't know what it's like.
I'm allowed to.
Well, yeah, to be fair, I don't understand why Docker should be like a kind of requirement, because that's what I'm hearing. So Docker is a tool that's useful for certain applications when you build stuff. I think none of the PyHC packages are necessarily have to be like Dockerized, because you can do it yourself. If you need something to build Docker upon Docker, like in the Kubernetes, or connect them all together, then you can do that. So, and since it's all in Python, you can run Python and Docker and pull any packages you want. So I think Docker is more about, can you run this on some other machines than yours? And with the Python tools that we have, I think yes. So
I beg to differ from experience. I could not get this stuff to install. I have notes from 15 trials to try to get this stuff.
It's a different barrier to entry, right? For some people, running a Docker is not that challenging, but installing 10 packages in Python and getting them all to talk to each other, that could be quite challenging. So you can't just say, here's the recipe, do it yourself. And they want to go spend a week fighting through that. In a lot of ways, software engineers are familiar enough with Docker that you hand them a Docker link, they can know what to do with that, but they don't want to be building Python packages from source or from Git or whatever.
So
multiplicity and stuff like the CDF-C library, which you need for PyCDF, you have to compile it, and like a lot of people don't like or feel comfortable compiling C code. But if all of those steps for the compilation of a CDF library are in a Docker file, that subtracts it from something they have to do.
Yeah, multiplicity and options will be.
Or gosh, if that were actually compiled and thrown into the binary wheel.
We're running overtime. Last chance for one comment. Go ahead, Daniel. You were trying to say something?
No, I have nothing to say.
Okay. All right. Thank you for your participation in the session. I'll hand it over to Julie to close it out.
Not much to say except see you tomorrow at 9, same time, same place. Yeah. Oh yeah. But yeah. So thanks everyone. See you.
Cool. I can stop recording.